All right, people. I believe everybody of you is doing great, nice, and absolutely fine. So, welcome to Unacademy NEET English. And if you have not liked the session yet, I would want you guys to smash the like button as soon as possible, because liking the session is marking the attendance, okay? And marking the attendance is extremely mandatory. All of you guys smash the like button as soon as possible. Okay, and call up your friends, because in this particular marathon we will be completing 7 chapters. Okay, extremely important chapters, high weightage chapters, I must say. Like you have ray optics, okay, and optical instruments, both ray optics as well as the optical instruments. Like you have the wave optics, like you have dual nature of matter and radiations, atoms, nuclei, like the complete modern physics. You have the semiconductors and you have the alternating current. Okay, so all of these chapters will be completing in the today's session. So I would want you guys to call up your friends and smash the like button and light up the chats with the fire emojis. Everyone means everyone. I would want you guys to boost my energy, okay, because that is very much important. Then only we can cover these chapters, then only we would be able to cover these chapters, otherwise it is not possible. Okay, so this is a mega marathon. And one more important thing I just want to tell you, sir, will you be starting from the scratch? Yes, I'll be starting from the scratch. But the point over here is, I'll not go into the depth. I'll not teach you guys the derivation part over here. Okay, the amount of information which is required to solve the problem, I'll be giving you that only. Okay, we don't have to talk about the unnecessary stuff at this point of time, because we have only 3 months left for the NEET. So in this much amount of time, we are supposed to study, we say, the concepts and the application of the concepts and the problems. That's it. We don't have to go in the depth part. We don't have to go into the derivation part. You guys can skip that for sure. Okay. Okay. So I would want you guys to let me know in the chats. Shall we start the session? Shall we start the session? I guess everybody has joined. We need to start the session. And the first chapter, basically, I'm starting with, that is the ray optics only. Okay, that is the ray optics only. Now, guys, let's dive into the session. Let's start the session over here. Okay. Now, my dear friends, these are the 7 chapters that we'll be covering. Okay. Once again, I'm showing you the list of the 7 chapters. And then you have got the first chapter, that is ray optics. Ray optics is an extremely important chapter when it comes to the NEET and JEE. For NEET, you can expect 4 to 5 questions from the ray optics. Okay. Now, my dear friends, the very first thing that we need to learn in this particular chapter, the first topic that we need to learn is we say a reflection of light. This is the first topic that we are starting with. Okay. Now, my dear friends, listen to me very carefully. Listen to me very carefully. What is a reflection? When it comes to the ray optics, in ray optics, we basically discuss light. We talk about the light. And one more thing I just want to tell you over here. When it comes to the ray optics, let's suppose I say I have got a light source over here. Okay. Understand this very carefully. This is a light source. Sir, what is a light source? From which light is coming out? There's a bulb, there's a torch, something like that. If I say light is coming out of the light source, means I will be considering this light as a straight line, or the ray. In case of the ray optics, we'll be considering this light which is coming out of light source as, this is a light ray. Sir, in modern physics, what we will consider this? We'll consider these are the photons coming out. Sir, in wave optics, what do we have to consider over there? Over there, we'll be considering this is a wave coming out of the light source. Okay. As of now, when it comes to the ray optics chapter, we will be discussing about light. We will study light. And when I say light is coming out of the light source, means it's a light ray. It's a straight line. Keep that thing in your mind. So the very first topic over here, that is reflection of light. What does a reflection of light actually mean? See, guys, let's suppose you have got a surface over here. You are throwing an object. Let's suppose there's a ball. you are throwing a ball on this surface. What is going to happen? Sir, it will be reflected something like this. So this is the reflection of the ball. But in this chapter, we have to see reflection of the light. Like ball reflects, in a similar way, light also reflects. Now guys, listen to me very carefully over here. Listen to me very carefully over here. See, I'm taking this surface over here. This is called the reflecting surface. Okay, this is called the reflecting surface. I'll mention over here. This is reflecting surface. Okay. Now, my dear friends, if I am saying a light ray is coming out from the light source. There is a light ray which is coming out of the light source. And this light ray falls onto this reflecting surface. This can be the mirror also. It falls onto the reflecting surface, on this surface. What happens? Like the ball was reflected, in a similar way, this light ray will be also reflected. If light ray falls onto the surface, it will be reflected. Now guys, see, this light ray which falls onto the surface is called incident ray. This light ray which is reflected is called the reflected ray. Okay. And from which it is reflecting, it is called reflecting surface over here. It is called reflecting surface over here. Now guys, if you draw a line over here which is perpendicular to this surface, which is perpendicular to this reflecting surface, this line is what we call the normal. Okay, normal is perpendicular to the surface. Now guys, this angle between normal and incident ray, angle between normal and incident ray, this is called angle of incidence. And this angle between normal and reflected ray, this is called angle of reflection. Okay. Now guys, this angle, if we say this is angle I over here, sir, angle between incident ray and reflecting surface, we call it alpha over here. And here, angle between reflected ray and reflecting surface, this is angle alpha also over here. Why? Because these two will be equal. Now, as of now, I have made you explain the diagram. Now, what does the law of reflection say? The first law says that, take a look over here. The first law says that the incident ray, this ray, the reflected ray, this ray, and normal, all lie at a point of incidence, all lie in the same plane. So this ray, and this normal, all the three are in the same plane. You can see these are in the plane of the board. Okay, they lie in the same plane at the point of incidence. Okay, I hope this is clear till over here. This is the first law. All the three lie in the same plane. Then you have the next law. Next law says that angle of incidence is equal to the angle of reflection. This angle of incidence is equal to the angle of reflection. This is the second law. Okay, there are two laws. One more important thing I just want to tell you in this particular case. Sir, this angle, I can say this angle alpha, and you can call, let's suppose this is beta over here. This angle alpha will be equal to angle beta. Sir, these two also will be same? Yes. Why? Because angle between incident ray and reflecting surface will be equal to the angle between reflected ray and the reflecting surface. Why? See guys, total is 90. This is I. So you can say this will be 90 minus I. And this I is equal to R. So this will be over here also 90 minus I. Forget about this. Don't get confused. Directly remember. Angle alpha is equal to angle beta. Angle I is equal to angle R. So this is the law of reflection that you can exactly see in this particular case. Okay. Then guys, let's move on to the deviation by a plane mirror. What does plane mirror actually mean? Guys. Let's suppose you are inside your room. You have got a mirror in front of you. That mirror in which you look at yourself. Okay. You make the hairstyle in the morning. That mirror is what we call the plane mirror. Nothing else. That mirror is called the plane mirror. Now guys, what I'm trying to say in this particular case is, listen to me very carefully. Let's suppose this is the plane mirror I'm taking over here. So I'll make it something like this is the reflecting surface. If you take a look at the back of the plane mirror, it is polished. It is polished from the back side, and from the upper side it is reflective. Now guys, If I say incident ray falls onto this plane mirror, it will be reflected something like this. Let's suppose I say there was no plane mirror present over here. What would happen? This incident ray would go something like this straight. But because of the plane mirror, we say this light ray got deviated from its original path. This is the deviation. Original path is this. It is deviated. This is the deviation. And if somebody asks you, can I write over here? I say, your incident ray got deviated from its original path. Your incident ray got deviated from its original path due to a plane mirror. And that's the reason we call it deviation by the plane mirror. And if somebody asks you, how much is this deviation? Directly remember, my dear friends, guys, how much is this total angle? 180. And how much is this angle? This angle, guys, this will be exactly, that is 2 theta. So this deviation I would want you guys to remember over here, that is 180 minus 2 theta. 180 minus 2 theta. Okay, 180 minus 2 theta. I hope this is crystalline clear. So this is the deviation in this particular case. So from now onwards, directly remember, guys, I am saying how much is the deviation created by the plane mirror? We say 180 minus 2 theta. This was the original path. It got deviated. How much it is? 180 minus 2 theta. Now, guys, directly, okay. See, when it comes to this session, if I say you have to remember this at this point, you will have to remember this. Don't ask me, sir, why, how, because now is not the time. We are supposed to cover 7 chapters in 12 hours. So for that, you will have to listen to whatever I say. Okay. Now, my dear friends, deviation by 2 plane mirrors. Look at this diagram over here. In this particular case, you have got 2 plane mirrors. This is M1, this is M2. This is M1, this is M2. The 2 plane mirrors are at an angle of theta. Directly remember. The 2 plane mirrors, okay, the 2 plane mirrors are at an angle of theta over here. Now, my dear friends, if I say there is a light ray in this particular case, this light ray falls onto the mirror M1. This light ray falls onto the mirror M1. What will happen in this particular case? Guys, what will happen in this particular case? We say this light ray will be reflected and it will fall onto the mirror M2. So here in this case, there is a light ray which is coming and it falls onto the mirror M1. So reflection will take place, it falls onto the mirror M2. Now, this light ray which is reflected for this one, it is a reflected ray for mirror M1, but it is incident for mirror M2. Again, reflection will take place something like this. Okay, again, reflection will take place something like this. This was the original ray. This is the final ray after the reflection. Okay, guys, this is original ray, this is final ray. Could you please tell me, sir, this will be the deviation? Okay, like in the previous case, angle between the original ray and the reflected ray, this was deviation. Similarly, in this case, angle between this incident ray, original ray, and the final ray, this is the deviation. If somebody asks you how much is the deviation over here, you will say 360 minus 2 theta, where theta is the angle between the 2 mirrors. Where theta is the angle between 2 mirrors. In the previous case, it was 180 minus theta when there was only one mirror. Here in this particular case, it will be 360 minus 2 theta. Now, guys, we have got a question over here. I would want you guys to focus on this particular question. See, what does the question actually say? Listen to me very carefully. This was the question which was asked in JEE Mains 2020. JEE Mains 2020. Now, guys, see, what does the question actually say? two plane mirrors are inclined to each other. This M1 and M2 are inclined to each other such that the ray of light is incident on the first mirror. Such that the ray of light is incident on the first mirror, M1, and parallel to the second mirror, M2. This ray of light is incident on mirror M1, but at the same time it is parallel to mirror M2. See, it is moving parallelly. It is moving parallelly. Okay, and is finally reflected from the second mirror. Guys, what will happen? This light ray will fall onto the mirror M1. It will be reflected. It will be reflected and it falls onto the mirror M2. When it is reflected and it is falling onto the mirror M2, again here it will be reflected. Second reflection. This is the first reflection on M1. This is the second reflection on M2. Okay. And then, guys, it says that and is finally reflected from the second mirror. Is finally reflected from the second mirror, parallel to the first mirror. See, this final ray is parallel to the first mirror. This final ray is parallel to the first mirror. The angle between the two mirrors will be, you are supposed to find the value of this theta. Guys, tell me one thing. Tell me one thing. We say here, in this particular case, if you take a look, I would want you guys to focus exactly over here. See, this is the incident ray. This is the reflected ray. Can I draw a normal over here? This is the normal. Yes. Now, can I say this is the angle of incidence? This is the angle of reflection. These will be equal. And my dear friends, see. We said this angle will be also equal to this angle. Why? Why? Because if you check over here, I have told you angle between incident ray and reflecting surface is also equal to angle between reflected ray and reflecting surface. Alpha is equal to beta, and call this as, let's suppose, theta. So similarly, you can say in this particular case, this angle is equal to this angle. Now, why do we call it theta? Because if this angle is given as theta, that is what we are supposed to calculate. This is theta, this is also theta, because this line and this line are parallel, and this is the similar line. So this is theta. If this is theta, this is theta. Now, if this is theta, this will be also theta. Okay, cool. Now, guys, take a look. If this angle is over here, theta, if this is theta, okay, can you say, sir, if this is theta, this line and this line are parallel, so this angle will be also theta? Yes. And this is the second reflection over here. Take a look. Draw a normal on the second reflection over here. Okay. Now, guys, something like this. This is the normal, something like this. Okay. Now, guys, in this particular case also, this is the incident ray, this is the reflected ray. Angle between the reflected ray and reflecting surface. Okay. And angle between the incident ray and reflecting surface. If this is theta, this will be also theta. Simple. This is theta, this is theta. If this is theta, this will be theta. Now, if this is theta, this will be also theta. If this is theta, this will be theta. Now, in this triangle, we can say from the triangle, what is the sum of all the angles over here? I can say from the triangle. Can I say what is the sum of angles? That will be 3 theta and it will be equals to 180 degree. So can I say theta in this particular case will be 60 degree? Is this crystalline clear? Please tell me in the chats. Please tell me in the chats if this is crystalline clear. Tell me, guys, is this crystalline clear? I would want you guys to let me know in the chats if this is crystalline clear. All the people out there. And my dear friends, smash the like button because liking the session is mandatory. Now, guys, come on to this one. Object and we say image. What does object and image mean? Let me make you understand over here. Guys, let's suppose I have got a mirror over here. This is the mirror that I'm taking. This is a plane mirror. Okay. This is the plane mirror inside your room. This is the plane mirror. Guys, understand very carefully. Let's suppose you are standing in front of the plane mirror. You are standing in front of the plane mirror, okay, over here. What happens? Sir, I would be able to see myself inside the plane mirror. So, what is that? This is what we call the image. Okay. So, this is what we call the image that you see inside the mirror. And this is what we call the object. This is what we call the object. So, object is standing in front of the mirror and its image is formed inside the mirror. And if this object is at certain distance, let's suppose D, we say image inside the mirror will be also formed at D. Image inside the mirror will be also formed at D. If you move close to the mirror, image will also move close to the mirror. Okay. Now, my dear friends, I would say, how does this actually happen? How does this actually happen? Let me show you over here. How does images actually form? How is image actually formed over here? See, guys, we say, let's suppose this is a plane mirror over here. This is the object. Always remember, if you want to create its image inside the mirror, we say incident rays will leave from the object. Directly remember, guys, incident rays will leave from the object and it falls onto the mirror. Incident rays will leave from the object and it falls onto the mirror. Okay? Okay. Now, my dear friends, understand this very carefully. Understand this very carefully. I'll make over here. Let's suppose I'm saying this is the plane mirror over here. This is the plane mirror over here that I'm creating. So what is this? This is the polished surface. So from the back side, it is polished with the red color or something like that. And guys, let's suppose you have got an object over here. This is the object. We say, sir, from the object, incident rays are leaving. Okay. From the object, always incident rays leave. Now, when it falls onto the mirror, when these fall onto the mirror, we say it will be reflected something like this. It will be reflected something like this. So these light rays, this is called the incident ray. This is IR. This is IR. This is also IR. And this will be the reflected ray, which is reflected from the surface. This is also the reflected ray, which is reflected from the surface. Now, guys, if I am saying that you extend these reflected rays, you extend these reflected rays, you extend this reflected ray. So the point where these reflected rays actually meet, image will be formed. This is how we define formation of image in ray optics. We say from the object, incident rays will leave, they will reflect it. These will be reflected from the surface. Now, if you extend these reflected rays, the point where they meet, that is what we call the image. So that's why we define object is, it is defined as the point of intersection of incident rays. It is defined as the point of intersection of incident rays. That point where incident rays intersect, that point where incident rays meet, that is what we call the object. And when we talk about the image, it is that point of intersection where reflected rays meet. Okay, it is the point of intersection of reflected rays in case of reflection. That point where reflected rays meet is called, we say image. Now, guys, we have a real image, virtual image, real object, virtual object. See, guys, in this particular case, we say incident rays are actually leaving from this. In reality, if you place the object over here, incident rays are leaving. So we call this object as real object. Now, guys, see. If we say in this particular case, I would want you guys to focus exactly over here. See, we say here this object is real. Incident ray will leave from this object and it will be reflected something like this. Incident rays will leave from this object, it will be reflected something like this. Now, if you extend these reflected rays, they appear to meet over here. They are not actually meeting. In reality, they are not actually meeting. Okay, so this is what we call the virtual image. Why? Because reflected rays appear to meet here. Reflected rays appear to meet. Similarly, if you take a look in this particular case, guys, if you take a look in this particular case, see, if incident rays are falling something like this, they are coming from infinity. If incident rays are falling something like this, they will be reflected. They will be reflected. Here, reflected rays are actually meeting. If reflected rays are actually meeting, image will be real. Two things are there. If incident rays are actually meeting, object is real. If incident rays appear to meet, object is virtual. Similarly, if reflected rays appear to meet, image is virtual. If reflected rays actually meet, image is real. Now come over here. See, in this particular case, this is the mirror. Incident rays are falling over here. Okay. Now in this particular case, my dear friends, can I say in this particular case, this one and this one, this is the incident ray, this is the incident ray. If you extend these incident rays, they appear to meet over here. So this is what we call the virtual object. And this is the real object. Real object means here incident rays actually meet, leave from this object or meet one and the same thing. But if the incident rays are something like this, okay, then if you extend the point where they meet, that is called the virtual object. Similarly, this is the virtual image because reflected rays appear to meet. This is the real image because reflected rays actually meet. Guys, is this concept crystalline clear? Please tell me in the chats. Is this crystalline clear? Please tell me in the chats. And I would want you guys to join my Telegram channel. That is very much important, okay? Because I put up everything in my Telegram channel, only notes, whatever it may be, okay? The last marathon notes I forgot to send, but today also I'll be sharing the notes of this marathon also and the notes of the last marathon also. So it is t.me/Yawar Manzoor, YAWARMANZOR. Search it on Google, you will land onto this channel and join it. And guys, tell me in the chats, is this crystalline clear? I would want you guys to let me know in the chats if this is crystalline clear to each and every single student. Tell me, guys. Is this crystalline clear? That's great. That's great. Now guys, image formation by plane mirror. That's what I already said. Let's take this example. Let's take a look at this example. You have an object over here. Now, my dear friends, we say in this particular case, incident rays will leave from the object. Let's suppose something like this. From the mirror, these rays will be reflected something like this. These two are reflected rays. These two are incident rays. Okay. Now, can I call this object over here as real or virtual? Let me know in the chats. Can I call this object as real or virtual? This is a real object. Why? Because incident rays are actually leaving or meeting at this point. Now, when the reflected rays are reflecting over here, if you extend these reflected rays, the point where these reflected rays actually meet, the point where these reflected rays appear to meet, this is called virtual image. Why? Because reflected rays appear to meet. So reflected rays appear to meet in this particular case over here. Okay. Now guys, let's take a look at this particular example, which I would want you guys to understand. See, the question is, find the minimum size of the plane mirror required. Find the minimum size of the plane mirror required to see the full image of an observer or the object. See guys, let's suppose you are taking a plane mirror over here. This is the plane mirror. Okay. And in front of the plane mirror, this is the object. This is the object. Okay. And its height is, let's suppose, h. Now we know its image will be created from the another side of the plane mirror. Yes. Now guys, in this particular case, we say one ray will leave from the bottom of, let's suppose there are a lot of rays which are leaving from the object. These are the incident rays. So the last ray will be at the bottom from the foot. This is the incident ray which is leaving from the foot of this object. Okay. Now, my dear friends, in this particular case, it falls onto the mirror and it will be reflected. It will be reflected. Okay. Now, in this particular case, I would want you guys to understand one thing. See, so we say when this light ray is reflected and it falls into the eyes of this person, eyes of this observer. Here, observer is also this, object is also this. Like. Observer is the one who is observing the image. I have the mirror in front of me. I'm standing in front of the mirror. Right now, I am looking at the image of myself. So I am the observer, I am the object. Now, if you have, let's suppose something like this. If you have a mirror, guys, see. If you have a mirror, you have a person over here, okay? Okay, and you have an object. You have an, let's suppose, a box. This box is, we can consider this box as an object over here. This will be observer. And its image will be formed over here. Sir, what about this? Its image also? Yes. Ignore the image of this one. If you are focusing on this object only, then consider this as the object. And who is focusing? The one who is looking at the image, that is what we call the observer. Okay, now if you have only person over here, right now this is the observer and this is the object. Keep that thing in your mind. Now guys, what happens? How image is formed over here? Incident ray will leave from this object, from the foot, and it enters the eyes of the observer. Another light ray will leave from the top. Another light ray will leave from the top. It enters the, after reflection, it enters the eyes of the observer. Okay. Now guys, if light rays are entering the eyes of the observer, then only observer is able to see its image. Now in this particular case, you guys can see light ray is coming from this object, falling onto the mirror, and it is reflecting back. Then here it is reflecting back. You guys can clearly see over here, all the light rays are falling onto the mirror between this point and this point. All the light rays, like if you take this light ray, if you take this light ray, if you take this light ray, all the light rays fall within this portion of the mirror. So what we are supposed to see is find the minimum size of the plane mirror. What is the minimum size of the plane mirror required so that we can see the full image? Only this much plane mirror is required. Sir, what about this? You can remove this. Still, you would be able to see the full image. And how much is this distance? This x is equal to h by 2. Okay. What is h? H is the height of this object over here. X is equal to h by 2. Okay. Like you have the question on this one. A man of 180 centimeter height is in front of the plane mirror. You have got a plane mirror over here. Okay. In front of the plane mirror, there is a man standing. Okay. And its height is given as 180 centimeters. Okay. His eyes are at height of 170 centimeters. Guys, from my eyes till the bottom, height is 170 centimeters. My complete height from the top till bottom, my height is 180 centimeters from the floor. Then the minimum length of the plane mirror required for him to see the full image. Guys, we say how much plane mirror is required to see the full image? X is equal to h divided by 2, where h is the height of the observer. So that is 180 divided by 2. That is 90 centimeters. So only 90 centimeter mirror is required to see the full image of the observer. Now I hope you got the feel of this particular question. Next you have this one. Okay, look guys, in this particular case, if a man wants to see the complete image of his, if a child wants to see the complete image of his father. Now see. In this case, this is the plane mirror over here. In front of the plane mirror, you have got child. Okay. You have got its father. Father's height is more than the height of the child. Okay. Question says, if the child wants to see the complete image of his father. Child wants to see the image of his father. So can I say in this particular case, this will be considered as observer, this will be the object. Why? Because child is seeing the image and this is the object. Yes. Now guys, in this particular case, I want you to understand, sir, what happens? One ray will leave from the top of the object and it falls into the eyes of the observer. Sir, why will it fall into the eyes of the observer? If it doesn't fall, the observer won't be able to see. It has to fall into the eyes of the observer. So I say in this particular case, one ray will leave from the top of the object and it falls into the eyes of the observer. Another light ray will leave from the bottom of the observer and it falls into the, from the object and it falls into the eyes of the observer. Now guys, can I say all the light rays are falling at between this part and this part? Yes, between this portion. How much amount of mirror is required? What is the minimum length required? This length is equal to D1H2, D1 plus D2. Now guys, what is D1? D1 is the distance of this child from the mirror. D2 is the distance of this father or the object from the mirror. H1 is the height of child, H2 is the height of the father. So this will be the length of the mirror required. Only this portion of the mirror is required to see the full image, and this will be the length. And how do we exactly calculate this similarity of the triangles? We don't have to do that mathematics. That will take a long time. So directly you will be remembering this. Now guys, if the father wants to see his son's image, if this father wants to see his son's image, could you please tell me in this case, which one is observer and which one is object? Father wants to see son's image. So this is observer and this is object. As simple as that. Now, we know that light ray will leave from the object. We know that light ray will leave from the object. It falls into the eyes of the observer. Another light ray from the top of the object falls into the eyes of the observer. Now, can I say here, this part of the mirror is required to see the full image? X. This X will be D2H1, D1 plus D2. This is D1, this is D2. This is H1, this is H2. I hope this is crystal and clear, and this one. Okay. The one who is observing the image, he will be the observer. Okay. And another one is object. Guys, give me the signal in the chats. I would want you guys to tell me quickly, as soon as possible. All the people out there, let me know in the chats. Quickly tell me in the chats, guys. Guys, if you are not like the session, and I would want you guys to smash the like button quickly, as soon as possible, Okay. Now guys, take a look over here. Relation between velocity of an object and the image. Guys, simply. Let's suppose this is the plane mirror over here. In front of the plane mirror, you have the object. If I move towards the mirror, you will find that image is also moving towards the image is also moving. As of now, don't say towards the mirror, away from the mirror, that we'll see. If you are standing in front of the mirror, you are the object. If you start moving, if you are at rest, image will be at rest. If you start moving, image will start moving. Let's suppose velocity of the object, I'm saying this is VO. Velocity of the object, let's suppose I'm saying this is VO. This is the velocity of the object. What will be the velocity of the image? And right now, sir, is the mirror at rest or mirror is moving? I'm saying in this particular case, velocity of the mirror is Vm. Sir, you will not keep the mirror at rest. Wait for some time. Right now, I'm assuming mirror is also moving. I'm moving along with me. Mirror is also moving. In that case, what will be the velocity of the image? Okay. And guys, one more thing. Object is moving perpendicular to the plane of the mirror. This is the mirror. Object is moving perpendicular to this. This will be parallel. This will be perpendicular. Plane. This is plane perpendicular to the plane. So I say in this particular case, this is the velocity of the image. 2 times Vm minus V naught. Okay. This is the velocity of image. Okay, guys, if you have an object moving with a velocity V naught or VO, mirror is also moving with a velocity Vm. So what will be the velocity of image? Velocity of image will be 2 times Vm minus VO. Sir, in 99% of our cases, I'll just write over here. In 99% cases, we consider mirror at rest. That means velocity of mirror we consider as 0. So we are saying mirror is stationary, it is not moving. In that particular case, what will be the velocity of the image? This is the general formula, guys. And velocity of image in that case will be 2 times Vm. Vm is 0 minus, I can say that is velocity of object. So I will be writing over here velocity of image will be minus velocity of object. As simple as that. If you have a mirror, you are moving towards the mirror, you will feel like image inside the mirror is coming towards you. Always remember, we take velocity as positive if the object is moving towards the right. If the object is moving in the right direction, we take its velocity positive. And we say if the object is moving towards left, we consider its velocity as negative. Towards right, it is positive. Towards left, it is negative. Similarly, if you are moving towards the mirror right, so your velocity is positive. And if object is moving, okay, velocity of image, velocity of object is positive, velocity of image will be negative. Why? Because it is opposite to you. Next you have case 2. Case 2 in this case is object and mirror are moving parallel to the mirror. Object and mirror are moving parallel. Object and mirror are moving parallel. Okay. Object and mirror are moving parallel. Okay. See. This is the mirror over here. And this is the object. This object is moving parallel to the plane of the mirror. It is that case. This object is moving parallel to the plane of the mirror. Now, guys, in this case, whatever is the velocity of object, same will be the velocity of image. Here, velocity of object is equal to velocity of image. Velocity of image is equal to velocity of object if they are moving parallelly. But if it is moving perpendicularly, in that case, this will be the velocity of image. And if mirror is at rest, this will be the scenario. I hope this is crystal clear. Let's take a look at this question. See, guys, the question says a man runs towards a stationary plane mirror. I see. A man runs towards a stationary plane mirror. So this is a plane mirror and velocity of the mirror in this particular case is 0. Why? Because it says stationary. When the mirror is at rest, in that particular case, what is the velocity of image? Minus times velocity of object. A man runs towards a stationary plane mirror with a velocity of 15 meters per second. Okay. So in this particular case, velocity of object is 15 meters per second. Can you tell me what will be the velocity of the image? Velocity of the image will be minus 15 meters per second. Okay. Then it says the magnitude of velocity of the man relative to the image. Guys, see. We are supposed to find velocity of object with respect to image. We are supposed to find the velocity of the object with respect to the image. There is a concept of relative velocity. What does that say? Guys. Relative velocity concept says that if there is an object which is moving with a velocity a, directly remember it. If there is an object which is moving with a velocity b, okay, this is VA, this is VB. Now, if I say, what is the velocity of A with respect to B? Velocity of A with respect to B. So you will say that is VA minus B. Like if this is moving with 10, this is moving with 5. So 10 minus 5, it is 5. Similarly, velocity of B with respect to A is VB minus VA. Simply. Here we have to find velocity of object with respect to the image. That is VOI. That will be velocity of object minus velocity of image. This is how you are supposed to solve the question. So I say in this particular case, velocity of object with respect to the image. Okay. Velocity of man with respect to the image. So you'll be saying velocity of object is how much? That is 15. Minus velocity of image is how much? That is minus 15. So minus and minus is plus. So it will be plus 30 meter per second. So it is simple. If you have two cars which are moving in the opposite direction, what will be the velocity of these two cars with respect to each other? So double. If this is moving at 10, this is moving in 10, 10 plus 10 is 20. It gets doubled. Okay. So when they cross each other, that's why velocity of object with respect to the image is 30. Next, could you please tell me the answer of this one? An object is moving towards a stationary plane mirror. You have got a stationary plane mirror with a speed of 2 meters per second in left direction. Okay. This is the stationary plane mirror. In this particular case, object is moving in the left direction. This is the object. Object is moving in the left direction. Okay. So velocity of object is 2 meters per second towards left. And I will not write it 2 meters per second. I'll say minus 2. Minus 2 meters per second. And my dear friends, mirror is stationary. So velocity of mirror is 0. Now tell me, what will be the velocity of image? Velocity of image will be minus times velocity of object. Because we know when mirror is at rest, velocity of image will be minus times velocity of object. And in that case, we say velocity of image will be simply minus times of this minus 2. So that will be plus 2 meters per second. This is velocity of image. Then it says the velocity of image with respect to the object is, we are supposed to find velocity of image with respect to the object. How will we find that? Velocity of image minus velocity of object. And how do we find that? Velocity of image is how much? 2 minus velocity of object is how much? Minus 2. So it will be 4 meters per second. Answer is 4 meters per second. I hope this is crystal and clear. Then you have got number of images formed by two plane mirrors. Guys, see. Let's suppose I'm saying in this particular case, you have got two plane mirrors. This is M1. You have got this M2. You are having two plane mirrors exactly over here, M1 and M2. Okay. And these two plane mirrors are at an angle of theta. Guys, understand this quickly. Okay, they are placed at an angle of theta, not parallelly, at an angle of theta. Let's suppose you are placing an object over here at an angle of alpha. Okay. Like, normally what do you say? You say, I have got a mirror over here. This is the object. This is at distance D. Image will be formed at distance D. Yes, same is the case over here. Here, I'm saying this is angular displacement. Over there, it was linear displacement. So, angularly, this object is placed at an angle of alpha. Alpha can be 30 degrees, 40 degrees, something like that. Don't you think that, sir, its image will be formed over here? I1. Image of this object will be formed over here. If the object is placed at alpha, image will be also placed at an alpha angle. 100%, sir. Now. See. Now, this image will behave like an object for M2. Guys, I am writing this over here. I'll write I1 behaves like an object for M2, for this mirror M2. Now tell me, if this behaves like an object for this mirror M2, see, this is how it happens. So in that particular case, this I1 is at what distance from this mirror M2? Sir, this is theta, this is alpha. So this is theta plus alpha. Now, its image will be at theta plus alpha. Why? Because this I1 is placed at an angle of theta plus alpha. So its image, sir, it itself is an image. This is the image for M1. But for M2, it is object. It behaves like an object. So its image will be at this point, and that is at theta plus alpha. That is at theta plus alpha. And I'll write this. And its image I2 is at theta plus alpha. Theta plus alpha. Okay. Now again, this I2 will behave like an object for M1. I'll mention this also. This I2 behaves like an object for M1. It behaves like an object for M1. So its image will be at what distance? Guys. Its image will be at, guys, this angle is theta. This is alpha plus theta. So alpha plus theta, that is alpha plus 2 theta. So its image will be at alpha plus 2 theta, that is I3. I'll write over here. So its image is at alpha plus 2 theta. Its image I3. Similarly, this will again behave like an object for this mirror, for this M2 mirror. And it will create its image, and it keeps on going. Now, this is what I'm giving you the idea how image formation takes place in this angular story. Now, in nutshell, if somebody asks you, the two mirrors are at an angle of theta, how many number of images are formed over there? That is the main question. The main question is, see, to find the number of images formed, guys, first you find the value of M. Sir, is M the number of images? No. M, how do you find M? M is just a number. How do you find M? M is 360 divided by theta. Theta is the angle. If I say angle between the two mirrors is 30, so 360 by 30, where theta is the angle between the two mirrors. Okay, I'll show you the question also. Now, guys, if you get the value of M as integer, if M is the integer, understand this very carefully. Then you have to check if M is even. Number of images will be M minus 1. I'll show you the questions also. Please wait for some time. And if M is odd, then you have to check if object is present at angle bisector, number of images will be M minus 1. If object is not present at the angle bisector, number of images will be M. Sir, please show a question. I'll show the question that will clear all the confusions out. First question is this. Two mirrors are inclined at an angle of 30 degrees. So angle between the two mirrors is 30 degrees. An object is placed at making 10 degrees with M1. Okay. You have got, this is 30 degrees. Object is placed over here. This object is making 10 degrees. Find the total number of images. Guys, in order to find the total number of images, we first find M. M is 360 divided by theta. So that is 360 divided by 30. So 3 12s are 12. So M is coming out to be 12. 12 is an integer. Now see, if M is integer, then you have to check. If M is even, number of images will be M minus 1. Now check. This is even. So can I say number of images is equal to M minus 1, that is 12 minus 1, that is 11. So number of images will be 11. Now take a look at this question. You have got over here in this particular case, two mirrors at an angle of theta. First one, they are saying that if theta is equal to 60 degrees, find the number of images. Guys, first, theta is equal to 60 degrees. Find the value of m. In order to find the number of images, you first find m. So m will be equals to 360 divided by theta, that is 6066. So in this case, this is even. I can say number of images. Number of images will be 6 minus 1, that is 5. Number of images will be 5. As simple as that. Now, second one, it is saying that if theta is equal to 72, theta is equal to 72 degrees, and object is present at 40 degree from M1. This is very important. Guys, see, I can say value of M in this case is 360 divided by 72. It comes out to be 5, which is odd. Now, if the value of M comes out to be odd, you have to check. Object is at angle bisector, number of images will be m minus 1. Object is not at angle bisector. Angle bisector means, let's suppose this angle is 30 degree. Its angle bisector will be exactly which is bisecting the angle in 15 degrees and 15 degrees. So angle bisector in this case is 15 degrees. So similarly here, if object is present at 40 degrees, what is the half of 72? 36, but it is 40. Object is not at angle bisector. Object is not at angle bisector. Okay. So number of images will be, when object is not at angle bisector, number of images is m. Number of images is m. So what is the value of m? That is 5. As simple as that. And then in the second portion, third one, theta is equal to 72. Object is at angle bisector. So once again, if theta is equal to 72, so here m is equal to 360 by 72, that is 5 odd, and object at angle bisector. So if object is at angle bisector in this particular case, because half of 72 is 36, so then number of images will be 5 minus 1, that is 4. And last one, theta is equal to 80 degrees. Guys, in this particular case, m will come out to be 360 divided by 80, that is 4.5. Okay. Now, my dear friends, if you get 4.5, in this case, directly you write 4. Number of images will be 4. Is that clear? Let me know in the chats, everybody out there. Is this clear? Is this clear? Next we have spherical mirrors. Guys, take a look. What does spherical mirrors actually mean? See guys, let's suppose you have a spherical ball over here. You take a sphere. Okay, this is a sphere. You cut this portion of the sphere, okay? Cut it over here. It will come out to be something like this. This bowl-shaped structure will come out. Okay? Now guys, this inner side is what we call the concave side. And this outer side of the bowl is what we call the convex side. Always remember this. Okay? Now. If you polish, this is polish, coloring, polishing. This is polish. If you polish it from the outer side, now a reflection will take place. Like you have the mirror over here, plane mirror. We say polished from the outer side, reflection takes place on this side. If you polish from this side, reflection takes place from the inner side. So reflection takes place from the concave side. So we call this as concave mirror. How do you define it? If the reflection takes place from concave side, it is a concave mirror. Now, If you polish this from the inner side, reflection takes place from the outer side, curved side. We say it is called the convex mirror. It depends from which side reflection is taking place. If reflection takes place from concave side, it's a concave mirror. If reflection takes place from convex side, it is, sir, why can't the reflection take place? Because it is polished from this side. Okay. Now, let's suppose I am making this curved mirror over here. This is a concave mirror. I am taking concave mirror because this is, your reflection is taking place from the inner side, concave side. This is the curved mirror over here, convex mirror, sorry, concave mirror. Guys, remember, if you draw a line over here, this line, which is cutting this into two parts, which is cutting the mirror in two parts. This line is what we call the principal axis. Always remember, this line is called the principal axis. Okay, which passes exactly through the center. Now guys, listen to me very carefully. If you cover this, assume that this is a complete sphere. So for this complete sphere, don't you think this will be the center? Yes. So this is called the center of curvature. So from now onwards, if I say this is a mirror, this is the center of curvature, what does it mean? It means that's the center of the whole sphere, if we assume it a whole sphere. Okay. Now from center to this sphere, this is called the radius of curvature. This is called radius of curvature. Okay. Okay. Now, my dear friends, listen to me very carefully. Listen to me very carefully. Sir, this center of curvature and this point at which it is cutting this sphere, this principal axis is cutting the this mirror over here. This is called pole. Between center of curvature and pole at the center, there is focus. And this focal length is always equal to r/2, half of the center of curvature. Because from here to here, it is radius of curvature. So radius of curvature divided by 2 is called the focal length. Okay. And one more thing. If you, let's suppose, send a light ray, this is the light ray. This light ray is parallel to principal axis. And then it is passing through the focus. After reflection, it is passing through the focus. Or light ray is passing through the focus, then it becomes parallel to principal axis. This is called para-axial ray. I told you 5 things. Remember, directly I'm saying. If you take a concave mirror, this line is what we call the principal axis. This point at the center is called center of curvature. From center of curvature till this mirror, this is called radius of curvature. This point is called the pole. Between pole and center of curvature, there is focus. And this focal length is equal to half of the radius of curvature. And if the light ray is parallel to principal axis, after reflection, it passes through focus. It is called a para-axial ray. I hope these points are clear. Next, image formation by take a look, guys. Take a look, guys. Image formation. Let's suppose, guys, like you studied image formation in case of the plane mirror. You were saying, sir, object is here, its image will be here. Directly, just one case. But in case of spherical mirrors, convex or concave mirrors, there are different kinds of images which are formed. Yes, we have to study that. See, when it comes to the image formation over here, we say in case of concave mirrors, guys, the first case that you need to understand, if the object is beyond 2f, guys, what is 2f? 2f is center of curvature. This is a convex concave mirror. This is the principal axis. Okay. This is center of curvature, or you say 2f also. This is focus. This is pole. Okay. Guys, understand very carefully. Let's suppose this is the object over here. This is the object over here. Incident rays will leave from the object, okay, and it will pass through the focus because this is the parallel to principal axis, and it passes through the focus. Another light ray will leave from it and it will be reflected something like this. Now guys, the point where incident rays meet, that is object. This is object. AB is object. Now, after reflection, this is ray. After reflection, this is ray. The point where reflected rays meet, that is what we call the image. So this will be the image. Okay, okay. Now guys, see, please look at this. I'll be showing you one case. You will be able to understand everything. If object is placed beyond 2f, don't you think that image is formed between f and 2f? Between f and 2f? Yes, image is formed between f and 2f. It will be real. Real means where light rays, where reflected rays are actually meeting. Reflected rays are actually meeting. It will be real. It will be inverted. Guys, this is erect. This is inverted. Upside down, it will be inverted. It will be diminished. Diminished means smaller than the object. Object is bigger. It is smaller than the object. So that is how we define image formation in case of spherical mirrors. This is the concave mirror. Another one. If object is between f and 2f. Guys, now object, previously it was beyond 2f. Now if it is between f and 2f, one light ray will leave, it will be reflected something like this. Another light ray will leave, it will be reflected something like this. This is the image. Don't you think that image in this particular case is real? Because these two light rays are actually meeting. Image will be inverted. Okay, and image is beyond 2f. Image is real. Image is inverted. Image is magnified. Magnified means bigger. Bigger than the object. This is image, this is object. Okay, so when you place the object between f and 2f, next case, if the object is between focus and pole. Now guys, this is focus, this is pole. First case beyond 2f, second case between f and 2f, third case between focus and pole. Light ray will leave something like this, it will be reflected. Another light ray will leave something like this and it passes through the focus. Now these two are divergent rays, these will not meet. But if you extend them, they will meet over here. Now this AB is the image where reflected rays appear to meet. Now it is, the image formed over here is virtual. Yes. The image formed is erect. Okay, this is erect. This is not upside down. And it is magnified. It is magnified. Okay. Magnified means bigger than the object. And this image can be formed between 0 and infinity anywhere. Anywhere. Next, image formation in case of convex mirrors. In case of convex mirrors, you have two cases only. This is the convex mirror. Guys, first, you place, why only two cases? Because in this particular case, focus will be from this side, okay, from the polished side. Center of curvature will be from polished side. Everything is from polished side. So here we define only two cases. If the object is placed near to the mirror, if you place the object near to the mirror, light ray will be something like this. It will be reflected. Another light ray, it will be reflected. Okay. Now, if you extend these reflected rays, if you extend this reflected ray, the point where they meet, okay, here, the point where they meet, image will be formed. And in this case, we say, when object is placed near to the mirror, image formed will be virtual, erect, diminished. Okay. Erect means it is not upside down. Diminished means smaller than the object. Between pole and focus. Between focus and pole. Guys, is this crystalline clear to each and every single student? Is this crystalline clear to each and every single student? One of my friends is in the chats. PR Wasim Raja sir. Extremely great teacher of physics. Is this crystalline clear? That's great. That's great. And the next case that we define over here is if the object is placed very far, means at infinity. Object is placed at infinity. That's why the rays coming are parallel. These are the parallel rays. Okay. Now, guys, this is one ray. Okay. This is a light ray, which is through the pole, kind of, I can say. It appears to pass through the pole. Now, guys, it will be reflected something like this. Okay. If you extend it, it appears to pass through focus. It appears to pass through focus. Okay. Because this light ray looks like it is coming from the focus only. And another light ray, which is through the center of curvature, it will be reflected back through this line only. It appears to pass through center of curvature. Now, guys, in this particular case, if you extend this reflected ray, the point where they meet, image is formed. And in this case, we say, in case of convex mirror, if object is placed at very far, means at infinity, image will be formed virtual. You guys see, virtual image. Why? Because reflected rays appear to meet over here. Okay. And my dear friends, in this particular case, it will be erect. And it will be small, very small, diminished over here. Okay. And one more thing, we say it is formed at focus. Okay. So these are the two cases that we define in case of we say image formation, in case of image formation of convex mirror. Now, guys, let's take a look at the mirror formula. Okay. Let's take a look at the mirror formula. So I have told you the image formation in case of convex mirrors, in case of concave mirrors. Okay. Now we need to talk about the mirror formula. Understand this very carefully. Guys, see. This mirror formula, we say it is 1 by V plus 1 by U is equal to 1 by F. Sir, what is this? It is simply the relation between position of the object, position of the image, and focal length. Let's suppose, my dear friends, I am saying I have a mirror over here. Okay. Let's suppose I am taking a concave mirror in this particular case. This is a concave mirror. And I am placing the object over here at certain distance. So let's suppose U is equal to 10 centimeters. I am giving you the focal length in this particular case. Focal length is something. I am asking you, tell me, where will be the image formed? V is the position of the image. Sir, you will be using this particular formula. So this formula helps us to find the position of the image, position of the object, or focal length. So that's why we say it's the relation between U, V, and F. But here you need to take care of the sign conventions. Okay. Now see, how we are supposed to take the sign conventions. See guys. Take that direction as positive in which incident rays are moving along the principal axis. Like, let's suppose, my dear friends, you have got a mirror over here. This is a concave mirror. Okay. Now, guys, in this particular case, I'm saying the object is over here. This is the object. In this particular case. Okay. Now, guys, we always say incident rays will leave from the object. This is the direction of incident rays. So, take the direction of incident rays as positive. So, we will be taking this side as positive. And opposite to it, we will be taking it negative. As simple as that. So, here, if somebody says object is placed at U is equal to 10 centimeters, position of the object is 10 centimeters, will you take it positive or negative? I am supposed to take U as negative in this particular case. Why? It is from the negative side. Okay. Let's suppose it is something like this. It is something like this. It is a convex mirror. Okay. And in this particular case, I'm saying this is the object over here. This is the object. We know, sir, if this is the object in this particular case, this will be the direction of incident rays. So here, this will be positive, this will be positive side, and this will be the negative side. Now, guys, in this case also, U will be considered as negative. But if I say focal length, focus of this mirror will be from this side. So focal length in this case will be positive. And if somebody asks you, what is the focal length of this? So that will be from the negative side. So F is negative. F is negative. You need to take care of the sign conventions. Okay. Is this crystalline clear? Tell me in the chats, is this crystalline clear? Everyone? Like, find the location of image. In this particular question, they are asking us to find the location of image. Tell me, guys, is this crystalline clear? Guys, tell me. Is this crystalline clear to each and every single student? I would want you guys to tell me in the chats. Whosoever is watching, let me know in the chats. Tell me, how much is it? Yes, 15, minus 15. Guys, see, in this particular case, you have got an object over here, and U in this particular case is given as minus 30. Why? Because this is the object. This will be the direction of incident rays. This will be positive side, and this will be negative side. U is minus 30. Now, my dear friends, in this particular case, focus of this is also from this side. This is a concave mirror. So focal length will be, sir, minus 10 centimeter. Okay. Now, we know the formula, that is mirror formula that we have recently studied. What is that? 1 by V plus 1 by U is equal to 1 by F. So I'll be writing over here 1 by V plus 1 by U is equal to 1 by F. Do the cross multiply. So we say U plus V divided by U. Okay, take it over there. We are supposed to find 1 by V minus 1 by U. We are supposed to find V. So 1 by V will be equals to 1 by F minus 1 by U. Now do the cross multiply. 1 by V is equal to U minus F upon U into F. Now do the reciprocal in this particular case. So I can say V is equal to U into F upon U minus F. Now V will be equals to, what is the value of U in this particular case? Minus 30, along with the sign conventions. Focal length in this particular case is minus 10 upon U minus F. U in this particular case is minus 30. Then minus U minus into minus is plus, and this will be 10. Okay. Now tell me, guys, this is 300. Okay. And this will be over here. This is 30 minus 10. That will be equal to 20. So this will come out to be exactly that. Okay. Is this clear? Is this clear? Let's suppose you have got this question. Find the location of the image in this particular case. Guys. In this particular case, this is the object. Can I say this is the direction of incident rays? Yes. So this will be the positive side and this will be the negative side. In this particular case, U is coming out to be minus 20 centimeters. Okay. And focal length in this case is coming out to be minus 20. Focal length is positive. F is equal to plus 20 centimeters. Why? Because focus of this is from a right side. Now, in this particular case, I would want you guys to understand one thing. Just a second, guys. Now, guys, in this particular case, I can say when it comes to directly, you'll be remembering this. U into F upon U minus F. So we'll be saying V is equal to U into F upon U minus F. So V will be exactly equal to, what is the value of U? That is minus 20. Minus 20. F in this case is plus 20 upon U. U in this case is minus 20 minus, this will be also 20. So this is minus 400 divided by minus 40, this and this, this and this. So it will come out to be 10 centimeter. Plus 10 centimeter. Okay. Is this clear? Okay. Yes, it will be the virtual image. Why? Because if you check in this particular case, reflected rays will be reflected something like this. Then if you extend them, those, then we can say this, that's why we are getting plus 10. Plus 10 will be from this side because this is minus side, this is positive side. So it will be the virtual image. Guys, this is the mirror, this is the object, light rays will be reflected something like. Then if you extend them, image will be formed over here. So extending means appear to meet. So means this is the virtual image. And in this particular case, it is real. Okay, because it is coming out to be minus 15. Object is at minus 30. Image will be formed somewhere around over here. So incident ray will go and it will come back. Reflected rays are actually meeting. So this is real and that one is virtual. Then you have over here, that is what we call the magnification. What does magnification actually mean? It is defined as the height of the image and the height upon height of the object. It is defined as height of the image upon height of the object. Like this magnification gives you an idea how bigger the image is or how smaller the image is, how magnified the image is. Height of the image divided by height of object. Like we say, image is magnified, image is enlarged, image is bigger, image is diminished, image is smaller. That is what we call the magnification. And my dear friends, in this particular case, M is height of image divided by height of object over here. Okay. Now in this case, we say another formula for the magnification in this particular case will be minus V divided by U. Minus V divided by U. This is in terms of height of image divided by height of object. This is in terms of, I would say, in terms of V and U. Position of the object and position of the image divided by position of the object. And if somebody says, is there another formula for the magnification? You say that is F upon F minus U. This is focal length and this will be focal length and this is position of the object. And then in terms of F and V, this will be focal length minus V, position of the object, image, V is position of the image divided by focal length. In terms of F and V, in terms of F and U, and this is in terms of height of image, height of object, this is in terms of U and V, Now guys, let's suppose you are given a question over here on the screen, this one. I would want you guys to tell me the answer of this particular question quickly in the chats. Everyone means everyone. Tell me, guys. Find the position of the image. Guys, the very first thing in this particular case is write the sign conventions. This will be the direction of incident ray. So this side we consider as positive and this side we consider as negative. This is positive and this is negative. Okay. Now guys, if this is positive and this is negative, I can say in this particular case, can I say, sir, U comes out to be minus 15 centimeters? Yes. And focus of this will be from this side only. And guys, radius of curvature is 20. Focal length will be half of the radius of curvature. So I would say here focus is R by 2 and that is 20 by 2. That will be minus 10 centimeters. Now tell me, what is the position of the image in this particular case? Yes, minus 30. That is the position of the image in this particular case. How do we find the position of image? Sir, simply V is equal to U into F upon U minus F. So V is equal to U. U in this particular case is given as minus 15. F in this particular case is given as minus 10. Divided by U minus F, that is minus 15. Then minus into minus is plus 10 over here. Okay. So V will come out to be minus 30. Is that clear? So you got the V as minus 30 centimeters. Now you are supposed to find height of the image and magnification. Let's first find the magnification as. Guys, tell me, when it comes to the magnification, you got the value of V, you know the value of U, you can use any formula in this particular case. Guys, see, I can write over here, when it comes to the magnification, that is F upon F minus U. So you will be writing over here as magnification M is equal to F upon F minus U. Now tell me, in this particular case, M will be equals to, what is the value of F over here? That is minus 10 upon, what is the value of F? That is minus 10, and then minus into minus is plus, and U in this particular case is 15. U in this particular case it is minus 15, minus into minus is plus. So okay, so this will come out to be minus 10 divided by 5. So this will come out to be magnification is minus 2. Okay, minus 2. So if magnification is minus 2, my dear friends, in this particular case, I would want you guys to focus. If magnification is minus 2, now you are supposed to find height of the image. So how will you find the height of the image? Guys, recently I told you, magnification is height of image divided by height of object. Height of image divided by height of object. So you guys can write over here, magnification is equal to height of image divided by height of object. So from this, magnification will come out to be, so from this height of image will come out to be, that is magnification into height of object. What is magnification? Minus 2. Height of object is minus 1 mm. So this will come out to be minus 2 mm. This will come out to be minus 2 mm. Next, guys, there is one more thing over here, that is longitudinal magnification. You directly remember this. Longitudinal magnification is, see. Object is placed parallelly on the principal axis. Like here, object is not placed perpendicularly on the principal axis. Okay, you have got a mirror in this particular case, and this is the object which is placed parallel to principal axis. AB is the object. Okay, and its image is, let's suppose, formed over here. Okay, its image is, let's suppose, formed exactly at this point. Now, my dear friends, in this particular case, if you want to find this longitudinal magnification, directly remember this. See. Sir, this is the object which is placed something like this. So from here to here, this distance is UB. Okay, from this point to this pole, this is UB. Now from here to here, this distance is UA. Similarly, this is the image. From this point till pole, this is VA. From this point till pole, this is VB. If somebody asks you, what is the value of longitudinal magnification, means object is placed something like this parallel to the principal axis. In that case, longitudinal magnification will be VB minus VA. Okay, VB minus VA upon UB minus UA, UB minus UA. Now guys, this is when size of object is finite, bigger. If the, I would say in this particular cases, size of object is very small. If the size of object is very small, then can I say this length, okay, this size of object, we can say this is du. Previously, what is this? UB minus UA. UB minus UA means this length of the object, size of the object. This is bigger. This VB minus VA, this is bigger. But right now, this is smaller. So small size means du. Small size of the image means dV. Here magnification, you guys can say dV divided by du. Longitudinal magnification. And one more important formula I want you guys to remember over here. That is, longitudinal magnification is minus m square transversal. Longitudinal magnification is m square transversal magnification, square of the transversal magnification. Like this one, previous magnification that we studied, this one. What is this? This is the transversal magnification. So if transversal magnification is given, you are supposed to find longitudinal magnification. Just put up the square and put negative sign in front. Like you have the question over here. The question is something like this. The question is something like this. See, an object of 0.1 mm at 15 centimeters from the concave mirror. Okay. Focus is this. Let's suppose you have the concave mirror over here. This is the concave mirror. Okay. An object is placed over here at 15 centimeters. U is equal to minus 15. Okay. Because this is the direction of, this will be the positive side and this will be negative side. Focal length in this case is given as minus 10 centimeter. Focal length in this case is minus 10. Find the longitudinal magnification. Guys, we can find the transversal magnification. I can say in this particular case, transversal magnification is f upon f minus u. Because f is given, u is given. From that you can find the longitudinal magnification. Now guys, tell me, what is the value of f? That is minus 10 upon. This is minus 10. Minus into minus is plus. U is given as 15 over here. Okay. Now this is minus 10. Plus 10 minus 15, that will be 2. Sorry, 5. That will be 5 plus 5. Now 5 ones are 5, 2s are 10. So this will be minus 2. Now guys, if you want to find the transversal magnification, how do you find the transversal magnification? Longitudinal. Sir, m longitudinal is minus m square transversal. So m longitudinal is equal to minus m transversal is how much? That is minus 2 whole square. So that will be minus 4. Now take a look at this. Take a look at this. Take a look at this. Velocity of the image. When the object and mirror are moving along the principal axis, when the object and mirror are moving along the principal axis. Guys, see, previously we discussed the velocity of image in case of the plane mirrors. Okay. Velocity of image in case of the plane mirrors. Okay. Now, my dear friends, in this particular case, see. Let's suppose, see, guys, there are some topics which are not the topics, some points which are extremely least important. If you think I'm not touching those small points, okay? So I would suggest you to go on to my detailed one shot of ray optics. Over there you will find it. Okay. Now, my dear friends, okay. In this particular case, I would want you guys to focus. Let's suppose you have got a plane mirror over here. In front of the plane mirror, object is moving with some velocity. And I asked you to tell me what is the velocity of the image. What is the velocity of the image? So previously we discussed that if the object is moving perpendicular to the mirror, if the object is moving parallel to the mirror, that is easy. That is easy. Okay. Now, my dear friends, if I am saying when the object and mirror are moving along the principal axis, but right now you have got the spherical mirror. Right now you have got this. Previously we were discussing velocity of image in case of plane mirror. right now we have the spherical mirror, concave mirror. Okay. Now guys, this is the object in front of the concave mirror and its velocity is VO. Its velocity is VO. Okay. And velocity of the mirror is Vm. Velocity of the mirror is Vm. If somebody asks you, and right now, when object and mirror are moving parallel to principal axis, see, this is principal axis, object is moving parallel to principal, mirror is moving parallel to principal axis. If somebody asks you, sir, in this case, image, let's suppose, what is the velocity of the image? Velocity of image will be minus m square into velocity of object with respect to mirror. Guys, this is the relative velocity. Velocity of image with respect to mirror is equal to minus m square. M square is magnification. Velocity of object with respect to mirror. And this will be the velocity of image with respect to mirror. Keep that thing in your mind. Now, my dear friends, in 99% cases, velocity of mirror would be 0. We consider mirror at rest. Then, can we write this formula? Come over here. Can we write this formula? Guys, see, Vi minus Vm. Why? Because velocity of image with respect to mirror, velocity of A with respect to B, Va minus Vb, Vi minus Vm. Vi minus Vm is equal to minus m square. Vo minus Vm, velocity of object with respect to mirror. If somebody says mirror is at rest, velocity of mirror is 0, so this will be 0, this will be 0. So velocity of image will be equal to minus m square velocity of object. And my dear friends, this is the velocity of the image with respect to the ground. With respect to the ground. Keep that thing in your mind. And this is when mirror is at rest. This is when mirror is at rest. Where m is the magnification. I hope this is crystalline clear. This is the velocity of the image. This is the velocity of the image. Okay. Now, this magnification you can write. Magnification is V by U also. So V square by U square. Minus V square by U square. Something like that. I hope this is crystal and clear. Okay. I hope this is crystal and clear. Okay. I am not leaving any of the topics. Don't worry about that. But if there is a small point which is not important at all, okay. So if there are students who still think that, sir, I need to cover that also, you can refer to the game of NEET 2.0. Over there it is mentioned. Okay. Now guys, listen to me very carefully. Let's suppose you have got here. Guys, first give me the signal in the chats. Is this crystal and clear till over here? And if you have not liked the session, and I would want you guys to smash the like button. Everyone means everyone. Now guys, take a look. The velocity of the image with respect to the ground in the figure is, okay. Now guys, mirror is stationary. You guys are supposed to tell me what is the velocity of the image with respect to the ground in this particular case. Please tell me the answer of this particular question in the chats quickly, as soon as possible. Quickly in the chats, guys. Let me know the answer of this particular question in the chats. I'm waiting for your answer. Tell me. Guys. See. This is a spherical mirror over here. How do we find mirror is at rest? If mirror is at rest, how do we find the velocity of image? Velocity of image will be minus m square, magnification square. Okay. Then we say velocity of object. You have got this object over here. Object is moving with 5 meters per second. Okay. And guys, this is the direction of incident rays. This side we consider as positive, and this will be over here negative. This will be negative. Now tell me, let's find the magnification first. Sir, magnification will be f upon f minus u in terms of focal length and position of the object. So magnification in this particular case will be f is how much? F in this case is given as 30, and that is minus 30. So f in this particular case is minus 30, u in this case is minus 20. So I can say this is minus 30 upon, this is minus 30 plus we say u is 20. Because it is minus 20, minus into minus is plus 20. So m will come out to be, this is 30 minus 20, that is minus 10. So minus 30 minus 10, that will be plus 3. Magnification is plus 3. Now guys, tell me, can I say now in this particular case, when it comes to the velocity of image, what will you say? Minus magnification square. So that is 3 square into velocity of object, that is given as, this is VO. VO is given as 5. So this is 5. So 3 square is 9, 9 5s are 45. So velocity of image is minus 45, okay, meter per second. Okay, keep that thing in your. Is this clear? Is this clear? Tell me the answer of this question, guys. Tell me the answer of this question. A point object is moving on the principal axis of a concave mirror. Okay, you have got a concave mirror over here. Okay, a point object is moving on the principal axis of the concave mirror. Okay, of focal length in this case is given as 24, and I would write over here minus 24 centimeters, because this side we consider as positive, this side we consider as negative. Okay, towards the mirror, it is moving towards the mirror. Okay. When it is at a distance of 60 centimeters, so when u is equal to minus 60 centimeters, when it is at a distance of 60 centimeters, its velocity is 9 centimeter per second. Velocity of object is 9 centimeter per second. Okay, what is the velocity of the image at that instant? Once again the same question, guys. When it comes to the velocity of image, it is minus m square velocity of object. So velocity of image in this particular case will be minus m square. Let's find the magnification first, guys. Magnification is f upon minus u. Tell me here, what is the value of f? F is given as minus 24 upon, what is the value of f? Minus 24 plus 60. Plus 60, because u is given as minus 60, minus into minus is plus. So magnification in this case will be minus 2 by 3. Minus 2 by 3. Now tell me, let's find the velocity of image. Velocity of image will be minus m square, that is minus m square, that is minus 2 by 3 whole square. And then we say velocity of object, that is 9 centimeter per second. So velocity of image will be, okay, minus into, this will be 4 by 9, minus 4 divided by 9 into 9. 9 and 9 will cancel. Velocity of image will be minus 4 centimeter per second. Okay, minus 4 centimeter per second. Is this clear? Okay, is this clear? Yes. Minus 4 centimeter per second away from the mirror. Away from the mirror. Keep that thing in your mind. Okay. Because in the starting I told you, if the body is moving towards right, we consider its velocity as positive. Do not take the sign conventions. This, no. These sign conventions are not for the velocity. If body is moving towards right, velocity is positive. If body is moving towards left, velocity is negative. So if this is minus 4, so body is moving away from the mirror. So body is moving away from the mirror. Is that clear? So I would write over here body image moving away from the mirror. Okay. Just a second. Now guys, take a look over here. Power of the mirror. Power of a mirror is defined as the ability to converge or diverge the light rays. Power of the mirror is the ability of the mirror to converge or diverge the light rays. Let's suppose I'm saying you have got a mirror over here, okay, in this particular case. Let's suppose I'm taking this. This is the mirror over here. The light ray is falling on this one, it will be diverged. Light ray is falling, it will be diverged. If I say power of the mirror is more, it has the more diverging power. Okay. So that's how we define the power of a mirror. It is the ability of a mirror to converge or diverge the light rays. Okay. Then if somebody asks you, find the power of a mirror, how do we find it? It is -1 upon f in meters. Whatever is the focal length of the mirror, so that will give you the power of the mirror. So it will be simply that is -100 upon f focal length in centimeters. So when you are supposed to write in centimeters, so it will be 100 by centimeters, in meters 100 by this. Like my dear friends, in this particular case, if I say I have got over here a mirror of a concave mirror, find the power of a concave mirror. This is a concave mirror. Okay. And we know in this particular case, we'll be placing the object over here. So focal length of concave mirror is -20 centimeters. If you find its power, that is -100 upon focal length in centimeters, that is 20. Okay, it will be -20. Why? Because focal length is -20. So this will be, and this is 5. So focal length power in this case will be 5 diopter. We mention it in diopter, plus 5 diopter. Similarly, if somebody asks you, find the power of a convex mirror of focal length 24. Guys, in this particular case, if you have the convex mirror, this is the convex mirror. It is polished from inner side. Okay. And so a reflection takes place from this side. So here in this particular case, we say this is negative side, this is positive side. So focal length of this will be +25. So if you find out the power, -100 upon 25, because here focal length will be from the positive side. So it will be -4 diopter, -4. Okay. Over there it is positive, here it is negative. Now let's move on to the refraction. Let's move on to the refraction of light. Guys, previously we discussed a reflection. Now we'll be discussing the refraction. See, if you have got a light ray over here, okay, this is the light ray, and my dear friends, this light ray which falls, guys understand here, this is the surface, above the surface you have got one medium one, below the surface you have got another medium means, let's suppose above the surface you have got air, below the surface you have got water. That's why we say medium 1, medium 2. Now guys, I'm saying in this particular case, I would want you to focus. If this light ray falls onto the surface, this is called the incident ray. If this incident ray falls onto this surface, now if it is reflected in the same medium, then it is considered as a reflection. It is called the reflection of light. Previously we discussed. Like you say, sir, angle of incidence is equal to angle of reflection. Then my dear friends, if you have a light ray, if it is moving into another medium, if it is basically transferred, if it goes into the other medium, If a light ray goes from one medium to the another medium, it is called the refraction. We say if a light ray goes from one medium to another, it is called refraction. If a light ray goes from one medium to another, it is called refraction. Keep that thing in your mind. It is called refraction. Now guys, in case of, let's suppose velocity of this light in the medium is v, and we say wavelength is lambda, frequency is f. So velocity is v, wavelength is lambda, frequency is f. Directly remember guys, if light is reflected in the same medium, velocity, wavelength, frequency all remain the same. It does not change. But my dear friends, if the light ray is transferred into another medium, we say velocity of light changes in that medium. Here it is v, here it is v2. And its wavelength also changes. So here it is lambda 2, here it is lambda. But frequency remains same. This is the important point. Frequency remains, because frequency does not depend upon the medium. Frequency depends upon the source. Okay. So, my dear friends, you'll remember two things. If the light ray is reflected in the same medium, all the three will remain same. But if the light ray is transferred into the another medium, so frequency is same, rest of the two are different. Now guys, let's suppose if this is the rarer medium, okay, is this the rarer medium? And this is the denser medium. Like this is air, this is water. My dear friends, see, if the light ray moves from rarer medium to denser medium, it is always bent towards the normal. It will be bent towards the normal. See, this was the original path, but it is bent towards the normal. If the light ray moves from denser to rarer, it is bent away from the normal. These 2 points you need to remember. Okay. So if the light ray moves from rarer to denser, it is bent towards the normal. If it is moving from denser to rarer, it is bent away from the normal. Now guys, law of refraction. Like we studied law of reflection, similarly we have law of refraction. See, what does law of refraction actually mean? You have got the incident ray in this particular case. Now, sure, refractive index of this medium is mu1. Guys, every medium has got its own refractive index. Refractive index gives us an idea how much optically denser a medium is. So I say, sir, this refractive gives us an idea how much optically the denser medium is. Sir, this has got large refractive index, denser medium. Sir, rarer medium, less refractive index. So my dear friends, let's suppose refractive index mu is for this is mu1, for this is mu2. Okay. Now I am saying in this particular case, the light ray goes from one medium to another medium. So this is the case of refraction. Now, this is the original path of incident ray. Due to the refraction, it is bent towards the normal. So means this is denser medium. So this is denser medium. This is rarer medium. This is denser and this is rarer. Now guys, angle between normal and this incident ray, it is called angle of incidence. Angle between normal and refracted ray, this is called refracted ray. This is called angle of refraction. Sir, do we say over here angle I is equal to angle R? No, we do not say it over here. That is over there. Now, what is the first law that we discuss over here? That is incident ray, refracted ray and normal all lie in the same plane. Next, what we say? Then the second law we say is called the Snell's law. Directly remember the Snell's law. What do we have to learn in this one? See, that is mu I, refractive index of that medium where incident rays are present, into sin I. sine of angle of incidence. This mu I into sine I. Sir, how do we find mu I? Mu I is that refractive index of that medium in which incident rays are present. Incident rays present in the upper medium. So this is mu of this will be mu I. If you send the incident ray something like this, then this will be mu I. This medium will be mu I. Okay, so we say mu I into sine I. Mu I, refractive index of this medium into sine of this angle, Then you have mu R, refractive index of that medium where refracted rays are present, into sine R, Okay, into sine R, into this sine R, Now guys, this is the Snell's law in terms of refractive index. If someone says that, tell me the Snell's law in terms of speed of light. So you will be saying sine I divided by V1. What is V1? V1 is the speed of light in the medium 1 is equal to sine R divided by V2. That is the velocity of light, speed of light in the medium 2, in the another medium. Now in terms of lambda, in terms of wavelength, this Snell's law, sine I divided by lambda 1 is equal to sine R divided by lambda 2. Lambda 1 is the wavelength of the light in the first medium, and this is the wavelength of the light in the second medium. I hope this is crystal and clear. So these are the only two laws you need to remember over here. Now, what is important in this one is this case, apparent depth and apparent height. What is apparent depth and apparent height? See guys, let's suppose you have got a bucket over here. Inside the bucket, you place some stone. Okay. Now, have you ever observed that if you try to look at that stone from the upper side? So basically, it feels like if let's suppose this is the bucket and you are looking from this certain height. If you place a stone inside this bucket and it's filled with the water, it feels like stone, this is the actual depth of the stone. It feels like stone is not at the actual depth. It feels like stone is present over here at this depth. But in reality, stone is present at this depth. This is called the actual depth. But it feels like stone is present here. Okay. But when you put your hand inside the water, you have to put it down, down, down until you reach the actual height. This height is called the apparent depth. This depth is called the apparent depth. Okay. Why does it happen actually? See, let's suppose from the upper side, this is the rarer medium. From the lower side is denser medium. Object is placed here. This is the stone. Now guys, incident ray will leave from the object. Okay. This is denser medium. This is rarer medium. So when the light ray goes from rarer to denser to rarer, it goes away from the normal. It moves away from the normal. Now, if this is the refracted ray, if you extend this refracted ray, it will meet here. The point where refracted rays meet, that is what we call the image. Or the point where reflected rays also meet, that is called the image. And my dear friends, basically, this observer is seeing the image of this object. So that's why it feels like object is present here. But in reality, object is present at the actual depth, that is D. So this is called the apparent depth. Now, if somebody asks you what is the value of this apparent D dash is equal to D actual depth upon mu I by mu R. What is mu I? Mu I is the refractive index of that medium in which incident rays are present. Mu R is the refractive index of that medium in which refracted rays are present. So we say mu I by mu R. Now, similarly, this is valid for virtual object also. Let's suppose the incident rays are coming something like this. Now, in this particular case, we say after refraction it will be bent. So they will meet over here. Now guys, these light rays are meeting actually at this point. These light rays, not actually. If we extend these incident rays, they appear to meet over here. This is the object, virtual object. and these reflected rays meet over here, refracted rays meet over here, this will be the image. Now in this particular case, guys, this is object happened. In this particular case, this is the object, this is the image. This is the depth D. This is the apparent depth D dash. This will be the actual depth. Now let me show you the question. See, in this question, it says that find the apparent depth of fish with respect to the bird. This is the tank, this is a fish tank problem. And there is a bird at height of 36 centimeter. This fish is present over here, which is at a depth of 24 centimeter. This is the actual depth. You have to find the, but when bird is looking at the fish, bird will see that the fish is present at the apparent depth, not the actual depth. And we say apparent depth of fish. Guys, how do we find the apparent depth of fish? D dash is equal to D upon mu I by mu R. Now, D means the actual depth of fish, that is 24 centimeter. 24 upon mu I, refractive index of that medium in which incident rays are present. Guys, see. If this is the object, incident rays will leave from the object. So this is the medium where incident rays are present. So its refractive index is 4 by 3. So mu I is 4 by 3. Refracted rays, refractive index of that medium where refracted rays are present. Refracted rays will be present in this upper medium. So it's air. For air, refractive index is always 1. So it will be 1. Okay. So 4 by 3. Okay. Now, my dear friends, you can write it 24 by 4 into, we can say 3. Okay. 4 ones are 4 6s are. So it will come out to be 18 centimeters. So according to the bird, this fish is at 18 centimeters, but in reality, it is at 24 centimeters depth. Similarly, we say apparent height of bird. Guys, what is the actual height of bird? That is 36 centimeter above the surface, above the water. Now, when fish is looking at the bird, so let's suppose you are a fish inside the water, you are looking at that bird. It feels like that is at apparent height, not the actual height. So I can say H dash will be equals to H upon mu I by mu R. Same formula here also. What is the actual height? That is 36 upon mu I, refractive index of that medium where incident rays are present. Right now, bird is object, this is observer. So right now, incident rays will leave from the bird. So here, refractive index mu I is 1. So 1 upon. Then those refracted rays go into the water. So mu R is 4 by 3. So this will be, if you do the reciprocal, again reciprocal. So this will be 36 into 4 by 3 only. Okay. So this will be 48. Is this crystalline clear? Is this crystalline clear? Is this crystalline clear? Now, guys, I would want you to focus over here. Here you have a refraction through a parallel slab. Refraction through a parallel slab. See, guys, let's suppose you have got a slab over here. Okay. You might have seen this slab in a rectangular slab in your schools. Okay. The light ray is falling onto this slab. Okay. Let's suppose this is the normal. So here, slab has got the refractive index mu m. The refractive index of air is, we say, sir, 1. So this is denser medium, this is rarer medium. When light goes from rarer to denser, it is bent towards the normal. Again, second refraction will take place. Here, light ray is moving from denser to rarer. It will bend away from the normal. Okay, it will bend away from the normal. So two refractions are taking place. First at this surface, second at this surface. Okay. And in this particular case, this is called the angle of incidence. Okay. This is the angle of refraction at first surface. Then, when here refraction takes place, this is the angle of incidence, this R, this angle of incidence at second surface. And this is the angle of refraction at second surface. This is also called angle of emergence. Now guys, what I'm trying to say is that this is the light ray. Its original path was this. But after two refractions, it is the path. This is called the shift. How much is the shift in the original ray? T upon cos R. R is this angle. T is this width. T is this width. Okay. Sine of I minus R. Sine of I minus R. Okay. I is the angle of incidence. R is the angle of refraction. Okay. This will be the shift. This will be the deviation kind of, you can say, or a shift, you can say. Next. Okay. Take a look at this. Okay. Now guys, see. Let's suppose you have a slab over here. In front of the slab, you have an object over here. Understand this very carefully. You have an object. Now there is an observer. Between the observer and the object, there is a slab. Basically, this observer is trying to look at the object. Okay. Now incident ray will leave from this object. It will enter the slab. Okay. So it will be bent. Again, when it leaves the slab, one medium to another medium, again it will be bent. This is the final ray. Now guys, this is the final ray or the refracted ray. If you extend this refracted ray, the point where it meets, that will be the image. Now, if this object is here, observer is here, observer wants to see the object. He won't be able to see the object, he will be able to see its image. So kind of, I can say here, object has shifted due to the slab. If you remove the slab, this observer will say directly object is here. But if you put the slab, observer will say object is here. So how much is the shift in the observer? That is X. So here, this shift X is T. T is the width of the slab. 1 minus 1 by mu relative. This is called the relative refractive index. Mu m by mu s. That is refractive index of this medium divided by refractive index of the surrounding. If it is air, so then it is 1. So this is how you can find the shift in the observer due to the slab. Next, shift for virtual objects. See guys, let's suppose this is the slab over here. Okay. In this particular case, object is at very far. Now these are the light rays coming. When they enter this slab, these will be bent. Again, when they leave the slab, again they will bend and they will meet over here. And this is the point, my dear friends, understand very carefully. This is the point where image will be formed. Yes, sir. But in reality, if you extend these incident rays, so it will meet over here. So this is the virtual object over here. Because incident rays appear to meet. This is the incident, this is the virtual object over here. But due to the slab, we said this bending took place and these rays meet over here. So due to the slab, this object has shifted to this. Now, if there is an observer which is looking at this object, he would be able to see it here. So here, this shift will be T into 1 minus mu relative. Same like the previous case. So due to the slab, this shifting is taking place for virtual objects also, for real objects also. Here the object is real. Here the object is real. Okay. And here the object is virtual. This shift is taking place because of the... Now you have got the critical angle and total internal reflection. See guys. Let's suppose you have two mediums. This is the surface. Above the surface you have rarer medium. Below the surface you have denser medium. And denser medium has got refractive index mu d. Rarer medium has got refractive index mu r. Okay. Now guys, a light ray is coming in this particular case. light ray is coming in this particular case, and this is called the incident light ray. It is moving from denser to rarer. Whenever the light moves from denser to rarer, it is bent away from the normal. It is bent away from the normal. This is the angle of incidence. This is the angle of refraction. Okay. Now guys, understand this very carefully. I'll just write in this case, I'll just write over here. Guys, if let's suppose angle I, R is, let's suppose I is 30, R is something 60. If you increase I, R will again increase. We say as we increase I, R will also increase. As we increase I, R will also increase. As we increase I, R will also increase. Okay. As we increase I, R will also increase. Now, my dear friends, in this particular case, as we increase I, R will also increase. At certain value of I, angle R will be equal to 90 degrees. Guys, as you keep on increasing the angle of incidence, R will keep on increasing. At certain value of I, R will be, angle of refraction will be 90 degrees. So my dear friends, that value of I is called critical angle. That value of I is called critical angle. That value of I is called critical angle. So critical angle is that angle at which refracted ray makes 90 degree with the normal. Okay, and we represent that with theta c, where angle R is equal to 90 degrees. Okay. Now guys, if we use the Snell's law over here, how do we use the Snell's law? Sir, we write it something like this. Guys, see, mu I, refractive index of that medium where incident rays are present, into sine of I is equal to mu R into sine of R. Okay. Now what is mu I in this case? Mu I is that angle. That refractive index of that medium where incident rays are present. That is this denser medium. So I'll write over here mu D sine of I is equal to mu R. So this is the rarer medium, mu R, where reflected rays are present, sine R, that is sine of 90. Because at sine I, this sine I is basically theta c, because we are saying that value of I at which theta is 90 degrees. Here this refracted angle is 90 degrees. That is critical angle. So that's why. So sine theta c, sine 90 is 1. So I can say sine of theta c will come out to be mu R by mu D. This is the value of critical. This is the value of critical angle. Now, see, guys, as you keep on increasing the value of angle of incidence, we say at certain value, a refracted ray makes 90 degree with the normal. If you further keep on increasing the value of angle of incidence, if angle of incidence becomes greater than theta c, then this refracted ray will be reflected in the same medium, and then we call it the total internal reflection. Because if the refracted ray is reflected in the same medium, we say that is what we call the reflection. So here we call it the total internal reflection. When does total internal reflection takes place? When I is greater than theta c. If I is greater than theta c, total internal reflection will take. Now, let's suppose you have got a question here. Question is, the light ray falls on the surface, its critical angle will be. Guys, this is the denser medium, this is the rarer medium. This is the incident ray, this is the refracted ray. Okay. Now you guys are supposed to tell me critical angle. Guys, simple. Sine of theta c will be equals to mu d divided by mu r. Recently I told you. So I can say sine of theta c will be equals to mu d. Refractive index of denser medium, that is root 2. Refractive index of rarer medium, that is 1. Okay. Denser by rarer by denser. That's what I was. Sine of theta c is equal to mu r by mu d is equal. What is the value of free? This is 1 divided by root 2. When is the value of sine theta as 1 by root 2? When theta is equal to 45 degrees. So in this case, critical angle is 45 degrees. Okay. What about this one? What about this one? If the critical angle for total internal reflection from medium to vacuum is 30 degrees. Okay. Then the velocity of light in that medium will be. Velocity of light in that medium will be. Guys, solve this. Tell me the answer of this question. If the total internal reflection from medium to vacuum, so basically you have got two mediums over here. Okay. So this is a medium. This is vacuum. So it says that light moves from, this is a normal. It says that light moves from medium to vacuum, This is the incident ray. Okay. If the critical angle, okay, critical angle in this case is given as 30 degrees. Critical angle in this case is given as 30 degrees. This is vacuum. Always remember, for vacuum, refractive index is 1. For air, refractive index is 1. And here theta c, we are supposed to find the refractive index of this medium first. Then we'll find their velocity. Basically, a light ray goes from this medium to this medium. Critical angle is given as 30. Okay. They are saying that what is the velocity of light in this medium? So in order to find the velocity of light, guys, velocity of light in a medium, always remember it is velocity of light in air divided by refractive index of that medium. So if we get the refractive index here, you can put it here and you will get the velocity of light in the medium. Now tell me, how do we find the refractive index of this medium? See, I'll write sine of theta c is equal to mu r divided by mu d. Critical angle is 30 degrees. So I can write over here, sine of 30 degree is equal to mu r. Rarer medium has got 1, mu d. I can say that is mu d over here. Sine 30 is 1 by 2 is equal to 1 by mu d. And here mu d comes out to be equal to 2. Refractive index of this medium is 2. Now velocity of light in this medium. So I can say V is equal to C, speed of light in air, 3 into 10 raised power 8 divided by mu is given as 2. 1.5, 3 by 2 is 1.5 into 10 raised power 8 meter per second. This is the velocity of light in that medium. Let's talk about the prism. Let's talk about the prism. Now guys, you might have seen the prism in your school. This is the prism. You might have seen it in your school, something like this. Okay. Light goes into the prism. Okay. Then it is bent. Then again it is bent. Okay. So I'll make it prism something like this. This is the front face. This is the prism. And this prism has got the refractive index, let's suppose mu. Its refractive index is mu. Okay, because it's a denser medium. Now, what I'm trying to say in this case is, a light ray moves from rarer medium. This is, let's suppose, air. Light ray moves from rarer medium to denser medium. This is the normal on the surface. Whenever the light ray moves from denser to rarer, rarer to denser, we say it is bent away from the, it is bent towards the normal. See, it is bent towards the normal. So refraction takes place. Now this is angle of incidence, this is angle of refraction. Now this light ray further goes, again it moves from denser to rarer, another refraction will take place. Okay, now here, this is normal. In this particular case, my dear friends, this will be considered as the angle of incidence, this will be considered as the angle of refraction. Angle of incidence, this is angle of refraction. Angle of incidence, angle of refraction. Now, my dear friends, see. This angle is also called the angle of emergence. See, this A is called the angle of prism, or you call the apex angle. I is called the angle of incidence on the first surface. R is the angle of refraction on the first surface. R2 is the angle of incidence for second surface. R2 is the angle of incidence for second surface. And E is the angle of emergence or angle of refraction on the second surface, or angle of... Okay. Now guys, wait for the break. We'll take the break exactly at 1:24. We'll take the break at approximately 2:30. Okay, because we'll have to finish 7 chapters. Okay, keep that thing in your mind. Wait. Or 2:15 we'll take the break. Let's see. Now, so this is how do we define the prism. Now guys, understand one thing. See, this is the original path of the incident ray. This is the final ray. Can I say this is what we call the deviation? This is the deviation in the original ray. This is the deviation in the incident ray. Now, I can say in this particular case, if somebody asks you, how much is the deviation in case of the prism? You say this deviation is I plus E minus A. I plus E minus A. Okay. And if somebody asks you how to find the angle of prism, R1 plus R2. R1 plus R2. This R1 plus R2 is equal to angle of prism. Okay. Now guys, if somebody says that apply the Snell's law on surface 1, apply the Snell's law on surface 1, because whenever the refraction takes place, we can apply the Snell's law. You say refractive index of this medium and sine of I is equal to refractive index of this medium and sine of R. See, I have done that over here. Mu air, refractive index of air, sine of I. Refractive index of prism, sine of R1, because here this is R1. You can apply the Snell's law on the second surface also. You can apply the Snell's law on the second surface also. So mu into sine of R2, mu refractive index of this medium into sine of this angle of incidence, that is R2. Then mu air into sine of E, mu air into sine of E. You can apply the Snell's law on both the surfaces. Let's talk about this one. This is the question we need to solve over here. Find R1, R2, E and delta, deviation. Angle of prism in this case is given as 75 degrees. Understand very carefully. I is given as 45 degrees. Guys, you need to first tell me, okay, do one thing. Apply Snell's law on S1, on surface 1. Okay, because here refraction will take place, another refraction will take place here. So how do we use? Sir, mu I, that is refractive index of this medium, that is 1, because refractive index of air is 1. Sine of I, we say sine of 45 is equal to refractive index of this medium, that is root 2, sine of this angle R1, sine of R1. Okay. Now sine 45 is 1 by root 2 is equal to, this is root 2 sine of R1. 1 by root 2 into this root 2 will become 1 by 2. So sine of R1 is equal to 1 by 2. When is the value of sine as 1 by 2? When R1 is 30 degrees. And theta is 30 degrees. Okay. So you got the value of R1. Now can I say as angle of prism A is equal to R1 plus R2? Yes. A is given as 75 degrees is equal to R1 we got as 30 degrees plus we say R2. So from here R2 will come out to be 75 minus 30, that is 45. R2 comes out to be 45. Now, apply Snell's law. Apply Snell's law on S2. This is the surface S2 over here, and this is S1. Now, what does that say? Refractive index of this medium and this angle over here will be R2, and this angle will be angle of emergence. So, refractive index of that medium, that is root 2 sine of R2. Okay, sine R2. R2 is how much? 45. Is equal to refractive index of this medium. This is air, so it is 1. So it is air. It is 1. And sine of E, sine of angle of emergence, or sine 45 is 1 by root 2. So it is root 2 into 1 by root 2 is equal to sine of E. Now tell me, root 2 will cancel. Sine E is equal to 1. E will be equals to 90 degrees. So we got the value of angle of emergence as 90. If somebody asks you what is the deviation, deviation is equal to I plus E minus A. I plus E. What is the value of I? That is 45 plus 90 minus, what is the value of A? A is 75. 60 degrees. Deviation came out to be. Now, one more thing I just want to tell you, that is, if you make the graph between deviation and angle of incidence, if you make the graph between deviation and angle of incidence, it is coming out to be something like this. This is the maximum deviation, this will be the minimum deviation. Okay? And for minimum deviation, keep that thing in your mind. If I is equal to E, if angle of incidence is equal to the angle of emergence, angle of incidence is equal to angle of emergence, then the deviation will be minimum. So if I is equal to E, deviation will be minimum. Okay? And in that case, always remember, guys, in case of minimum deviation, R1 and R2 will be equal. We can call it R. If R1 and R2 is equal, so can I say, guys, A is equal to R plus R. So A is equal to 2R. So R is equal to A by 2. Because we say A1 plus R1 plus R2 is equal to A. So R will be equal to A by 2. And in that case, deviation will be 2i minus A. Why? Because when it comes to a deviation, it is I plus E minus A. So both are equal. So you can say 2i. I plus I is 2i minus A. So these are the cases or the conditions when in case of the minimum deviation. Now, let's take a look. If somebody asks you, sir, can you find the refractive index of a prism? Is there any formula? This is the refractive index of the prism by this formula. Sine of A. A is the angle of prism plus minimum deviation. If minimum deviation is given, you can find it. Upon sine of A by 2. Okay. Like you have over here. 60-degree prism has a root 2 angle of incidence. So I is given as, okay, angle of incidence. For the minimum deviation is. So we are supposed to find angle of incidence. We have got a prism and this is 60-degree prism. Okay. Here we are supposed to find the angle of incidence. In this particular case. Now tell me guys, and refractive index of this is given as a root 2. This is normal. This is angle of incidence. Okay. Guys, tell me one thing. It says that 60-degree prism has mu is equal to root 2. Angle of incidence for minimum deviation is, and here in case of minimum deviation, we say I is equal to E. And we say R is equal to A divided by 2. Angle R1 is equal to R2 is equal to R is equal to A by 2. What is A? That is 60 divided by 2, which is 30 degrees over here. Yes, this is 30 degrees over here. Now guys, use Snell's law. Apply Snell's law. Apply Snell's law. What will you say? You'll say mu I sin I is equal to mu R sin R. What is mu I? Refractive index of this medium, that is air, that is 1. Sine of I we need to find out is equal to mu R. Refractive index of this medium, that is root 2. Sine of R. R we are getting over here as 30 degrees, sine 30. Sine of 30. Sine 30 is how much? That is 1 by 2. So you can write over here sine I is equal to root 2. Sine 30 is 1 by 2. So you can say in this particular case sine I is equal to, so root 2 into 1 by 2. So I would want you guys to do one thing. Multiply with root 2 and divide with root 2. Root 2 into root 2 is 2. That will cancel with this one. So it will come out to be 1 by 2. When is the value of sine 30 as 1 by 2? When the value of theta is 30 degrees, 45. So angle of incidence in this case is 45 degrees. Please tell me in the chats if this is crystalline clear. Tell me guys. Is this crystalline clear? Let me know in the chats. And smash the like button, everybody out there. Okay, take a look at this one. If the angle of minimum deviation is 60 degrees for an equilateral prism, you have got an equilateral prism. You have got an equilateral prism. Its angle of prism A is given as 60 degrees. Then the refractive index of the material, then the refractive index for the material of the prism will be, if the angle of minimum deviation, this is not the angle of minimum. So here minimum deviation, angle of minimum deviation is given as, S minimum is given as 60 degrees. Okay. Then the refractive index of the prism will be, okay. Okay. Now my dear friends, refractive index mu is equal to, if you want to find out sine of A plus minimum, and this is an equilateral prism. Equilateral prism, this is also, if the angle of minimum deviation is 60 degrees for an equilateral prism, this is also 60 by the way. Okay. Mu is equal to sine of A plus minimum deviation divided by 2 upon sine of A by 2 upon sine of A by 2. Now guys tell me, this is sine of A. A is given as 60 plus sine of minimum deviation divided by 2, that is 60 by 2, that is 30 upon sine of A by 2, that is sine 30. Okay. So 60 plus 30, sine of 90 divided by sine of 30. What am I doing? So minimum deviation in this particular case is 60 divided by 2. Sine of A is 60. 2. Sine of A by 2 is given as 60. A is 60. 60 by 2 is 30. Sine 30. And 60 plus 30 is 90. 90 by sine 30. Is this what you are getting, guys? 2. A is 60. How A is 60? Because it says that equilateral prism. Equilateral triangle has got an angle of 60 degrees. All the angles in case of equilateral triangle is 60 degrees. Okay. Is that clear? Okay. When we'll take the break exactly at. Okay. Yes, 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 yes. It is whole divided by 2. Sorry, 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 sorry. I made a mistake over here. That's why it is whole divided by 2. That's why I was getting the wrong answer. It is whole divided by 2. It is whole divided. Okay. Now you can say sine of A. A is given as 60 plus 60 divided by 2 upon sine of 60 divided by. Now it is correct. So sine 60 plus 60 is 120. 120 by 2 is sine of 60 divided by sine of 60 by 2 is sine 30. Okay, put the values. This is 1 by 2 and this is root 3 by 2. 1.73 around, something like that. That will be the correct answer. Now guys, let's talk about the dispersion. Let's talk about the dispersion. Dispersion of light. It is the process of splitting of white light into 7 different colors. Let's suppose guys, you have a medium over here. It is air from this side. It is mu medium from this side. A white light is entering. Okay. This is, let's suppose, normal. This is the surface. Right now, this is not the surface. Keep that thing in your mind. This is the surface which is dividing the two mediums. From this side it is air, from this side it is medium. And this is the normal. This will be the angle of incidence over here. Now, if this white light is divided into 7 different colors, this violet, indigo, V, I, B, 1, 2, 3, 4, 5, 6. It is divided into 7 different colors. Violet, indigo, blue, green, yellow, orange, red. V, I, B, G, Y, O, R. So V, I. Then I'll make the indigo over here. Indigo, let's suppose that is this one. This is the indigo one. Okay. So this splitting of white light into 7 different colors is called the dispersion of light. Like in this particular case, there is an example which is mentioned. You have got a white light entering the prism. Now it is basically divided into 7 different colors. Violet, indigo, blue, green, orange, green, yellow, orange, red. VIBGYOR. VIBGYOR. This is called the dispersion of light. Now guys, let's understand dispersion through prism. Let's suppose you are taking a prism. White light is entering. Now guys, here. White light is dispersing in 7 different colors. I'll make only 3. Okay, this is violet. Then I'll take yellow and then I'll take red. Topmost. I'll take 3 only. Okay, all the colors will be there. I'll take yellow, this violet, yellow, red. Okay, this is how we define it. Now, my dear friends, this is the original path of the incident ray, original path of the white light. Now, when this violet goes over here, we say it will be again refracted. Why? Because light is moving from rarer to denser to rarer. Here it was moving from rarer to denser. Again, this yellow will be refracted something like this. Again, this red will be another. If somebody says where is indigo, indigo will be here. If somebody says where is green, green will be somewhere around over here. Okay. Now guys, see. In this particular case, can I say, this is what we call the deviation of red. This is the path of red. Original path was this. This is what we call the deviation of red, delta R. This is what we call the deviation of violet, delta V. This is called the deviation of yellow, delta Y. And this is what we call the angle between, or we say this distance between this red and this yellow. this violet. Okay, okay. Now guys, delta Y is the deviation of yellow light, delta V is the deviation of violet light, delta R is the deviation of red light. And how do we find this deviation of violet? Sir, refractive index of violet. Guys, always remember, when this white light enters into a medium, this medium is going to offer different refractive index to all the colors. Sir, violet will have different refractive index here? Yes. Okay. So this has refractive index different. Okay. Now, my dear friends, all will have different refractive index. So this medium is offering all different refractive index to all. Now here we say deviation of violet, we can find refractive index of violet -1 into A, where A is the angle of prism. Deviation of red will be refractive index of red -1 into angle of prism. And this theta, this deviation between red and violet, it will be deviation of red, violet minus deviation of red. You can also write it something like this in terms of refractive index, mu V minus mu R into A. Mu V minus mu R into A. Next, guys, then we define also mean deviation over here. How do we define mean deviation? Mean deviation is mean refractive index. Okay, I'll tell you how to find it. -1 into angle of prism. And how do you find mean refractive index? Mu V plus mu R divided by 2. If you know the refractive index of violet, if you know the refractive index of red, divide it with the 2, you'll get the mean refractive index. Or there is another formula for mean deviation. So mean deviation is also equal to deviation of violet plus deviation of red divided by 2. Now another term we define over here, that is dispersive power. So dispersive power says that how much a material is able to disperse the white light. If a material is able to disperse the white light more, it has got more dispersive power. Okay, so different prisms will have different dispersive power. And how do we define this dispersive power? So it will be dispersive power is equal to theta. Okay, and what is theta? Theta is this deviation between red and violet. That is deviation minus red of violet minus red. Okay, okay. So, or you can say mu divided by mean deviation. So you can also write it mu V minus mu R into A upon mu mean minus A, because the value of this is this, value of this is this, and this will cancel. This will be the dispersive power. Or you can write this dispersive power something like this also. That is, instead of theta, you can write SV plus SR, because theta is SV minus SR. SV, not SV, delta V minus delta R upon mean deviation. Mean deviation you can write over here delta V plus delta R divided by 2. This is also how we can write the dispersive power. Let me show you the question on this. The question is something like this. Compare the dispersive power of two prisms. Compare the dispersive power of two prisms. If one of them deviates violet light by and red rays by 10 degree and 6 degree. This is the prism. Okay. Its deviation of violet is 10. Deviation of red is 6. So in this case, it is deviating the violet light by 10 degrees, deviating the red light by 6 degrees. Now, if somebody says that, what is the dispersive power here? We'll be saying, sir, dispersive power is delta V minus delta R divided by delta V plus delta R divided by 2. Simply, for this, delta V is how much? 10 minus 6. 10 minus 6 upon 10 plus 6 divided by 2. 10 minus 6 is 4 divided by 10 plus 6 is 8. This is 16 by 2 is 8. So that will be 0.5. Now, if somebody asks you, for another prism, you have got one more prism. Okay. For this prism, deviation of violet is 8 degrees. Deviation of red is 4.5 degrees. And if you want to find the dispersive power in this case, what will you say? That is SV plus SV minus SR. 8 minus 4.5 divided by 8 plus 4.5 divided by 2. Okay, that is 3.5 divided by 12.5 divided by 2 is 6.25. So this will be 0.56. Check it. Next you have refraction at the spherical surfaces. 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 Now guys, take a look in this particular case. See, when it comes to the refraction at spherical surfaces, you have got a surface. Previously, we spoke about the refraction in this particular case. Let me show you here. We discussed the refraction in this particular case previously. All of this refraction here, this refraction. So this surface was plane surface. This is called the refraction at the plane surface. Light is moving from one medium to another medium and the surface is plane. Let's suppose if the surface is spherical. Over there, how you can explain the concept of refraction? How you can explain the concept of refraction? Refraction at spherical surfaces. Like my dear friends, you have got a surface over here. From this surface, on this surface it is medium 1. On the another surface it is medium 2. This is the refractive index of here, medium mu I. Refractive index of this medium is mu r. Object is present here. This is the incident ray. Sir, in case of the mirrors, it was reflecting, but right now it is refracting. It will move to the another medium, something like this. Let's suppose object is here, its image will be here. And in this case, we are saying this is the position of the object. This will be the position of the image. Okay. Now, here if somebody asks you, I'll give you the position of the object. I'll give you the refractive index in this case. Tell me what is the position of the image. So you can use this formula. Like you have over there 1 by V plus 1 by U is equal to 1 by F. Here you have mu R divided by V. Refractive index of that medium where refracted rays are present. Please note it down. Then you say minus mu I by U. Refractive index of that medium where incident rays are present. Mu R minus mu I divided by R. Here also you can find the magnification. That is V divided by mu R upon U divided by mu I. Okay. Even you can find the velocity of image also with respect to the spherical mirror. Okay. With respect to the spherical surface. Like over there, you are finding velocity of the image with respect to the mirror. Here it is with respect to the spherical surface. So it is V velocity of image with respect to the spherical surface. So it is V square by U square. Okay. V square by U square. Mu I by mu R. Mu I is refractive index of that medium where incident rays are present. Refractive index of that medium where refracted rays are present. Into velocity of object with respect to the spherical surface. This is how we find over here. This is how we find over here. Let's suppose we have got this question in this particular case. I would want you to tell me the answer. Given the spherical surface of radius 20 centimeter. Okay. Given the spherical surface of radius 20 centimeter. Here, radius of the spherical surfaces, radius of curvature is given as 20 centimeter. Okay. Mu I is given as 2, mu R is given as 3. Refractive index of this medium is 2, refractive index of this medium is 3. And you guys need to take care of the sign conventions also. If this is the object, this will be the direction of incident rays. So this will be positive side, this will be negative side. Keep that thing in your mind. This will be positive side and this will be negative side. And Object in this particular case is present as minus 15 centimeters. Why? Because it is on the negative side. You guys are supposed to tell me, what is going to be the position of the image. Find the position and size of the image also. Basically magnification as well as position. Come on, give it a shot. Directly you will have to apply the formula and you will have to get the answer in this case. Tell me guys, quickly. Tell me. Now guys, see. What is the formula I'm supposed to use in this case? Simple. Mu r by v minus mu I by u is equal to this one. So I will say as mu r divided by v minus mu I divided by u is equal to mu r minus mu I divided by this r. This is the formula that we have. Okay. Now guys, what is the value of mu r? That is 3 divided by v minus mu I is given as 2 divided by u is given as minus 15, so it will be plus over here, is equal to mu r minus mu I. Mu r is 3 minus 2 divided by radius in this particular case is given as, guys, radius will be from this side. Radius of this is from this side. So I can say radius is plus 20. So it will be over here. Solve this, v will come out to be, that is minus 36. Minus 36. Similarly, you can find the size also, magnification also. How do we find the magnification? You can use the formula v divided by mu r, v divided by mu r upon u divided by mu I into mu I into u. Just put the values. So what is the value of u in this particular case? U in this particular case is minus 15 divided by mu r in this particular case is 3 into mu I in this particular case is, that is 2, and u comes out to be minus 36. So it is 24 by. Okay. Is this clear? Is this clear? Next we have lenses over here. Guys, next we have lenses. What is a lens? We say a lens is made up of two surfaces in which refraction takes place. See guys, there are two types of lenses. We have convex lens and we have concave lens. There are two types of, like you have concave mirrors, convex mirrors. Similarly, convex lens, concave lens. Now what is convex lens? See guys, this is the convex lens that I would say exactly over here. This is called the biconvex lens. Okay. Okay. Why? Guys, if you remember, I told you previously that bowl when you took out, this was the bowl when you took out. This was the bowl when you took out. Now, my dear friends, in this particular case, this is what we call the convex side. Okay. This is what we call the concave side. If I'm saying you take this outer side and you put one more surface from this side, okay, so it becomes, this is the convex side and this is also the convex side. So two convex sides are meeting. That's why we call it the biconvex lens. So this will have the radius of curvature from this side, that is R1. This will have the radius of curvature R2. Okay. This is having the radius of curvature R1. This is having the radius of curvature R2. Similarly, when we talk about the concave lens, guys, if this is the lens, this is the convex side, this is the concave side. Okay. Now tell me, take this concave side, take one more concave side, this inner side, join these two, concave side. This is called the biconcave lens. This is called the biconcave lens. Radius of this is R1, radius of this is R2. Biconcave, biconvex. Okay. Now guys, you have lens maker's formula here. You have lens maker's formula. Like you have mirror formula, here you have lens maker's formula. Similarly, here we have the lens maker's formula. Lens maker's formula, which helps us to find the focal length of the lens. Position of the object, position of the image. Like guys, in case of mirror formula, what do you have? 1 by V, okay, plus 1 by U is equal to 1 by F. Okay, relation between U, V and F. Similarly, here also, it is relation between U, V and F in case of lens. Now guys, see, here lens maker's formula is 1 by V. What is V? V is the position of the object. Image. What is U? U is the position of the object, is equal to mu L by mu S, refractive index of the lens divided by refractive index of surrounding. Let's suppose if it's the lens, it has got refractive index mu L, this has got surrounding mu S, minus 1. 1 by R1, let's suppose this has radius of curvature R1 and this part has radius of curvature R2, 1 by R1 plus 1 by R2. Or you can also say, instead of this, you can write 1 by F. 1 by F is equal to mu L by mu S minus 1, 1 by R1 minus 1 by R2. This is the lens maker's formula. Okay. Here, magnification, if you want to find out, V divided by U, F upon F plus U is equal to F minus V upon F in terms of F and U, in terms of U and V, in terms of F and V. Okay. And if somebody asks to find the parallel component of the velocity of the image, guys, velocity of the image in this case, how do you find out? How do you find out velocity of the image? See, you say velocity of image with respect to the lens. That will be V square divided by U square into velocity of object with respect to the lens. This is the parallel component. And when it comes to the perpendicular component, that is velocity of image with respect to the lens will be m into velocity of, here it is m square, is V square by U square, and velocity of object with respect to the lens. These are the formulas that you guys need to remember in case of the lens, like you have over here. If somebody asks you the question, calculate the focal length. Okay. Here. Guys, this is the incident ray. So this side will be positive, this side will be negative. So could you please tell me here, R1, radius of curvature of this lens will be from this side. So R1 is positive. So what is the value of R1? Plus 30. And R2 in this case is, radius of curvature of this lens will be from negative side, minus 60 centimeter. Okay. And guys, refractive index of lens is given as 3 by 2. And what else do you need? We are supposed to find the focal length. And this refractive index of air is 1. How do we find? 1 by F is equal to mu L divided by mu S minus 1. Then you write mu L divided by mu S into 1 minus 1. Then you write 1 by R1 minus 1 by R2. 1 by R1 minus 1 by 1 by R1 minus 1. Now 1 upon F will come out to be mu L, that is 3 by 2 by 1, because refractive index of surrounding is 1. I will not mention that. minus 1. 1 by R1. R1 is given as 30. Then plus, because this is minus 60. So 1 upon 6. Guys, solo it, you'll get the value of F. Now, cutting of lens. Now take a look here. You have got the cutting of lens. See guys, see guys. In this particular case, what we are supposed to learn is that cutting the lens parallel to the principal axis. Guys, let's suppose you have got a lens over here. We'll be taking the break after 3 slides. 1, 2, 3. After 3 slides, we'll be taking the break because then you have the next portion of this that is simple. That is this optical instruments. It will take us 30 minutes. Then we will move on to, then rest of the chapters are very small. This was the only chapter which is big. Rest of the chapters are very small. Okay. Now guys, cutting the lens parallel to principal axis. If you have got a lens over here, guys, if you cut the lens parallel to principal axis, if you cut the lens in multiple parts, let's suppose focal length of this lens is this is cutting. If this is F, when you cut it into multiple parts, what will happen to its focal length? Focal length remains the same. Why? Because if you join it once again, its focal length will remain the same if you cut along the principal axis. Now guys, if you have the lens, if you cut it something like this vertically, we say if its focal length is F dash, here focal length of this will be twice 2F dash, focal length of this will be 2F dash. Okay, it will be doubled. Now, if you combine the lenses, let's suppose 1, 2, 3, there are multiple lenses that you are combining. Its focal length is F1, F2, F3, and this is F. So we say instead of all the 3, you can make a one lens will be having the equivalent focal length. 1 by F equivalent is equal to 1 by F1 plus 1 by F2 plus 1 by F3. It is like some of the students might have experienced this. Like if sometimes what happens is that if you have a problem in your eyes, you go to the doctor, okay? Over there, he'll put the lens in front of you and ask you to read the letters, okay? Then he says, sir, I'm not able to read. Then he'll put another lens in front. Then say, read now. Then you say, no, sir, I'm still not able. Then he'll put one more lens. Yes, sir, now I am able to read. That's the application of this. Put 1, 2 or 3 lenses and then make. Then at the end, when he gives you the lens, does he give you the 3 or 4 lenses or just one lens? One. So that is this one. Equivalent focal length. So how to find? 1 by F1, 1 by F2, 1 by F3. Okay. And here we also calculate the power, equivalent power. That is power of first, power of second, power of third. Keep on adding up to n. Next, lens with separation D. If you have got this lens and you have got this lens, separation between the lenses D. Okay. Focal length of this is F1, it is F2. And if somebody asks you how to find the equivalent focal length in this particular case, you say 1 by F equivalent is equal to 1 by F1 plus 1 by F2 minus D upon F1 into F2. D is the separation between the two. This is how you can find the equivalent focal length in this particular case. Okay. Shall we take the break? What's the time? Okay, guys, we are back. Let's start once again. Okay. Zarur. Now, guys, let's take a look exactly over here. We need to understand basically the simple microscope. Okay. I hope everybody has joined back. Okay. Okay. Now, guys, take a look exactly over here. When it comes to the optical instruments, in the optical instruments, we'll have to understand simple microscope. Okay. We'll have to understand compound microscope. Okay. And we will have to understand the telescope. We will have to understand the telescope. These are the three instruments that we need to learn in this particular case over here. Okay. I see. When it comes to the simple microscope, see, we say the simple microscope is the simple lens that you can see out there. Okay. Like, let's suppose I have a paper over here. There is mentioned on the paper, something is written on the paper in this particular case. Okay. And it is not visible. Whatever is written over here, it is very small. Then what do you do in order to see it? You bring that lens, simple lens, okay? And then you put between your eyes and that simple microscope and that paper. So put the lens. Now, this lens over here, this simple microscope over here magnifies whatever is mentioned on this paper so that you are able to see it. That's what we call the simple microscope. Okay. So simple microscope, the work of a simple microscope is to magnify the things, If there is a thing which is very small, you want to see it, you want to make it bigger, you will be using the simple microscope to make us see small things large, Okay. If you want to see an object with our normal eye, okay, it should be at least placed at 25 centimeters. That is called the least distance of distinct vision. One more point I'm mentioning over here. Guys, let's suppose there is an object over here. I'm saying that what is the minimum distance between your eyes and this object so that you are able to see it? So minimum distance should be 25 centimeters. Okay. That is called the least distance of distinct vision at which you can see. Now, what is the work of a simple microscope? Its work is to magnify the small things. Like anything is mentioned on the paper which you are not able to write, you will put the simple microscope in between your eyes and the paper so that it can magnify those words which are mentioned on the paper. Then you would be able to see those words. Okay. Now, in case of simple microscope, there are two cases we need to learn over here. Okay. What is that? First is image at infinity made by the lens or made by the simple microscope. Simply, you have got a lens over here. Okay. You have got a lens over here. And in this particular case, let's suppose you want to see this particular object. You want to magnify the object. So the work of the microscope is what? Its work is to magnify the things, to make the small things bigger. Okay, to make the small things bigger. Simply, if there are two cases we have to learn, in case of simple microscope also, in case of compound microscope also, in case of telescope also. First, image is made at infinity. Okay. Now guys, I would want you to understand in this particular case. See. Here, if I'm saying in this particular case, see this properly. If I'm saying in this particular case, if the image is made at infinity due to a simple microscope, its magnification will be d divided by f. Okay, d divided by f. Okay, and this d is the least distance of distinct vision. Least distance of distinct vision. As simple as that. Now guys, next, when it comes to the compound microscope, don't go in much depth, because if you want to learn this simple microscope and compound microscope in much detail, then you need to watch my ray optics lecture, which I don't want you guys to go at this point of time. Right now, whatever I am saying, just keep on focusing. Wait for some time, you'll get to understand everything. Okay, that is in the game of NEET 2.0. Now, image made by the microscope at distance d, least distance of distinct vision. Here, see. In the previous case, we said images at infinity. Okay, images made at infinity. Now, my dear friends, if this simple microscope is making the image at a distance d, in that particular case, magnification is going to be how much magnified this is going to do. In that particular case, that will be 1 plus d divided by f. 1 plus d divided by f. Okay, so this is going to be, this f is focal length over here. D is the least distance of distinct vision. So this is, so basically you are having the simple microscope. In simple microscope, you have two cases. The first case is images made at d. Second case is images made at images made at infinity, images made at d. At d, this will be the value of magnification. Like, this is the object placed over here. This is the lens in this particular case. Here is the image made. And you see, this image is magnified in this case. And it is placed at what distance? Image is made at least distance of distinct vision. Okay, this is the object, this will be the image. Image is magnified, and this is the magnification in this particular case. You can see exactly over here. Okay, now guys, let's move on to we say, and here, guys, you can clearly see in this particular case, when it comes to this object, these light rays are meeting over here. These are the reflected rays. Okay, these are the refracted rays over here. And in this particular case, I can clearly say, sir, in this particular case, you have got this object, you have got this image. Okay, but here the light rays are parallel. So they will never meet. They will meet at infinity. That's why we say in this case, image will be made at infinity. So the object, in this case, light rays are parallel. So we say they will meet at infinity, image will be made at infinity. Here, image will be made at distance d, least distance of distinct vision. This is the magnification, how magnified the image is, and over there, that is d by f. Here it is 1 plus d by f. Now you have the compound microscope. Compound microscope is that microscope that you might have seen in the schools. Okay, that you might have seen in the schools. See, in case of compound microscope, you have got two lenses. This is the first lens and this is the second lens. This is what we call the objective. This is called objective and this is called the eyepiece. This is the objective and this is the eyepiece. Now guys, if you have an object which is placed in front of objective, if you have an object which is placed in front of the objective, okay, you want to magnify it. Guys, in this case, we say two magnifications will take place. This will also magnify it and this will also magnify it. I'll not go in the detail. Like, you have the light rays first, okay, after refraction they will meet exactly over here. See, this is magnified. Okay, this is the first image. Second image, we say then the light rays will go something like this and they will meet at infinity. Okay, so final image will be made at infinity in this case. So my dear friends, what I'm trying to say here, if you have a compound microscope, two stages of magnification happens over here. This also magnifies the object. Okay, if we want to further magnify it, this also magnifies the object. Case 1 in this case is, what is the first case? That object image made at infinity. Case 1, image made at infinity. Image made at infinity. Guys, like in case of simple microscope, you said, sir, here you are putting the lens between your eye and the object. This is the lens, this is your eye, this is the object. Now, sir, you want to magnify this object, but image is made at infinity. The light rays will go parallel. So parallel light rays, we say, meet at infinity. So image made at infinity. Magnification is d divided by f. Then you said the next case, sir. When the image is made at distance d, here image is made at distance d. In this case, magnification is 1 plus d by f. Then you said, sir, compound microscope. In case of compound microscope, you have two lenses. Objective, eyepiece. Sir, this is a good microscope. So 2 stages of magnification takes place. This will also magnify. This will also magnify. Okay. And when it comes to the total magnification here, that is magnification total will be magnification due to the objective lens, magnification due to the eyepiece. Okay. So you multiply these two simply. Now, guys, when it comes to the objective lens, you can say its magnification is V0 divided by U0. Okay. And this is d divided by f. Eyepiece is simply d divided by f. This is the magnification when image is made at infinity, when final image is made at infinity. This is the final magnification. Okay. Okay. I hope this is crystalline clear. And V0, U0, V0 is the position of the image. Position of the image from the objective. Position of the object from the objective. Okay. From this, you guys can exactly see. This is the object. This is U0. This is the first image. This is U0. This is V0. Okay. This is the focal length of this lens, eyepiece. And of this focal length of this is focal length of objective. Simply, you guys will remember over here, this is the magnification in case of compound microscope, because only we have to see how much magnification it will do. Then we say tube length in this particular case. Tube length will be this distance between this and this. How much is the tube length? That will be this plus this. You guys can clearly see that is V0 plus Fe. Okay, so it is till here. So this distance plus this distance, this is going to be the tube length in this particular case. Okay, okay. Next case, guys, the second case here is, if we want to magnify the final image at distance d. Previous case, we were making the final image at infinity. Now we are making the final image at distance d. If, my dear friends, this is the objective, this is the eyepiece. Okay. Now, guys, this is the object placed over here. Light rays will leave from the object. So first they will meet exactly at this point. So image will be formed. You see, this is the first image and this lens has magnified the first image. H dash is the first image. Then I can say light rays will leave and they will go something like this. They will go something like this. If you extend these, they will meet at this point. Now see, this is the final image. H double dash is the final image. You see, final image is magnified. And this final image is at distance d, capital D. So that's what I'm saying. Final image is as distance d. Now if somebody says, what is the magnification over here? Guys. It is magnification due to objective, magnification due to eyepiece. So this is V0 by U0. Okay. So 1 plus d by f. This is the magnification due to objective. This is the magnification due to eyepiece. Because eyepiece is simply this is simply whatever was the magnification over there in case of simple microscope. Okay. As simple as that. As simple as that. So this is going to be the magnification due to a compound microscope if the final image is made at distance d, if the final image is made at distance d. And when the final image is at infinity, like guys, here this is the light ray, it is going something like this, and then these light rays become parallel over here, so they will meet at infinity. That's why we say final image is at infinity. Now let's take a look at the question. So only two things you have to remember. In case of compound microscope, if the final image is made at infinity, then magnification is going to be V0 by U0 d by f. Here magnification is going to be V0 by U0 1 plus d by f. Now take a look here. Take a look here. Question is saying a compound microscope has an eyepiece of focal length. A compound microscope has an eyepiece of focal length 10 centimeter. Okay. So FE is given as 10 centimeters. Okay. And an objective of focal length 4 centimeters. FO is given as 4 centimeters. Calculate the magnification if the object is kept at a distance of 5 centimeter. U is given as 5 centimeters. Okay. So basically, object is placed at a distance of U0. U0 is given as 5 centimeter. So U0 is given as 5 centimeter. From the objective, that's why it is U0. So that the final image is made at the least distance of distinct vision. Final image made at distance D. Now tell me guys, if the final image is made at distance D, what is going to be the magnification? V0 by U0, 1 plus D by F. 1 plus D by F, and this is FE over here, focal length of eyepiece. So I can say here magnification is going to be V0 divided by U0, 1 plus D divided by FE. This is going to be the magnification in this particular case. Simple as that, as simple as that. Just put up the values in this particular case and get the answer. Okay. Okay. Now guys, first and the foremost thing in this case is D is given as 20, FE is also given over here. That is 10. V0 is also, U0 is also given, V0 we are supposed to find out. It is like you have an objective, okay? And in front of the objective, you are placing an object which is placed at U0 is equal to 5 centimeters. And my dear friends, this will be the direction of incident rays, okay? And this is positive side, and this will be over here, negative side. Now, if you want to calculate where will be the image formed, first image will be where formed. How do we calculate? From the lens maker's formula, you take the equation. From the lens maker's formula, it is like the question of lens. Like over here. 1 by V minus 1 by U is equal to 1 by F. Same formula you need to use over here. Okay. That is 1 by V minus 1 by U is equal to 1 by F. Take it over there. 1 by V is equal to 1 by F minus 1 by U. Do the cross multiply. So you guys will say 1 by V is equal to, that is U minus F, this is plus U plus F upon U into F. So V will come out to be U into F upon U plus F. Okay. Okay. Now guys, this is the value of V in this particular case. Now, how do we calculate this V? So V is going to be in this particular case. What is the value of U? U in this case is given as minus 5. Okay. And focal length of this will be also minus 4 divided by, we say 5 minus 5, we say minus 4. Okay. Because focal length in this particular case is going to be, this is U and U into 5, U into this. Okay. Now guys, tell me in this particular case, what is going to be the answer? So this minus 5 minus 4, U in this case is minus 5 minus 4. Okay. So V will come out to be minus 20. Okay. That will be minus 9, 20 by 9. It should come out to be 20 minus 5 plus, minus into minus is plus. Okay. Yes, 20. Okay. I am supposed to take this is positive. This is positive. Okay, 5 into 4. This is 5 plus 4. So V will come out with 5, 4 minus 20. This will be minus 1, so it will be 20 centimeters. Okay, when you get the value of V naught as 20 centimeters in this particular case, then what are you supposed to do? Now put the values in this case over here. So you will write in this case, what is the value of V naught? That is 20 divided by, this is coming out to be 5. V naught is 5. 1 plus D divided by F. D is given as 20 and focal length of eyepiece is given in this particular case. Okay. So this is 5 ones are 4s are. Okay, 4 into, this is 10 plus 20 is 30 divided by 10. Okay, so this comes out to be equal to 12. So 12 is the correct answer. Okay. So simply in this particular case, you were supposed to find first what? The value of V. When you calculated the value of V, okay, V naught, you got V naught. From V naught, you can put it into over here and then you can calculate the magnification. Simply. Now guys, you have the telescope. If someone asks you, where do we exactly use this telescope? If someone asks you, where do we use this telescope actually? We say, it is used to magnify the objects placed at the large distances. Like you have an object which is, where do we use the telescope? To see the stars, to see the moon, okay? To see the objects which are placed at very far distance. So we say, for that only we use the telescope. So it is used to magnify the objects placed at very large distances. Now, we say in telescope, objective lens is large and eyepiece is small. You guys can see over here, this is the telescope. Just the opposite of compound microscope. Here we place objective lens as large. Why? Because the light rays are coming from infinity. So if we catch more, if we place the objective bigger, we say we can catch more light rays in that particular case. Now, if we catch more light rays in that particular case, intensity, clarity of the image will be good. So that's why we are placing the objective lens large over here. Okay. Like it is mentioned, in telescope, objective lens is large and eyepiece is small. And the lens facing the object is objective and it has a large aperture and focal length. Okay. And the other lens through which the image is observed is called the eyepiece. Other lens through which the image is observed is called the eyepiece. Okay. So this is the eyepiece through which the image is observed. Final image. Like you might have seen the telescope. From the front side, lens is bigger. From the back side, that is smaller lens through which we see. That is the eyepiece. This is the objective. Okay. In this particular case, my dear friends, we say final image is made at infinity. Case 1 is final image is made at infinity. And what is case 2? Final image is made at distance d. I would want you guys to directly remember. Light rays are coming, they're meeting over here. Okay. These light rays meet over here. So this is the image produced. Okay. H dash is the first image. Then light rays will leave from this H dash and they will go parallelly. So we say final image is made at distance d. Sorry, final image is made at infinity. Now guys, I want you to understand this. If final image in case of telescope is made at infinity, if final image in case of this is made at infinity, and somebody asks you what is the value of magnification, magnification is minus FO by FE. Focal length of objective, focal length of eyepiece. Focal length of objective, focal length of eyepiece. And tube length over here, that will be FE plus FO. FE plus FO. As simple as that. Now, second case here is, case 2 here is, in case of the telescope, if final image is made at distance d, if final image is made at distance d, I want you to understand this. So these are the light rays, okay? They are basically converging at this point. This is the first image. Then the light rays will leave from this first image. We say they will converge. If we extend these, it appears to meet here. So this will be the final image. And final image is made at distance d. This is the distance d. This is the final image. Okay? And when final image is made at distance d, somebody asks you, what is going to be the magnification in this particular case? That is FO divided by FE, 1 plus FE divided by D. This is the final image. This is the magnification when final image is made at distance d. One more important relation you need to remember over here. In this particular case, the tube length, distance between the two lenses. What do you think? Don't you think it is going to be this FO and this UE? Okay, this plus this. Okay, this plus this. Now, my dear friends, this distance plus this distance. And similarly, I'm just writing over here. And this is what UE means, position of the object from the eyepiece, And how you can calculate this? Guys, FO plus FE will be the tube length. And this tube length is going to be FO plus. How you can calculate this UE? Sir, UE I can use 1 by V minus 1 by U is equal to 1 by F. So from this formula, I'll get U is equal to V into F, V plus FE. Just put it over here. This will be the tube length. That's it. Let me summarize it. When it comes to the simple microscope, it is that instrument which is used to magnify the small things. Now, final image is made at 2 points. First is infinity, second is distance d. If final image is made at distance d, in that case, magnification, where is the simple microscope? In that case, magnification is going to be d by f. Okay? If final image is made at distance d, like here, magnification is going to be 1 plus d by f, where f is the focal length of this lens. D is the least distance of distinct vision. Then, compound microscope. Sir, compound microscope is a good microscope and it has got two lenses, objective and eyepiece. Two stages of magnification takes place. This also magnifies the object, this also magnifies the object. Sir, here, if final image is made at infinity, then magnification will be equal to V0 by U0, D divided by F. Sir, V0 is the position of the image from objective. Position of the object from objective. Okay? Okay? And F in this case is the focal length of eyepiece. D is the least distance of distinct vision. Then, if the final image is made at distance D, in that particular case, magnification will be V0 by U0, 1 plus D by FE. That's it. Sir, in case of telescope, we say, sir, it is that device which is used to see the objects which are placed at a very large distance. And sir, in case of telescope, you have got the objective lens which is bigger, because so that large amount of light rays enter the lens. And here eyepiece which is smaller, and here through the eyepiece you see the object's final image. Now, final image, if it is made at distance, if it is made at infinity, then magnification in that case is going to be FO minus FO by FE. And tube length is going to be FO plus FE, like this distance plus this distance. And then, my dear friends, one more thing. If final image is made at distance D, in that particular case, tube length is going to be FO, D plus D into FE, D plus FE. And here, final magnification, if image is made at distance D, minus FO by FE into 1 plus FE divided by D. FO is the focal length of objective, focal length of eyepiece, least distance of distinct vision. I hope this is crystalline clear. Let me know in the chats if this is crystalline clear, guys. Tell me quickly. Quickly in the chats, quickly in the chats. I would want you guys to give me the signal in the chats if it is clear. That's great. The magnifying power of a telescope is 9. Magnifying power of a telescope is 9. When it is adjusted for the parallel rays, the distance between the objective and the eyepiece, so FO plus FE, okay, this is found out to be 20 centimeters. Okay, that is the tube length. We know in case of a simple microscope, if the final image is made at infinity, tube length is FO plus FE. Magnification is FO divided by FE. FO divided by FE. Okay. We say as magnification is FO divided by FE. This is given as 9 is equal to FO divided by FE. And from this, FO is equal to 9 times of FE. Now guys, put it over here. Put it over here. So this is 9 times of FE plus FE is equal to 20 centimeters. Okay. Now this is 10 FE is equal to 20. Ones are, twos are. So FE is coming out to be 2 centimeters. So focal length of eyepiece is 2 centimeters. If focal length of eyepiece is coming out to be 2 centimeters, what about the focal length of objective? So you will say FO plus 2 is equal to 20 centimeters. Okay. Now here FO is going to be 20 minus 2, that is 18 centimeters. This is what we are supposed to find. The focal length of the lenses are. Now guys, you guys can solve the questions on this optical instruments, okay? Because I have shown you every single formula. Let's move on to the next chapter as of now. That is wave optics. Okay, we are done with the ray optics. Let's move on to the wave optics. Let's move on to the wave optics. Guys, understand very carefully when it comes to the chapter wave optics. In case of ray optics, I told you the simple thing. In case of ray optics, I told you the simple thing. What is that? That is, when it comes to the ray optics, I told you here we consider light as a ray. Okay. But when it comes to the wave optics, ray means straight line. In case of ray optics, we consider light as a wave. Why, sir? Because see, and in modern physics, like dual nature of matter and radiations, we consider light as a particle, like photon. So my dear friends, in wave optics, we consider light as a wave. So means if I am saying this is a light source over here, light is coming out of the light source. So you'll be saying, sir, these are the waves coming out of the light source. These are the waves coming out of the light source. Okay. These are the waves coming out of the light source. If I say this is a light source, light is coming out of this light source in ray optics. So you say straight line, light ray. And in modern physics, these are the particles. Now, since we started the wave optics, we'll be considering the light as a wave, because we say light has got dual nature, particle nature as well as wave nature. So right now we are studying the wave nature of the light. Okay. Wave nature of the light. Now guys, understand one thing very carefully. If we have to study this wave nature of the light, so there was the first scientist, the name of the scientist physicist was Huygens. He came up with the wave theory of light. He said light is a wave. Then how he presented, basically he said light is a wave. Light is a wave. Even he said light is a mechanical wave, but light is an electromagnetic wave. So Huygens' principle, basically, Huygens was a physicist. He said light is not a particle, light is a wave. And then people asked him, what is the proof? He came up with the principle. That's what we need to understand. Okay. So let's now understand the wave nature of light. See guys, let's suppose you have got a tank over here. This is the tank. Okay. Now this water droplets are falling into the into this tank. What will happen? Side view. You guys will say, sir, these kind of waves are produced over here. These waves are being produced over here whenever the droplet falls. So waves are being produced over here. If you see from the top view, this is the water droplet falling. So these are the waves which are being produced over here. Yes. Okay. This one, this is what we call the source particle. Source particle, which creates the wave, which disturbs the neighboring particles. This is called the source particle. Now guys, what does Huygens say? Understand this very carefully. Can I say in this case? In this case, like over here, Huygens said, like over here, when the water droplet is falling into the water, it is creating these waves. These waves are what we call the wave fronts. These waves are called the wave fronts. He said, like when the water droplet falls, wave fronts are being created. Same happens, same as in case of the light source or the bulb. If you light the bulb over here, similarly the light waves or the wave fronts will go out. These are what we call the wave fronts. These are what we call the wave fronts. Okay. He said if you light a bulb over here, okay, in this case also the wave fronts will come out. In this case also the wave fronts will come out. Okay, this is a bulb. Exactly like this. Okay. So basically these are what we call the wave fronts. How does it exactly happen? See, when the source particle falls into the water, it disturbs the neighboring particles. It gives the energy to the neighboring particles. Like here, in this case, when the source particle falls, it disturbs the neighboring particles. It disturbs the neighboring particles. Then they start lifting in the upward direction. Okay, then they start vibrating. Now, if you join these with a common tangent, this forms the wave front. This forms the wave front. Okay. Similarly, now this particle will also disturb its neighboring particles. Okay. This particle will disturb its neighboring particles. Okay. Now they form the secondary wave front. Okay. Like here. This is the primary source particle. It disturbs the neighboring particles. The neighboring particle will disturb its own neighboring particles. Okay. Now if you join these with a common tangent, they form the secondary wave front. This is the secondary wave front. Okay. And this one is the first primary wave front. And these are also called the secondary wavelets. These. Okay. The source particle disturbs the neighboring particles when they are joined together with a common tangent. It forms the wave front. The secondary wavelets, these secondary wavelets, okay, will further disturb their neighboring particles, and produces the another wave front, This is called the Huygens principle. Okay. So what did Huygens say? How this wave is being produced? A source particle disturbs the neighboring particles. The neighboring particle disturbs their own neighboring particles. If you join them with a common tangent,
It forms the wavefront. It forms the wavefront. This will be called the primary wavefront. This is called a secondary wavefront. That's it. This is the Huygens principle. Now, guys, you have over here path difference. Path difference. You have over here the path difference. You have over here the path difference. You have over here the path difference. Now, guys, understand one thing very carefully. Okay, one more thing I just want to tell you over here. What is that? Huygens also mentioned few of the points, not in this principle, but he also said some of the points. He said, like, if you take a surface, if there is a light source over here, if light is coming out of the light source, you show these light sources with the help of a wave. These are the wave fronts falling on this. These are the wave fronts falling. So now we know reflection of light takes place. So now this light will be reflected. When it comes to the ray optics, we were showing it with the help of a straight line. But here wave optics, Huygens said, show it with the help of wave fronts. So these are the wave fronts falling, wave fronts reflecting. Similarly, if we talk about the refraction, these are the wave fronts falling and these are the wave fronts getting reflected. This is the refraction, this is the he said we can prove this law of refraction and reflection with the help of this also. With the help of considering light as a wave. Now, guys, let's move on to path difference. Let's move on to the path difference. See, guys, if let's suppose this is the point A, let's suppose this is the point B over here. This is the point B. Okay, this is the point B. This is the point B. Guys, let's suppose this wave has traveled 5 kilometers. This wave has traveled, let's suppose, 10 kilometers. Could you please tell me how much is the difference in their path? You say, sir, path difference will be 10 minus 5, that is 5. This has traveled 10 kilometers, this has traveled 5 kilometers, so 10 minus 5 is 5. This will be the difference in their path. Yes. Then you have phase difference. What does phase difference actually mean? See, guys, path difference is simply difference in their path. When it comes to the phase difference, see, guys, let's suppose this is a wave, yellow wave, this is a blue wave. In this case, both are starting from 0. Okay, both are reaching the maximum at the same time, when this is maximum, this is maximum. Then when this yellow is 0, this is also minimum. So both are minimum, negative extreme from this side, negative extreme, 0, 0. So we say in this particular case, the two waves are in phase. Here, they have got the phase difference, delta phi is equal to 0. So the two waves are in phase. This is how we define the phase. Like here, phase difference, guys, when this blue wave is at 0, yellow is at maximum. So phase difference in this case is delta phi, in this case is pi by 2. Why? Because when yellow wave is 0, blue is maximum. When blue is 0, yellow is maximum from the negative extreme. So in this particular case, phase difference is pi by 2. Like here. When this is at extreme from one side, from the positive side, this is from the negative side. So we say here phase difference is 180 degrees. In this particular case, phase difference is 180 degrees. This is how we define the phase difference of the two waves. Now, see, one more important point. Constructive and destructive interference. What does it mean? Guys, let's suppose there are two waves. These are the two waves meeting. I'm saying this is the wave. This is called the crust, this is called the trough. Okay, my dear friends, when crust of two waves meet, the amplitude becomes large. The amplitude becomes large. See, this is it is like this. It is like this. Two waves. So crust of two waves are meeting at a point. When crust of two waves meet at a point, its amplitude. Amplitude means how much is this? How much is this? Okay. And how extreme it can go. So we say in this particular case, its amplitude becomes large, that is 2a. And this is what we call the constructive interference. I'll give you the feel also of this one. As of now, when crust of two waves meet, their amplitude becomes large. Okay, its amplitude, net amplitude is a plus a, that is 2a. Okay, so they have got the zero phase difference. They have got the zero phase difference. Because when this is maximum, this is maximum. So that's why they are having the constructive phase, constructive interference. Like you have this wave, you have this wave. If these two waves meet, when this is at maximum, this is at maximum. When this is at minimum, this is at minimum. So we say in this particular case, resultant amplitude will increase. So constructive interference will take place between these two waves. If these two waves meet, why? Because here phase difference is how much? 0. Because here phase difference is 0. So that's why constructive interference will take place. So two waves constructively meet if the phase difference is 0. Next, when crust and trough of a wave meets, then amplitude becomes 0. Crust of one wave, trough of another wave. We say amplitude here is 0. We say A net in this particular case is 0. Straight line. Okay. This is called destructive interference. This is called destructive interference. So what is constructive interference? Constructive interference means when you have two waves, the crust of the two waves meet, amplitude becomes large, and it is called the constructive interference. When crust of one wave meets the trough of another wave, it is called destructive interference. And here, amplitude becomes 0. Now guys, you have got these two. In this particular case, what is the phase difference between the two? That is 180 degrees. So when phase difference is 180 degrees or pi, we say destructive interference will take place. And what is the resultant amplitude? Resultant amplitude in this case is 0. Okay, because crust is meeting trough. Crust is meeting trough. Now guys, you will get the more feel. You will get the more feel. Wait for some time. Let's suppose we have got the two waves. Y1 is equal to A1 sine omega t. Y2 is equal to A2 sine omega t cos phi. As of now, you just remember this is the wave. This is the wave. Okay. This is the equation of the wave. How do we write the equation of the wave? A sine omega t. A is the amplitude, angular frequency, time. Okay. Now guys, you can represent the amplitude of these two waves on a phasor diagram. Phasor diagram means amplitude of A, you can represent it with an arrow like this. Amplitude of this wave you can represent with an arrow. Okay. And you can see difference between the two is phi. Here phi is 0, here it is phi. So that's why angle between this difference, phase difference between the two is phi. Okay. If you have a wave, its amplitude is A2. If you have a wave, its amplitude is A1. If you want to find the resultant amplitude, it is like the vector sum. This is A net. It is like the vector sum. How do you find? Sir, A net square will be equal to A1 square plus A2 square plus twice A1 A2 cos phi. Twice A2 A1 A2 cos phi. This is how you can find the resultant amplitude. So what I'm trying to say, you have got two waves. Now you are representing their amplitude with an arrow. You want to find the resultant amplitude. This is how you can find. Now, this will give you the feel. Let's suppose two waves are meeting constructively. Two waves can only do the constructive interference when phi is 0. Okay, when phi is 0, that's what I told you. Now tell me, what is the resultant amplitude in that case? Sir, A net square is equal to A1 square plus A2 square plus twice A1, A2 cos of 0. Okay, because then only constructive interference will take place. Now, you can say in this particular case, A net square will be equals to A1 square plus A2 square twice plus 2 times A1, A2 cos phi. Tell me guys one thing. Tell me guys one thing. In this case, A1, guys, cos phi, cos 0 is 1. So this will be A1 square plus A2 square plus 2 times A1, A2. Don't you think it is A plus B whole square? Yes. So I can say A net square in this case will be A1 plus A2 and this is whole square. A1 plus A2 whole square. Now guys, this square goes. So in this case, A net will be simply that is A1 plus A2. That's what I was saying. This is the proof. If the two waves are meeting constructively, then we say net amplitude is increasing. Now, if somebody says, if A1 is equal to A2 is equal to A, what will be the net amplitude in that case? You say net amplitude is A plus A, that will be 2A. Okay, like if two waves are meeting destructively, there are two waves which are doing destructive interference. What does that mean? Phi is equal to 180 degree. Now in this case, what will be the net amplitude? So that is A1 square plus A2 square plus 2 times A1, A2 cos of pi. And guys, in this particular case, you can say, what is this A1? A1 is the amplitude of first wave. Okay, so this is A1 square plus A2 square plus, and instead of plus I write cos pi is minus 1. So minus 2 times A1, A2. Guys, this is A minus B whole square. So can I not write over here A net square will be, this is A1 minus we can say A2 whole square. This and this goes. In this case, A net will come out to be A1 minus A2. So if two waves are meeting destructively, their net amplitude will be A1 minus A2. Now if I say if A1 is equal to A2 is equal to A, can I say in that particular case, net amplitude will come out to be A minus A, that will be 0. Yes. Now, let's talk about the end. So as of now, I told you, if the two waves are meeting, they are doing the constructive interference. Okay. Then in that particular case, resultant amplitude increases. And cos phi in case of constructive interference is 0. If two waves are meeting, they are doing destructive interference. Cos phi in that case is 180. Now intensity. What is intensity? Intensity is simply power upon area. Power upon area. Or you say energy upon time into area. Power means energy upon time into area. Like you have got, you say bulb. This is a bulb. So the intensity of the bulb is large. What does that mean? How much power it is giving. What is power? Power is how much energy, light energy it is giving. If it is giving large light energy, power will be more, intensity will be more. As simple as that. Now see. Mathematically, we say intensity is proportional to amplitude square. Okay? Intensity is proportional to amplitude square. Now guys, wherever you see intensity I, you replace it with the A square. You replace it with the A square. Okay. Take a look. Here. We say as, can I say A net square is equal to A1 square plus A2 square plus 2 times A1, A2 cos of phi. Now, if we have to write the formula for the intensity from this equation, how can we write? Replace A square with I. I net is equal to I1 plus I2 plus 2 times. Instead of A, guys, we say A square is equal to I. Can I write A will be equals to, take this over here, root of I? Yes. So instead of A, I can write root of I1. This will be root of I2 and this is cos of phi. Now, this will be the formula of intensity. This will be the formula of intensity. Now, if constructive interference is taking place, okay, if constructive interference is taking place, look at this, see, okay, if constructive interference is taking place, what is the value of phi? 0. What's the value of cos phi? 1. I net will be I1 plus I2 plus 2 times of I1, I2 cos 0. That is 1. So it will be 1 over here. Now. Can you write this as root I1 plus root I2 whole square? If you open this up, you'll get this. If you open this up, a square plus b square plus 2ab, you'll get this. Okay? This is what we call the maximum intensity. For constructive interference, phi is 0. Intensity will be maximum. Maximum intensity will be equal to root I1 plus root I2 whole square. If I1 is equal to I2 is equal to I0, if the intensity of the two waves is same, then we say this will be root I0 plus root I0. This will be twice root I0 whole square. This will be 4 I0. So maximum intensity will be 4 times of I0. Many times this question has been asked. Next, for destructive interference, take a look. We say theta is equal to 180 degrees. Cool. Cos phi is equal to 1. What is the formula? I net is equal to I1 plus I2 minus 2 times I1. It is basically plus 2 is I1, I2, root I1, I2 cos phi. Cos phi is minus 1. That's why I got minus 1 over here. Now, instead of this, you can write this. Root I1 minus root I2 whole square. Because if you open this up, you will be getting this. A square minus b square, a square plus b square minus 2ab. You'll be getting this. Done. This is called the minimum intensity. Okay, this is called the minimum intensity. Now, by any chance, if I say I1 is equal to I2 is equal to I0, if the intensity of both the waves is same, then put it over here. Intensity net will come out to be 0. Net intensity will come out to be 0. Okay, now one more thing. When it comes to the maximum intensity, that is root I1 plus I2 whole square. When it comes to the minimum intensity, that is root of I1 minus root of I2 whole square. This is the ratio. Remember it, very important. Next. Okay, first let me talk about this question. See guys, two beams of light having the intensities I and 4i. This is the light, it is having the intensity I and 4i. Interfere to produce a fringe pattern on the screen. The phase difference between them is pi by 2 at a point A. Okay, guys, this is the wave. Let's suppose it is falling at this point. Okay, and this is another wave. It is falling at this point. Produce a fringe pattern on the screen. The phase difference between them is pi by 2 at point A. This is point A. So when these two waves are meeting at point A, phase difference is coming out to be 0.2. And what is the value of this? I, and this is 4i. Then it says that you have got same two waves when meet at point B. This is point B. Phase difference is coming out to be 2 pi. Phase difference is coming out to be 2 pi. Then find out the resultant difference between their resultant phase difference. Guys, see, let's find the resultant here. We say I1 will be equals to, how do we find? This is I1 plus I2 is equal, this is I net. Okay, then you say plus 2 times root I1 root I2, we say cos of pi by 2, that is cos 90. This will become 0 because pi by 2. Okay, and now what is the value of I1? This is I plus this is 4I plus 2 times of this will be a root of I, root of 4I. Okay. Okay. And this will become 0. This will become cos of pi by 2. This will become 0. This is the intensity at point A. So this will become 5. This will come out to be 5I. This is IA. Similarly, using the same formula here, this is I, this is I. In this particular case, if you use this particular formula, I net is equal to, what will you say? I plus 4I plus 2 times of root I, root 4I, and then you say cos of 2 pi, cos 360 minus 1. This will come out to be 9I. This is the intensity, net intensity at B. This is the net intensity at A. We are supposed to find the difference between these two. So IB minus IA will come out to be 9I minus 5I, which will be 4I. This is the answer. The same question. Okay. Two coherent sources, each emitting the intensity I naught, interfere in a medium at a point, where phase difference is coming out to be pi by 3. Phase difference is 2 pi by 3. Okay. And intensity of first wave, I1 is given as I naught, intensity of I2 is given as I naught. What will be the resultant intensity? Simple formula based. You guys are supposed to do it from your own. Simple formula based. Next, tell me about this one. Two sinusoidal waves of intensity I having same frequency, same amplitude interferes constructively at a point. The resultant intensity will be 4I. Why? Why? Guys, I can say when the two waves, look at this. When the two waves interfere constructively, what is the resultant intensity? Root I1 plus root I2 whole square. Okay. Then if I1 is equal to I2 is equal to I naught, then resultant intensity 4I naught. So this is the formula. Okay. And you can put it over here. I net I max is equal to under root of I1 plus root I2, this whole square. Now put up, this is root I plus root I whole square. This is 2 times root I whole square. That will be 4I. Now guys, as of now, I have told you constructive interference and destructive interference. Sir, you said constructive interference takes place when theta is equal to 0 degrees. Destructive interference takes place when phi is equal to 180 degrees, and here when phi is equal to 0 degrees. Okay. Sir, will this constructive and destructive interference take place at these points only? Will this constructive and destructive interference take place at these phase differences only? No. There is a general formula. Guys, see what the general formula is. Let's see where does the constructive interference takes place. Guys, for constructive interface phases, okay, in general, we say phi is equal to 2n pi. So whenever the value of phi is 2n pi, the constructive interference will take place, where n is 0, 1, 2, 3, 4, and so on. If you put the value of n is 0, phi will become 0. So add phi is equal to 0, constructive interference take place. If you put the value of phi is 1, so constructive interference, so this will come out to be 2 pi. This will be 2 pi. If you put the value of n is 2, 2 into 2 is 4, so this will be 4 pi. So at all of these values, if the two waves are meeting at a point, they are producing the phase difference of 2 pi, 4 pi, means constructive interference will take place. Similarly, in case of destructive interference, okay, what is the general formula? That is 2n minus 1 into pi. N is 1, 2, 3, 4, and previously it was 0, 1, 2, 3, 4. It is n 1, 2, 3, 4. Now, guys, if you put n is equal to 1, 2 into 1 is 2, 2 minus 1 is 1. So that is pi. So at theta is equal to pi, pi means 180. So destructive interference will take place. If you put n is equal to 2, 2 into 2 is 4, 4 minus 1 is 3, so 3 pi. At 3 pi, destructive interference take place. If you put n is equal to 3, 5 into 3 is 15. Okay, sorry. 2 into 3 is 6, 6 minus 1 is 5, 5 pi, 7 pi. So at all these phase differences, destructive interference will take place. Okay, one more thing. Guys, part difference and phase difference. Part difference in case of constructive and destructive interference. Let's suppose there are two waves which are meeting at this point. Constructive interference is taking place. What will be the value of phi? 2n pi. Now, if I say, what will be the value of path difference, not the phase difference? Part difference will be n lambda. Part difference will be, if I am saying the two waves are meeting at this point, how much is the part difference if they are meeting constructively? So that is n lambda. Okay. Okay. And in this particular case, we can say n is equal to 0, 1, 2, 3, 4, and so on. So 0, if part difference is 0, constructive interference taking place. Lambda, constructive interference. 2 lambda, constructive interference. Similarly, if two waves are meeting at a point and destructive interference will take place, then path difference in that case will be this: 2n minus 1 lambda by 2. If you put n is equal to 1, so 2 into n, 2 into 1 is 2, 2 minus 1 is 1, so lambda by 2. So at lambda by 2, when there is part difference, lambda by 2, destructive interference will take place. When n is equal to 2 into 2 is 4, 4 minus 1 is 3, 3 lambda by 2, 5 lambda by 2. So at all these values of part difference, destructive interference takes. Now, let's move on to the YDSC. Young's double slit experiment. Young's double slit experiment. Now, guys, see, Young's double slit experiment. What does Young's double slit experiment exactly mean? See, guys, YDSC, Young was basically a scientist, physicist. He performed an experiment. That's called Young's double slit experiment. This experiment was performed so that it could prove the wave nature of light. It proved the wave nature of light. It is mentioned over here. Like. He took basically a sheet over here. Okay. Let's suppose this is a source. This is a source. What source? Light source. Okay. Then he placed a big sheet over here. Okay. Then he draw two slits. Okay. Cut the sheet something like this. This is the top view. Don't say it's a hole. It's not a hole. It's a slit. Cut it very narrow slit, thin narrow slit. Okay. Now the light is coming and it is crossing through these slits. Okay. He said, if the light is a particle, okay, guys, understand, then this light should pass through these narrow slits and it should fall there. This is the screen. This is the screen. And it should fall on the screen. Only this part should glow. Only this part should glow. Because if you throw a particle, it cannot follow this path. It can go a direct path. It can follow the direct path. Similarly, the light which passes through this slit, through this narrow slit, it falls at this point of the screen, Okay. So only these two portions of the screen should glow. But this doesn't happen. What happens is when the light passed through these narrow slits, we got this bright dark pattern. This is called the bright fringe. Bright fringe. And this is called the dark fringe. Bright fringe, dark fringe, bright fringe, dark fringe. Okay. Yes. We got bright dark pattern. And this is what we call the central bright. Central bright. Okay. So this clearly, this production of fringes, this production of fringes is called production of fringes proves light is a wave, because for a particle it is not possible to deviate its path and fall over here. No. So when we consider the light as a wave, then only we say these fringe patterns are made. So this is called the Young's double slit experiment, production of these fringes, or we also call this as maxima, central bright, or we say maxima. And this is also this is called minima. Either you call it the dark fringe or the minima, it's one and the same thing. Okay. Now guys, take a look. In this particular case, guys, see, let me show you over here. We say this maxima is formed. I'll just write maxima is formed due to the constructive interference of two waves. Maxima is formed due to the constructive interference of two waves. Okay. And minima is formed due to the destructive interference of two waves. So we said this maxima is formed due to the constructive. When the two waves constructively interfere over here, then only maxima is formed. Destructive interference because of the minima, because of the destructive interference. Now guys, in this particular case, this central bright fringe, let's suppose a wave is falling at this point, another wave is falling at this point. Don't you think that these two waves have traveled the same distance at the central point? So here path difference will be 0. So when path difference is 0, that is what we call the central maxima. Okay, because we have already discussed, in case of constructive interference, path difference can be 0, lambda, 2 lambda, 3 lambda, 4 lambda. Now take a look. I don't have to explain it again. So when path difference is 0, path difference is lambda, 2 lambda, okay, 3 lambda, we say maximas will be formed. Okay. Now guys, when it comes to the destructive interference, come over here. When path difference is lambda by 2, 3 lambda by 2, 5 lambda by 2, we say destructive interference will take place. When path difference is lambda by 2, it is first minima. When path difference is 3 lambda by 2, it is second minima. 5 lambda by 2, third minima. So here, guys, this will be the central maxima. This is the first minima. After central maxima, it is first minima. Then this is the first maxima. Then second minima. Second maxima. third minima, third maxima. Similarly from the lower side also. This is how do we define it. And this is the path difference in case of maximas and minimas, already discussed. I hope there is no problem in this one. So maximas are formed at when delta x is equal to 0, lambda, 2 lambda, 3 lambda, so on. General formula is L lambda. Minimas are formed when delta x is equal to lambda by 2, 3 lambda by 2, 5 lambda by 2. General formula is 2n minus 1 lambda by 2. Okay. Distance at which the maximas and minimas are formed. Guys, see. Let's suppose this is the central maxima over here. Okay. I'm saying let's suppose at this point a fringe is formed. Okay. At this point the fringe is formed. Sir, which fringe? Bright or dark? Anything. Anything. Okay. And how much will be this distance from the central maxima? This is y. This y you can calculate delta x d by d. What is delta x? Path difference d by d. This is the distance at which the fringe will be made from the maxima. This is the distance at which fringes are made from central maxima. From central maxima. Like. The question is, find the distance of fifth maxima from the central maxima. What is the formula? Y is equal to delta x d by d. Delta x d divided by d. Now it is asking for the minima. So, what is the path difference for the minima? Guys, what is the general formula for the path difference of minima? 2n minus 1 lambda by 2. So, I'll be writing over here as for minima. Can I say delta x will be 2n minus 1 lambda by 2? Delta x will be 2n minus 1 lambda by 2. And for fifth minima, n will be equal to 5. So, delta x will be equal to 2 into 5 minus 1. 2 into 5 minus 1 lambda by 2. So, delta x in this case will be 2 into 5 is 10. 10 minus 1 is 9. So, it will be 9 lambda by 2. Okay, because it's talking about the fifth minima. Now, put it over here. So, this will be delta x is 9 lambda d by 2d. This is going to be the. Similarly, find the distance of seventh maxima. What is the formula? Delta x d divided by d. Now for maxima, what is the value of delta x? That is n lambda. Now n is 7, so it will be 7 lambda. So it will be 7 lambda d divided by d. As simple as that. Then you have fringe width. Fringe width. Guys, let's suppose I have got the fringe over here, which is made on the Young's double slit experiment. Okay, this is the fringe. This is the fringe. How much is the width of the fringe? How much is the width of the fringe? How much is the width of this fringe? That is called the fringe width. That is called the fringe width. And how do you exactly calculate the fringe width? Okay, so you say it is lambda d by d. Lambda d by d. What is this d? D is, by the way, the distance between the slits and the screen. I forgot to tell you. D is distance between the slits and the screen. Small d is distance between the two slits. Distance between the two slits. Lambda is the wavelength. Okay, d divided by d. Capital D is the distance between the screen and the slits. This small d is the distance between the two slits. Simple, simple, simple. Okay. Angular fringe width. Guys. See. Let's suppose I am saying you have got these fringes over here. Okay. So this is the central maxima. You have got this fringe width over here. I'm saying, sir, what is the linear fringe width? That will be this one. This is the linear fringe width. Then angular fringe width. it is placed at what distance? This theta. Angular fringe width. What will be this angle? How much will be this angle? Okay, angular fringe width. At what angle it is placed from the central maxima? From the central maxima. Okay, that is simply tan theta is equal to lambda by d. Tan theta is equal to lambda by d. Okay, lambda by d. Small d. Now there are some questions. In a Young's double slit experiment, if the separation between the slits is halved, so if d dash becomes d by 2 and distance between the slits is doubled. Okay. Distance separation between slits. If the separation between the slits is halved, yes. So d dash is equal to d by 2. And distance between the slits and the screen is doubled. So capital D dash is equal to 2d. Then the fringe width will be as compared to the original fringe width. Guys, what is the original fringe width? Lambda d by d. New fringe width will be beta dash. Guys, lambda will remain lambda only. If you are doubling this, so this is 2d. And if you are decreasing this, halving is, if you make it halved, so d by 2. 2 into 2 is 4. 4 lambda d divided by d. That is 4 times beta. 4 times. Yes, 4 times. Okay. In a Young's double slit experiment, blue light of wavelength 500 nanometer is used. So lambda is given as 500 nanometer. If you convert this nanometer into meter, so it will be 500 into 10 raised power minus 9. The slits are 1.2 mm apart. So small distance, small d is given as 1.2 mm. So if you convert it, this is in the meters. If you convert this into meters, 1.2 into 10 raised power minus 3 meters. And viewing screen is 5.4 meter away. So capital D is given as 5.4 meters. Okay. Find the fringe width. So fringe width will be simply lambda d divided by d. Just put the values over here, get the answer. Is this clear, guys? Tell me. Is this clear? Give me the signal in the chats. Okay. Now, guys, non-standard YDSC. Guys, when it comes to the non-standard YDSC, I would want you guys to focus over here. Non-standard YDSC means if you have the Young's double slit experiment placed in a medium. Previously, we were performing the Young's double slit experiment in air. Right now, we are placing it in a medium which has got the refractive index mu. In this particular case, understand one thing. Lambda of any medium is given as lambda divided by refractive index. Now, guys, position of the maxima and minima will be like y. At what distance fringe will be formed? Simply, you guys will be writing over here n lambda d divided by mu d. N lambda d divided by mu d. Okay. If you're talking about the fifth brine fringe, so n will be 5. Okay. Okay. And lambda d is the separation between the slits and the screen. Mu is the refractive index of the medium. D will be the separation between the slits. Similarly, y minimum, that is distance of the minima, it is going to be 2n minus 1 lambda d divided by 2 into mu d. This is going to be the distance of the minima from the central maxima. Similarly, fringe width, instead of fringe width, when it comes to the fringe width, how thick the fringe width is going to be, lambda d divided by mu d. Lambda d divided by mu d. Previously, it was lambda d by d. Right now, mu is added over here. This is called the non-standard YDSC. Let's suppose if you place a slab in front of the slit, in that particular case, what is going to happen? This is a Young's double slit experiment. You are placing a slab in front of the slit. What is going to happen? Central maxima will shift in the direction of slab inserted. If the slab is inserted from this side, so central maxima will shift from this side. If the slab is inserted from the lower side, central maxima will shift. Fringe width will remain the same. Okay. If somebody asks you, how much central maxima will shift on the screen to the upper side? Shift is equal d into mu minus 1 into t. T is the width of the slab. Mu is the refractive index of the slab. Upon d. Okay. Mu is the refractive index of the slab. T is the width of the slab. Okay. I hope you will mark it down. Number of fringes. How many number of fringes will be made on the screen? That is mu minus 1 into t divided by lambda. Mu is the refractive index of the slab. T is the width of the slab. And lambda is the wavelength. Now comes the diffraction. What does diffraction mean? In case of diffraction, you have only one slit. Like over here, this is the door. This pattern of fringes due to only one slit is what we call the diffraction. In case of YDS, you have two slits. In case of diffraction, you have only one slit. Okay. Okay. Now, guys, take a look here. Diffraction. Now, this is a slit over here. This is a source over here. Light is passing through this slit. It falls onto the screen. As light coming from the source goes through the narrow opening. As light is coming from the source, it goes through the narrow opening. Okay. Now, guys, it should directly fall on the screen. It should directly fall at this particular point. But this doesn't happen. But it bends and reaches the shadow regions also. It bends and reaches these regions also. Okay. It is called the diffraction. Like in this particular case, this light was supposed to reach here only, but it is reaching at all the points. This pattern is called the diffraction. Now, you have single slit diffraction. Okay. Okay. Now, guys, take a look. See, through this slit, light is falling and fringe patterns are made on the screen. In case of diffraction, always remember here, this is called the central maxima. Central maxima is wider and it is having the large intensity. Keep that thing in your mind. The intensity of the central maxima in case of diffraction is large and it is wider. Then you have the first maxima, second maxima, third maxima. Minima, 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 minima. Okay. So this is the intensity graph. Intensity is large. Then it keeps on decreasing, and intensity of last one will be 0. Okay. So it keeps on decreasing. This is the intensity graph. Now, there is an experiment. Okay. This was the physicist who performed this experiment, that is diffraction at single slit. See, guys, you'll be having a slit over here, and then you place a lens. Okay. Now, when the light leaves, because it becomes parallel, okay? No, sorry, this is the source over here. So light is coming from the source. After the source, this lens makes the light parallel. Now, these parallel rays pass through this slit. These parallel rays pass through this slit, okay? And my dear friends, fall on the screen. This is the screen. Don't get confused with this diagram. These are the light rays which are passing through the slit. This is the slit. How much is the opening of the slit? A. Okay, here opening of the slit is A. Width of the slit is A. Okay. Now guys, one light ray falls something like this. Another light ray falls something like this. If this is A, this will be A cos theta. This will be A sin theta. And this A sin theta will be the path difference between this and this. In case of single slit, if light rays are entering, first light ray will be this, last light ray will be this. If this is A, this is theta, this will be A cos theta, this will be A sin theta. This A sin theta is the path difference over here. Okay. And this will be central maxima. This is any fringe you have, bright, dark, whatever it may be. Now guys, see. I say path difference. Guys. Let's suppose the wave is falling at this point. How much is the path difference between this? That is A sin theta. That's what I'm saying. Path difference in case of diffraction is A sin theta. Okay. Path difference is A sin theta. Now guys, if somebody says that for maxima, what is going to be the path difference for maxima? What is going to be the path difference? What is going to be the path difference for maxima? What is going to be the path difference in case of diffraction? We'll say, sir, path difference is delta x is equal to A sin theta. Guys, what was the path diffraction in case of maxima in YDSC? Here I told you that path difference in case of maxima in YDSC is n lambda. Path difference in case of YDSC, in case of minima, it is 2n minus 1 into lambda by 2. But when it comes to this, for single slit diffraction, path difference is A sin theta, that is 2n plus 1 lambda by 2, where n is 1, 2, 3 and so on. If you put n is equal to 1, 2 plus 1 is 3 lambda by 2 will be the path difference. So in case of diffraction, if delta x comes out to be 3 lambda by 2, we say maxima will be formed. Okay. If you put 2 over here, 2 into 2 is 4, 5 lambda by 2. And this is the path difference. And one more thing, angular position of nth maxima. Angular position, guys. Angular position. Understand one thing. Let's suppose at this point, this is maxima formed. Guys, at what angle it is formed, that is called the angular position, this theta. This theta. And this theta will be equals to 2n plus 1 into lambda divided by 2a. Okay. 2n plus 1 into lambda divided by 2a. So this is going to be the angular position of nth maxima. If you are talking about the fifth maxima, n will be 5. If you're talking about the fourth maxima, n will be 4. Then, my dear friends, position of maxima from central maxima. Position of maxima from central maxima. Like you have position of maxima from central maxima. This central maxima. This is the, let's suppose, any maxima, nth maxima. What is the position? How much is this distance? So that is how you can find that. How you can find that? That will be 2n plus 1 divided by 2a lambda d. D is the separation between the slit and the screen. N is the which maxima you are talking about. A is the width of the opening, width of the slit. So this is going to be the position of the maxima from the central maxima. This is going to be the angular position. This is going to be the path difference. I hope all the 3 points are clear. I hope all the 3 points are clear. Now guys, for minima, if let's suppose somebody says, sir, at this point P, minima is formed, what is going to be the path difference in case of minima? You guys will say, sir, in case of minima, path difference A sine theta is going to be n lambda. It is going to be n lambda. Okay? And my dear friends, where n is 1, 2, 3, 4, and so on. And so on. And guys, angular position of maxima, angular position of minima means if I say here minima is formed, at what angle it is formed? So this angular position is going to be, for minima, it is going to be, that is n lambda d divided by a, n lambda d divided by a. Angular position is this, sorry, n lambda by a, and position of the minima from the central maxima. So from the central maxima till that, it is n lambda d divided by a. This is the linear position, that is the angular position. Okay? Yes. Yes. One more thing that we define over here. Central maxima. Guys, see, when it comes to the central maxima, in case of diffraction, central maxima is bigger. Okay? So here central maxima is more wider with large intensity. It is more wider with large intensity. Okay? Now linear width of central maxima. How much is this width of central maxima? That is 2 lambda d divided by a. What is d? D is the separation between the slits and the screen. A is the size of this opening, narrow opening. Lambda is the wavelength. Okay? If somebody says angular width means this angular width. Okay? This angular width. You'll simply say angular width is 2 lambda divided by a. 2 lambda divided by a. Like, guys, let's take a look at this question. In a single slit diffraction, width of slit is 1 mm. Okay? Width of slit means A is given as 1 mm. So means that is 10 raised power minus 3 meters. Wavelength of the light is 5000 angstrom. Lambda is given as 5000 angstrom. So 5000 angstrom, if you convert into the meters, so 5000 into 10 raised power minus 10 meters. You will be writing it something like this. Okay. Distance of the slit is 2 meters away from the screen. So capital D is given as 2 meters. Find the position of first minima. So position of first minima. This is the position. Now guys, understand very carefully. If they ask position of the angular position of the minima, then you will be using this formula. If they ask position of the first minima from the central maxima, we'll be using n lambda d divided by a. For first minima, n will be 1. Y is equal to n lambda d divided by a. Y is equal to n lambda d divided by a. Just you need to put these values and get the value of y. then, okay, you'll be putting these values over here. Next in this one, they are asking width of central maxima. This is the first for second. Width of central maxima. Guys, width of central maxima will be, if they ask angular width, you'll be using this. If they ask width only, means linear width, 2 lambda d divided by a. So 2 lambda d divided by a. Now again put these values over here, you'll get the answer. As simple as that, as simple as that. Let's suppose you have this. Light of wavelength lambda is equal to 6000 angstrom. That is 6000 into 10 raised power minus 10 meters. Is incident normally on a slit of width. So slit having the width 24 into 10 raised power minus 5 centimeters. If you convert this in meters, so multiply it with 10 raised power minus 2 and then it will become meters. Find the angular position of second minimum from the central maximum. Find the angular position of second minimum. Angular position of second minima. Angular position of minima. Sin theta is equal to n lambda divided by a. Okay. Sin theta is equal to n lambda divided by a. If it is asking for the second minimum, so I can write over here sin theta is equal to n means 2 because it is saying for the second minimum. So lambda is given as over here 6000 into 10 raised power minus 10 upon, this is over here 24 into 10 raised power minus 5 into 10 raised power minus 2. Okay. Now do the calculations from your end. Okay. Now this is how much, guys? So from the upper side, 2 into 6 into 10 raised power plus 3 into 10 raised power minus 10 upon, in the denominator, 10 raised power plus 5. Guys, this is 24 into 10 raised power minus 5, 10 raised power minus 2, 10 raised power minus 7. In the numerator, this is also 10 raised power minus 7, 10 raised power minus 7. 26 is 12. So 12 divided by 24, ones are, twos are, so it is 1 by 2. So sin theta is coming out to be 1 by 2. So theta is coming out to be 30 degrees. Theta is coming out to be 30 degrees. So this is the, find out the angular position, means you are supposed to find the theta. What about this one? A plane wavefront of wavelength, a plane wavefront of wavelength lambda is equal to 6000 angstrom is incident upon a slit of 0.2 mm. This is 6000 into 10 raised power minus 10 meters. A is given as 0.2 into 10 raised power minus 3 meters. Okay. Screen is 2 meters away. D is given as 2 meters. Find the width of central maxima. That is 2 lambda D divided by A. Just put the values over here and get the answer. Just put the values and get the answer. Okay. So this is 2 lambda, in this case is 6000 into 10 raised power minus 10. D in this case is 2 upon, this will be over here 2 into 10 raised power minus 4. Okay, now do the calculation, it should come out to be 12. Okay. So this will be 2 into 2 is 4 into 6 into, this is 10 raised power minus 7, 10 raised power minus 7 upon, you have 2 into 10 raised power 4. 2 ones are, 2 twos are. So this will be 12 into, in mm will be, okay, 12 into, guys, this is 10 raised power minus 7. 10 raised power minus 7 into 10 raised power 4. That will be 10 raised power 3. 12 into 10 raised power minus 3. So that will be 12 mm. Central maximum mm, that is 12 mm. Polarization. Now guys, take a look. Polarization of light is an electromagnetic wave in which electric and magnetic field vectors vary sinusoidally. Guys, see, when it comes to a light, we say light is an electromagnetic wave in which electric field is also vibrating, magnetic field is also vibrating. Guys, see, this is what we call the electric field. This is what we call the magnetic field, which is vibrating perpendicularly, sinusoidally or perpendicularly. Okay? Mutually perpendicular to each other. So we say light is an electromagnetic wave in which electric and magnetic fields are vibrating, present. Okay? Okay? Perpendicular to each other, as well as perpendicular to the propagation of wave. What does that mean? If electric field vibrates like this, okay, if electric field vibrates like this, magnetic field like this, wave is propagating in the forward direction. All the three are mutually perpendicular. The magnitude of electric field vector is much larger as compared to the magnitude of electric field vector. As compared to the magnitude of magnetic field vector. Guys, electric field vector present in the wave is large as compared to the magnetic field. Okay? Thus, we describe light in terms of electric field oscillations only. So, we say light is made up of electric field only, okay, because magnetic field vector is less. Then you have unpolarized light. In ordinary light, the electric field vectors disturb uniformly in all possible directions perpendicular to the propagation of wave. Guys, see, if let's suppose you have a light over here, it's unpolarized light. It means in this unpolarized light, electric field will be vibrating like this, like this, like this, in different directions, in many directions. Electric field will, this is unpolarized light. Electric field is vibrating in many directions. But you want to polarize it. What does that mean? That means you want this electric field to vibrate only in one direction. So basically, when you pass through this light through the polarizer, it will allow only that component of electric field which is something like this, parallel to this axis. Okay, so this component will be allowed. This will not be allowed. This will not be allowed. This. So this unpolarized, this portion will be removed. Now see, this is the polarized light. Only that component is allowed which is along this polarizer axis, transmission axis. Okay? Okay? And then my dear friends, that's what I'm trying to say. See, here this electric field is, this portion of the light is only allowed. This is cancelled out. This is cancelled. So this is the polarized light. Similarly here, and when the light gets polarized, guys, always remember its intensity becomes I naught by 2. Here, if it is intensity is I naught, here it will become I naught by 2. Again, when it enters the next polarizer, that is called the analyzer. Now, guys, see, this is the axis of the previous polarizer, and this analyzer is bit rotated. Okay, with this it is making the angle phi. When this light enters this polarizer, analyzer, final intensity of the light will be I naught by 2 cos square of phi. I naught by 2 cos square of phi. And this phi is the angle between axis of the polarizer and axis of the analyzer and axis of the polarizer. Angle between these two. This is the final. So if I naught is entering the polarizer, intensity becomes I naught by 2. If it further enters the analyzer, intensity becomes I naught by 2 cos square of phi. This is called the law of Malus. This is called the law of Malus. Okay. This is called the law of Malus. Okay. What does law of Malus say? It says when the light enters the polarizer, its intensity becomes I naught by 2. Okay. Then if it enters, further passes through another polarizer called analyzer. Its intensity becomes I naught by 2 cos square of phi. And let's suppose if theta is equal to 60 degrees, what will be the value of final intensity? I will come out to be. So in that case, I will come out to be I naught by 2 cos square of 60. Cos 60 is 1 by 2. So I will come out to be I naught by 2 cos 1 by 2, 1 by 2 whole square, that will be 1 by 4. So it will come out to be I naught divided by 8. And if theta is equal to 90, you have completely rotated it. In that case, final intensity will be I naught by 2 cos square of 90. Cos square 90, that is 0. I will come out to be 0. The final, no light will come out in that particular case. Guys, give me the signal in the chats. Is it clear? Is it clear? Now, Brevister's law. This is the law which we need to cover over here, and we are done with this chapter. See, what does Brevister's law actually say? According to the Brevister's law, if an unpolarized light goes from one medium to another, this is one medium, that is air, this is another medium, it is having the refractive index mu. If an unpolarized light goes from one medium to another, okay, then some part of it gets reflected and some gets refracted. Some part of it gets reflected, some gets refracted. The one which is reflected in the same medium is called reflection. The one which is refracted in the another medium is called refraction. Some part of it gets reflected, some part of it gets refracted. Okay. If the angle between the reflected light and refracted light is 90 degrees, if the angle between the refracted and reflected light, if this is 90 degrees, if it is 90 degrees, okay, then the reflected light gets completely polarized. Reflected light gets completely polarized. This one gets completely polarized. And refracted ray gets partially polarized. If this angle comes out to be equal to 90, this gets completely polarized, this gets partially polarized. That is what the Brevister's law says. This is completely, this is partially. This is what does the Brevister's law say. Okay. And in this particular case, we define here incident angle is called IP, that is polarization angle. So mu is equal to tan of IP. So here incident angle is called IP. This angle is called IP. And we say mu will be equals to tan of IP. Okay, tan of IP. Let's suppose if a medium has got refractive index √3, okay, and somebody asks you what will be the angle of incidence in that case, what will be the angle of polarization in that case, tan IP is equal to √3, IP will be is equal to 60 degrees. Okay, with this we are done and dusted with this chapter. Next we'll be starting the modern physics.
Guys, tell me, is it clear till over here? Is it clear till over here? Break will take later on, huh? Is it clear till over here? Okay, guys. Let's start the modern physics, that is dual nature of matter and radiations. Guys, the first thing that I'll be telling you over here is, when it comes to the modern physics, always remember, we consider light as a particle here. In this particular case, we consider the light as a particle. We consider the light as a particle. Now, guys, what does that mean? That means if I say from now onwards, there is a light source, okay? From this light source, light is coming out. So you'll be saying that these are the photons coming out. These are the particles coming out. So basically, what is this coming out of this light source? This is how we define as photons. These are the photons coming out of the light source. Okay, that's how we define. Now, guys, take a look. If I say, sir, this light which is coming out over here, this is photons. This light has energy. Yes. So these photons will also have energy. These photons will also have energy. Light energy, photon energy. Now, the first topic that we need to understand in the dual nature of matter and radiations, that will be energy of a photon. We say light is coming out of the bulb. These are the photons coming out. And these photons will have energy. How to find the energy of a photon? That will be h multiplied by f. H means Planck's constant, f is frequency. Directly remember this. So this is the basic formula for the energy of a photon. When Planck's constant is multiplied with the frequency, it gives you the energy of photon. There is no derivation for this. Then, guys, sir, is there any other formula for the energy of a photon? Yes. We can say F is equal to C by lambda. F, we can say C by lambda. So instead of F, I am putting C by lambda. So this will be the energy of a photon. This is also the energy of photon. Sir, is there any other formula? Yes. We can say, and one more thing I just want you to remember over here, value of H is 6.6 into 10 raised power minus 34 joule second. Now, guys, when you put the value of Planck's constant here, when you put the speed of light, 3 into 10 raised power 8. So we say Planck's constant is 6.6 into 10 raised power minus 34 joule second. Planck's, this speed of light is 3 into 10 raised power 8. If you put it over here, then if you solve, it comes out to be 2 into 10 raised power minus 25 divided by lambda in joules. This is the energy of a photon in joules. Okay, this is the energy of a photon in joules. And here, lambda is in meters. Lambda is in meters. Next. Sir, is there any other formula to find the energy of a photon? Yes. That is, energy of a photon is 1240 in electron. Guys.
this, like if I say you have got, if I say you have got mass of this block as m is equal to 1 kg. Okay. You are also saying mass of this block is 1000 grams. So gram is also unit. Okay. Kg is also unit, gram is also unit. Similarly, you can measure the energy of a photon in joules also. You can measure the energy of a photon in electron volts also. Electron volts also. Okay. So my dear friends, if you want to calculate the energy of a photon in electron volts, you say it is 1240 divided by lambda, and where lambda is in nanometers, where lambda is in nanometers. So I can write, this is the energy of a photon in electron volts. This is the energy of a photon in electron volts. Okay. Where lambda is in nanometers. Lambda here is given in nanometers. Keep that. I'll show you the question also. And this is the energy of a photon in electron volts, where lambda is in angstrom. Where lambda is in angstrom. Example. Let's suppose I'll give you this. Let's suppose I have got a photon over here. Okay. This photon has got a wavelength of 4000 angstrom. I'm saying find energy in electron volts. Sir, you will be using energy of a photon is 12400 divided by lambda. This will be in angstrom and energy will be in electron volts. Why? Because use this formula. When lambda is given in angstrom, energy is given in electron volts. Okay. Now tell me, sir, you will be saying E is equal to 12400 divided by 4000 over here. Solve this, you will get the energy of a photon. Now guys, if I am saying you have got a photon over here and lambda of photon is 310 nanometer. Okay. Find the energy of a photon. Sir, you will be using 1240 divided by lambda in nanometer. Okay. This will be in electron. When lambda is in nanometer, 1240. When lambda is in angstrom, 12400. Sir, what about in joules? What about in joules? Okay. What is the energy of a photon in joules associated with a photon of wavelength this much? Guys, you have to find the energy in joules. Which formula I am supposed to use when I am supposed to find the energy in joules? 2 into 10 raised power minus 25 divided by lambda. This lambda is in meters. So I can use this formula only. So energy of a photon is 2 into 10 raised power minus 25 divided by lambda is in meters. Now you can say E is equal to, in this particular case, you can say E is equal to 2 into 10 raised power minus 25 divided by lambda is given as 4000. So this is 4000 into 10 raised power minus 10. Because when you convert this lambda, this is an angstrom, when you convert this in meters, we will be writing lambda is equal to 4000 into 10 raised power minus. Always remember, 1 angstrom is equal to 10 raised power minus 10 meters. 1 nanometer is equal to 10 raised power minus 9 meters. Okay. So this will give you the energy of photon in joules. Okay. And you can find the energy of photon in electron volts also. Then you have over here the concept that is what we call energy of light. Guys, the simple concept is if you have got a light source over here. If you have got a light source. Over here. Okay. So light is coming out of the light source. This is the light which is coming out of the light source. Okay. This is the light which is coming out of the light source. Now, is this light made of one photon, n number of photons? Sir, this is made up of n number of photons. N photons. Now, guys, if one photon has got the energy hc by lambda, 10 photons will have 10 hc by lambda. N photons will have n hc by lambda. So this is what we call the energy of light. So energy of n photons will be the energy of light, because light itself is made up of n number of photons. Okay. Then you have power of light. How do we define the power of light? Power is defined as the energy per second. Guys, let's suppose I have got a bulb over here. This is the bulb. So this bulb is basically sending the light. This bulb is sending the light. Okay, it is sending the photons. I'm saying, how much power does this bulb has? Sir, it has got a lot of power. How do we define power? Power means how much energy it is giving every second. Sir, it is giving more energy. Sir, this bulb is giving less energy, less brightness. So I can say less power. So power is simply how much energy it is giving every second, energy upon time. Power is defined as energy per second. How much power it is giving every second. If it is giving large energy every second, then power will be large. So power is energy upon time. Energy is what? NHC by lambda. NHC by lambda multiplied by time. This is power. Okay. Okay. Like you have a question over here. Let NR and NB be the respectively the number of photons of the red bulb and the blue bulb. You have got two bulbs over here. Okay. So this one, this one. This is a red bulb. This is blue bulb. Okay. Now it says that in this particular case, photons are coming out of the red bulb. Okay. NR is the number of photons of red. NB is the number of photons of blue. Okay. Power of both is equal. Power of red is equal to the power of blue. Okay. Power of red is equal to the power of blue. You guys are supposed to tell me in this particular case, which will emit more number of photons? Which will emit more number of photons? Basically, both are giving you the photons. Which of the two bulbs will give the more number of photons in this particular case? Which of the two bulbs will send the more number of photons in this case? Tell me in the chats quickly. Tell me, guys. When it comes to the power, we say power is NHF. Now NHF divided by T. Because what is energy, guys? Energy is equal to NHF divided by energy upon time. Then we say F is C by lambda. NHC divided by lambda into time. So F is frequency. Okay. Is equal to, this is number of photons of red, frequency of red. Okay. This is NHF divided by T. Number of photons of blue, frequency of blue. H will cancel, time will cancel. This is same for both. Now here, number of photons of red into frequency of red will be equals to number of photons of blue, frequency of blue. Frequency of blue. Now guys, tell me in this particular case, I want you to understand. We say frequency of red, always remember, frequency of red is less than frequency of blue. See, their product is equal. If frequency of red is less, frequency of red is less as compared to the frequency of blue, then we say, then NR, number of photons of red, must be greater than number of photons of blue. Why? Because if you say this is less, this is also less, so the whole term will become less. It will not be equal to this. If this is less, this has to be more. This has to be more. This has to be more. Then we have the intensity of light. Now guys, what is intensity all about? Intensity is defined as energy per second per unit area. Means it is power upon area. Simply. Sir, we have got the bulb over here. How do we define the intensity? How much energy it is giving every second per unit area. Like, I'll define over here. This is a bulb, okay? From the bulb, photons are coming out, okay? Let's suppose it is falling on the plate. On this unit area, how many number of photons are falling? How much energy is falling? Every second. That is intensity. More energy is falling on this unit area, every second intensity will be more. Like you say, my dear friends, you have the bulb over here. Near the bulb, intensity of the light is large, okay? Area is small. Away from the bulb, intensity of the bulb will be less brightness over there. So intensity means NHF. Instead of energy, I'll write NHC divided by lambda into AT. Lambda into AT. This is the formula. Okay, number of photons, Planck's constant, speed of light, wavelength, time, area. This is how we define the intensity of light. Okay. Now guys, an important topic that we need to talk about is photoelectric effect. That is photoelectric effect. Important topic is photoelectric effect. See, how do we define photoelectric effect? Guys, let's suppose you have got a metal surface over here. Let's suppose you have got a metal surface over here. Okay. And you have got a light source over here. You have got a light source over here. And in this particular case, I am saying that we are performing an experiment. You took a light source, you took a metal surface. Now light is falling on this metal surface. Light is coming out of the source and it is falling on this metal surface. We observed that electrons are coming out. Electrons are ejected from this metal surface. So this phenomena, when light falls on a photosensitive metallic surface, electrons are ejected from the surface. When light falls onto the photosensitive metallic surface, electrons are ejected from the surface. The process is called photoelectric effect. The process is called photoelectric effect. When the light falls onto the metal surface and electrons are ejected from the surface, the process is called photoelectric effect. The process is called photoelectric effect. Okay. Now, my dear friends, in this particular case, we define a term that is called the work function. What does work function actually mean? Work function means it is the minimum energy required to pull out the electrons from the metal surface. Like, I'll give you the example. I have got a metal surface over here. I am supposed to pull out the electrons from the metal surface. How am I supposed to do photoelectric effect? So basically, you will send a photon, you will send the light, photon, that will fall onto this one. Because of falling of photon, electron will come out. Now guys, if I say work function of this metal is 2 electron volts, then this photon must have the energy of 2 electron volts to pull out the electron. Sir, what if its energy is less than 2 electron volts? That it cannot pull out the electron. So we say it is the minimum energy required to take out the electron. Like, work function of this metal is 5 electron volts. So what should be the energy of photon? So energy of photon must be 5, greater than 5, but not less than 5. So then only electron will come out. So work function of a metal defines how much energy is required so that you can take out the electron, so that photoelectric effect takes place. Now, experimental setup of photoelectric effect. Guys, see, when you take the experimental setup of photoelectric effect, you take a vacuum chamber, something like this. This is a vacuum chamber. Okay, this is a tube-like structure. Inside this tube-like structure, you take a metal plate, namely cathode, and this metal plate, namely anode. Okay. Now guys, simply, I'll tell you what happens over here. You keep the narrow opening and then you take a light source over here. So we say photons are coming out of this light source and it falls onto this metal surface. Whenever photons fall onto this metal surface, electrons are ejected from the metal surface. Electrons are ejected from the metal surface. Okay. Now guys, if let's suppose a photon of 8 electron volt falls onto the cathode. Okay. Now electron inside this cathode, some energy it will use in order to come out of this metal surface. Let's suppose 2 electron volt is the work function. So how much energy is required to pull out the metal electron from the metal surface? 2 electron volt. Energy of photon is 2. So this photon is giving the electron to 8 electron volts energy. Photon is giving how much? 8 electron volts. Now among those 8 electron volts, 2 electron volt it is using to come out, in order to come out. Sir, what about the rest of the 6? 6 electron volts it will be using as a kinetic energy so that it can move forward. Like this is the cathode, this is the electron here. You are sending a photon, its energy is 8 electron volt. So this electron is getting 8 electron volt. Work function of this metal is 2. So first it will use 2 electron volt so that it can come out. Once it comes out, now it has 6 electron volt energy. Due to that 6, it will move forward. Due to that 6, it will move forward. So what I'm trying to say is that energy of photon is used in work function so that electron comes out of the metal surface, and in kinetic energy so that it moves forward. So can I write energy of a photon is equal to work function plus kinetic energy maximum? Is equal to work function plus kinetic energy maximum. This is called Einstein's photoelectric equation. This is called Einstein's photoelectric equation. This is called Einstein's photoelectric equation. Energy of photon is equal to work function plus kinetic energy maximum. Okay. 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 Now guys, listen to me very carefully. If let's suppose 10 electrons are coming out of the cathode and only 4 are able to reach anode. Understand this scenario I'm saying. Guys, see, I'll make you understand this. Let's suppose this is the cathode. This is the cathode and this is anode. If let's suppose photons are falling, photons are falling, photons are falling. Due to the fall of photons, electrons come out. How many? Let's suppose 10 electrons are coming out. Okay. Out of 10 electrons, only 4 are able to move. Why only 4? Because these 4 are getting the sufficient amount of energy. What about rest? They are not getting the sufficient energy. Okay. Like this electron, it is getting work function is, let's suppose, 2 electron volts. It is getting energy only 1 electron volt. So that's why. So let's suppose it is getting only 2 electron volts. Energy is only getting 2 electron volts. So it is just coming out. So its kinetic energy is 0. So how is it possible that it will move forward? It will not move forward. So what you will do is that you will connect a battery. So when you connect a battery, positive terminal connect from this side. So it will create the positive charge on this. So this is positive terminal, this is negative terminal. So when it creates the positive charge from this side, it will attract the electrons. So when it attracts the electrons, these electrons start moving. These electrons start moving. And when electrons start moving, current will start flowing, current will increase. Initially, only 4 electrons were moving, less current. Now, as you increase this positive charge here, it will attract the negative charge because positive charge attracts the negative charge. So current will increase. And then, guys, if due to the motion of electrons, we say photocurrent is produced. Due to the motion of electrons, photocurrent is produced. Now guys, this is called the EMF. If you increase the EMF, potential difference, we say here positive charges, let's suppose 10 volts, some positive charge, 20 volts increase positive charge, it will attract electron. As you increase the positive charge, as you increase the EMF, we say photocurrent is also increased. Photocurrent is also increased. Okay. And my dear friends, so the photocurrent increase something like this and becomes constant. Why? Because let's suppose you applied a sufficient amount of EMF over here. So all the 10 electrons now start moving. When all the 10 electrons start moving, we say in that particular case, graph will be constant. Simply, I would want you guys to remember in this particular case, when these electrons fall onto the cathode, so we say energy of photon is used in the work function and kinetic energy maximum. Okay. Then, because of the kinetic energy, electrons will flow to the anode side and photocurrent is produced. And if somebody asks you, what is the graph of that photocurrent? You say graph of that photocurrent will be something like this. This is the graph of photocurrent versus EMF. This is the graph of photocurrent versus EMF. And what is this EMF? EMF is, I said only 4 electrons were moving. Then you connected the battery. You increase the EMF, positive charge increases. It will attract the electrons. When it attracts the electrons, photocurrent keeps on increasing. Let's suppose, guys, if you reverse the polarity, means if you connect positive terminal from this side, negative terminal from this side, it will create negative charge now. Okay. Now, this negative charge will repel these electrons. So it will stop the flow of electrons. So that's why if you increase the negative EMF, so current will decrease and it will become 0. So when current is 0, that value, let's suppose you are applying minus 20 volt. At minus 20 volt, no electron is able to reach this cathode. So that potential is called stopping potential. Stopping potential. That potential is called stopping. EMF means potential difference, like you have over here 20 volts, 30 volts, 40 volts. Is this clear? Is this clear? So why this graph, how this graph is exactly made, I hope this is crystalline clear to each and every single student. I hope this is crystalline clear to each and every single student. So basically I said, if let's suppose 10 electrons are coming out of 10 electrons, only 4 are able to reach anode. Why? Because they are getting sufficient energy. Then what do? We connect a battery. Okay. This is the positive terminal. Positive terminal creates positive charge. Let's suppose initially you apply 20 volt. Sir, now this starts moving, this starts moving. Sir, now apply 30 volt. It increases more positive charge. Now this starts moving, this starts moving. Sir, now apply 40 volt. This starts moving, all started moving. Now we say graph between photocurrent and EMF. As you keep on increasing EMF, okay, photocurrent increases. Okay. And when all, let's suppose at 40 volt, all are moving, photocurrent becomes constant. So photocurrent becomes, that's called the saturation current. Sir, why didn't you start the graph from 0? Because when EMF was 0, no battery was connected. Still 4 electrons were moving. 4 electrons were, so current was there, current was not 0. Now I am saying reverse the polarity of the battery. Okay. Negative from this side, positive from this side. It will create negative charge on this. So let's suppose minus 20. If you are applying minus 20, sir, now it is repelling these electrons. It is repelling these electrons. Okay. It is repelling these electrons. This negative charge repels the electrons. Initially at 0 volt, 4 were moving. Now when you apply 20 volt, now this is repelled, this is repelled. At let's suppose 30 volt, all are repelled. No electron flow, so photocurrent becomes 0. If you keep on increasing, sir, minus 10 volt, minus 20 volt, and minus 30 volt, photocurrent decreases, and here it becomes 0. So this is called stopping potential. So stopping potential is where photocurrent becomes 0. It is that potential where photocurrent becomes 0. Now guys, take a look. For a certain metal, V means frequency. Let's call it F. For a certain metal, frequency F is 5 times F naught. F naught will be the threshold frequency. Like guys, I'm saying if a photon falls onto this metallic surface, okay? If the photon is falling onto the surface, electron is coming out of the surface, okay? We say energy of photon is used into the work function plus kinetic energy maximum. You can write it something like this, guys. This is the minimum energy required to pull out the electron. This energy of photon you can write H into F, because we know it is H into F is equal. This energy of this work function you can also write H into F naught. Why? Because whenever you multiply frequency with Planck's constant, it gives you energy. This will also give energy. Then you say plus 1 by 2 mv square, because this is kinetic energy is 1 by 2 mv square. So what is this F naught? F naught is the threshold frequency. Okay, like this is the minimum frequency at which photoelectric effect takes place. This is the minimum energy at which photoelectric effect takes place. This is the minimum frequency at which photoelectric effect takes place. Okay. Now guys, see, what does it say? It says that you have got a metal surface over here. Okay. On this metal surface, a photon is falling. A photon is falling. There is a photon which is falling on this metal surface. Its frequency is 5 times F naught. Its frequency is 5 times F naught. Okay. So its frequency F is equal to 5 times F naught. Okay. And due to this, the electron which is coming out, this electron has a velocity of 8 into 10 raised power 6. 8 into 10 raised power 6 meter per second. Okay. Yes. Then it says that if F is equal to 2 times of F naught, if another photon falls over here, if its frequency becomes 2 times F naught, if its frequency becomes 2 times F naught, if another photon falls over here, if its frequency becomes 2 times F naught, then the electron which comes out, it will have what velocity? V2. Let's suppose this is V1. If there is a photon which is falling, its frequency is this. If this is the frequency, what is the velocity of the photon? See guys, in this particular case, I would want you guys to focus exactly over here. Guys, use Einstein's photoelectric equation. What does that say? Energy of photon is work function plus kinetic energy maximum. So it says that H into F is equal to H into F naught plus 1 by 2 mv1 square. Now guys, H into F is equal to H into F naught. Okay. Here F is the frequency of the photon. In first case, frequency of the photon is 5 times of F naught. So 5 times hf naught is equal to hf naught, and take this here, it will be minus hf naught is equal to 1 by 2 mv1 square. 5 minus 1, that is 4 hf naught is equal to 1 by 2 mv1 square. Call this as equation first. Now guys, in this case, use Einstein's photoelectric equation. So you will be saying, sir, here frequency is h into f, h into f. What is the value of f over here? 2 times f naught is equal to h into f naught, because this is h into f naught, plus 1 by 2 mv2 square. Now 2 minus 1 is 1, so this will be hf naught is equal to 1 by 2 mv2 square. Call this as equation second. Divide first and second. Divide first and second. If you divide first and second, what are you going to get? So it will be 4 hf naught divided by hf naught. This divided by this. So it will get you 1 by 2 mv1 square upon 1 by 2 mv2 square. This and this will cancel. hf naught will cancel. So v1 divided by v2 will be equals to root of 4. That will be 2. So v2 will be equal to v1 divided by 2. So what is the value of v2? v1? v1 is given as 8 into 10 raised power 6. 8 into 10 raised power 6 divided by 2. That is 4 into 10 raised power 6 per second. Is this clear? Is this clear? Guys, this is the question on the same concept. This is the question. I'll show you it. You guys will solve it from your end. Just I'll give you the idea. 2 radiation of photon energies fall on a photosensitive material. Okay. So this is the radiation. Its energy is given as 1 electron volt. Okay. This is another radiation. Its energy is given as 2.5 electron volt. Fall on a photosensitive material of work function. This has work function of 0.5 electron volt. This has work function of 0.5 electron volt. The ratio of, okay, so the electron which comes due to this, electron which comes out due to this, it has got velocity v1. The electron which comes out due to this, it has got velocity v2. You are supposed to find v1 is to v2. Simple, guys, simple, extremely simple. What you are supposed to do in this particular case is use the Einstein's photoelectric equation. Guys, energy of photon is equal to work function plus kinetic energy maximum. Okay, how do you write it? H into F is equal to HF naught, or directly you say. Guys, in case 1, what is the energy of photon over here? That is 1 electron volt is equal. Work function is 0.5 plus 1 by 2 mv1 square. 1 minus 0.5, that is 0.5, so it will be 1 by 2 is equal to 1 by 2 mv1 square. Call this as equation first. Okay, use the Einstein's photoelectric equation here. So energy is 2.5 is equal to work function is 0.5 plus 1 by 2 mv2 square. Okay, 2 minus 0.5, 2 is equal to 1 by 2 mv2 square. This is the equation second that you have over here. Okay. Now tell me, guys, in this particular case, so you'll be writing over here, divide first and second. So this is 1 by 2, okay, divided by this 2. So it will get multiplied over here. 1 by 2 mv1 square upon 1 by 2 mv2 square. This and this will cancel. 1 by 4. So V1 divided by V2 will be equals to, this is 1 by 4 and its root. So root of 1 by 4. That'll be 1 is 2. Okay. Is that clear? Now guys, this is an important relation which I want to tell you. See guys, when it comes to the frequency, guys, always remember, if frequency increases, we say energy of a photon is equal to h into f. So energy of photon is directly proportional to the frequency, so energy of photon will also increase. Okay. Now guys, as when we talk about the energy of a photon, we say it is work function plus kinetic energy maximum. Now, if energy of photon increases, we say kinetic energy maximum increases. Okay. So I can say kinetic energy increases. One more formula I forgot to tell you. What is that? That is kinetic energy is also equal to EV naught, where V naught is the stopping potential. This is the relation between kinetic energy and stopping potential. If kinetic energy increases, if this increases, we say V naught also increases. So V naught also increases. That's what is mentioned over here. If frequency is increasing, photon energy is increasing. If photon energy increasing, kinetic energy is increasing. Kinetic energy of electron. If kinetic energy is increasing, stopping potential is increasing. As simple as that. As simple as that. Next, intensity. Guys, take a look over here. Intensity. We say when it comes to the intensity, it is NHC divided by lambda AT. Intensity, this is the formula for intensity. So here, intensity is proportional to number of photons. Okay. Number of photons. So basically, if intensity increases, so number of photon increases. Number of photons increase. Okay. Number of photon increase. Now guys, if number of photons increase, guys, if more number of photons are falling on the plate, we say more electrons will come out. More electrons will come out. So you are saying, sir, more number of photons are falling on the plate, more electrons will come out. Yes. If more electrons are coming out, more electrons are moving, we say photocurrent will increase, more photocurrent will be produced, photocurrent will increase. Okay. So this is the relation between these. This is the relation between these. Now guys, I would want you guys to understand one thing over here. What is that? Intensity has the relation with photocurrent. We say intensity is proportional to photocurrent. And frequency is related to stopping potential. So we say stopping potential is related to frequency. These two I want you to understand. Now look at the graph. Guys, you have got the three curves over here between photocurrent versus frequency. Can I say the three curves have got the same photocurrent? Same photocurrent or same saturation current. So I can say intensity of the three graphs will be same. I1 is equal to I2 is equal to I3. Same. Intensity of the three graphs will be same. And stopping potential of this is this, it is different. If stopping potential is different, just a second. Hello, Sigad. You got the generator on? Guys, take a look. So we say V1, V2, V3. We say stopping V0 is different. So stopping potential is different. V0 is different, so stopping potential is different. As simple as that. V0 is different, stopping potential is different. Why? Because stopping potential has directly relation with, oh sorry, if V0 is different, so frequency is different. Frequency is different. Because frequency has direct relation with stopping potential. So I can say in this particular case, we say here. I can say frequency of third is greater than frequency of second is greater than frequency of first. Why? Because stopping potential of this is greater than this, greater than this. That's why. It has direct relation. Now, let's talk about this graph. Here, could you please tell me which intensity is same or stopping potential is same? Sorry, intensity is same or frequency is same? In this particular case, saturation current is different. I is, here we say, photo current is different. Okay. So, intensity is different. Okay. So, I can say I2 is greater than I1. Okay. Because you say intensity is directly proportional to photo current. But when it comes to the stopping potential, V0 is same. So, frequency is same for both. F1 is equal to F2. This will be the relation in case of frequency and this. Here it will be opposite in this particular question. Let's take a look at this one. You have got, this was the question asked in AIPM 2014. From the figure shows which one of the following is the correct statement. Photocurrent versus EMF. Guys. Here I'll make this graph something like this. I'll make it something like this. The curve is given. This is between photocurrent and stop EMF. This is the curve. Okay. This is curve A, this is curve B, and this is curve C. Guys, clearly you can say in this particular case, see, A and B has got the same stopping potential. So A and B has the same frequency, but different photocurrent. Okay. But when it comes to the B and C, they have got the same photocurrent. Okay, same intensity, different frequency, because stopping potential is different. Now tell me which option is correct over here. Which option is correct? Curves B and C represent the incident radiation of different frequency. B and C represent the incident radiation of different frequency. Okay. Yes. Because stopping potential is different. And different intensities. No, intensity is same. B and C represent the incident radiation of same intensity. No. Curve A and B represent the incident radiation of same frequency. A and B has got the same frequency, but different intensities. Option B is correct. Option B is correct. Option B is correct. Because when it comes to the A and B, they have got different photocurrent, so intensity is different. They have got same stopping potential, so frequency will be same. F is same. We'll take the break exactly at 6 o'clock. At 6, we'll be taking the break. Now, guys, you have over here matter wavelength, or you have de Broglie wavelength, de Broglie's wavelength. What does it say? According to the de Broglie was basically a physicist. According to a de Broglie, everything in this universe has a wave nature, like this pen marker. This has got a particle nature. We can feel it. Yes, it's a particle. So it has a wave nature also according to the de Broglie. Yes, everything in this universe has got a wave nature. And the wave associated with it is called the matter wave. So it has got the wave nature. It will have the wave associated. What kind of wave does it have? That is called the matter wave, because there's a matter. And that matter wavelength, if somebody wants to ask you, sir, what is the matter wavelength of this? If somebody says, sir, is this phone a particle or a wave? Sir, this phone is a wave. Okay. This phone is a particle. We can feel its particle nature. Sir, is this phone a wave? Yes, this phone is a wave. How, sir? Because de Broglie said everything in this universe has a wave nature. And it has a wavelength associated with it. That is called the matter wave or de Broglie's wave. And how do we calculate its wavelength? Lambda is equal to h divided by mv. H is Planck's constant. mv means momentum, mass into velocity, mass, velocity. So it is momentum, h by mv. Okay. So means if a mass is moving with some velocity, it has the de Broglie's wavelength associated with it. It has a wavelength, so that will be h divided by mv. So it behaves like a wave. It behaves like a wave. Now, we have to see de Broglie's wavelength for a different number of particles. For different particles, you will have to see the de Broglie's wavelength. Guys, see, when it comes to the different forms of it, de Broglie's wavelength in terms of kinetic energy. Guys. When it comes to the de Broglie's wavelength, you say, sir, lambda is equal to h divided by mv. Lambda is equal to h divided by mv. This is de Broglie's wavelength in terms of momentum. In terms of kinetic energy, this will be the formula. In terms of kinetic energy, this is the formula. So h upon under root of 2 mke. This will be the de Broglie's wavelength. Now, guys, for different types of particles, de Broglie's wavelength will be different. De Broglie's wavelength for a relativistic particle. Relativistic particle means that particle which has got a speed comparable to the speed of light. It is moving with a very faster speed. Like electron, proton. Its de Broglie's wavelength will be lambda is equal to h multiplied by under root of 1 minus v square by c square. V is the velocity of that particle with which it is moving. C is the speed of light upon m naught into v. I'll write over here. V is the speed of that particle. And what is the C? C is the speed of light. Okay. What is this m naught? Rest mass of that particle. If that particle comes to rest, this will be the rest mass. Okay. Then you have, if there is a particle which is accelerated with the potential difference delta V. A particle can be, directly remember this, a particle can be accelerated with the potential difference delta V. So we can write its de Broglie wavelength will be lambda is equal to h upon under root of 2mq delta V. Q is that charge, delta V is the potential difference. Now, charge at rest in an electric field. If you place a charge in an electric field, this is the electric field. If you place the charge over here, what will be its de Broglie's wavelength? That is h upon QET. E is the electric field, Q is the charge, T is time, H is Planck's constant. H is Planck's constant. Then you have charged particle placed in a magnetic field. If let's suppose this is a magnetic field, In this magnetic field, you are sending a charge q with a velocity v. Okay. And this is h. Guys, always remember, when you send a charge inside the magnetic field, it follows the circular path. Okay, if you send it perpendicularly at an angle of 90 degree, where r is the radius of that circle. So h upon qbr, q is the charge, okay, b is the magnetic field, okay, r is the radius of that circular path. Now, de Broglie's wavelength for a gaseous molecule at temperature T. A gaseous molecule which is at temperature T. So you can write lambda is equal to h divided by under root of 3m kBT. 3m kBT, where kb is the Boltzmann's constant, T is the temperature. T is the temperature. Okay. Then you have de Broglie's wavelength for an electron moving in nth orbit of an atom. For an electron moving in nth orbit of an atom. Let's suppose you have got an atom over here. Okay. So this is the nucleus. This is the electron which is revolving in the nth orbit. Okay. What will be its de Broglie's wavelength? That is this. nh under root of 2m. And it means the nth orbit, number of orbit, which orbit you are talking about. H Planck's constant 2m, 13.6. Okay. Now guys, there is a question which was asked in JMeans 2021. The following will have the same kinetic energy. Which of the following had the largest wavelength? Guys, see, when it comes to, let's suppose you have got alpha particle. In the next chapter, we'll have to see what is alpha particle. Alpha particle is made up of two protons and two neutrons. Okay. And we say a proton. And we say a neutron. Okay. And we say an electron. Guys, always remember, mass of alpha particle is greater than mass of neutron is greater than mass of proton is greater than mass of electron. Now it says that all the four has same kinetic energy. Kinetic energy is same for all. In the question it is saying, what will be the de Broglie's wavelength? Guys, can I say as when it comes to lambda, we say lambda is equal to h upon under root of 2m into energy, 2m into ke. H is same for all the four, E is same for all the four, 2 is same for all the four. So lambda is inversely proportional to mass. The one which has got more mass will have less de Broglie's wavelength. So can I say lambda for alpha particle is less than lambda for proton, lambda for neutron is less than lambda for proton is less than lambda for electron. So electron will have the largest wavelength. So electron will have the, so lambda E is large. Find the ratio of the velocities of the proton and alpha particle if the de Broglie's wavelength of both the particles is same. Guys, when it comes to the alpha particle, always remember, when it comes to its mass is 4m. Okay, its mass is 4m. So 4m means mass times 4 times mass of proton, because alpha particle is made up of 2 protons plus 2 neutrons. We say almost proton and neutron almost have same mass, so it has 4 times mass. And then if you are talking about a proton, okay, so proton mass is how much? Mass of proton is m. Now guys, tell me, when it comes to the lambda of alpha particle, it says lambda of proton is same. The ratio of velocities of the proton and alpha particle both have got the same de Broglie's wavelength. It says de Broglie's wavelength of alpha particle is same as the de Broglie's wavelength of proton. Okay. Now how can we write this? H divided by mv, and mass in this case, H divided by m. Mass of alpha particle. Mass is 4 times mass of proton, okay, into velocity of alpha is equal to de Broglie wavelength of proton, h upon mass of proton into velocity of proton, h mm. So take it over there, velocity of proton divided by velocity of alpha, 4:1. So this will be the ratio of velocities. This is an important question which was asked previously. An electron of mass m and a photon has the same energy. You have got an electron. You have got an electron. You have got a photon. Okay? Both have got the same energy. The ratio of de Broglie's wavelength associated with the electron and the photon. You have to find the de Broglie's wavelength of electron. You have to find the de Broglie's wavelength of electron, photon, then you have to divide them. Guys, see, when it comes to the lambda of electron, how do we find? H upon under root of 2m into energy is given as E. This is the de Broglie's wavelength in terms of energy. Now for a photon, guys, we use this formula. Energy of a photon is equal to hc divided by lambda. Always remember, this lambda is de Broglie's wavelength. Here we do not use this one. This is the energy of photon in terms of kinetic energy. Here for photon, we use this. So I can say here, lambda of this photon, ph, it will be equals to, that is, lambda of this photon, it will be equals to, that is, hc divided by E. Because they say both have got the same energy. Now, what if I tell you divide the two? So lambda E divided by lambda P, this will come out to be. So it will be h upon under root of 2m into E multiplied by this. E upon, we can say, hc. Now h and h will cancel. Do one thing. Multiply with root 3, root E, and divide with root E. This root E, take a look over here. This root E into root E becomes E, that will cancel with this E. So lambda of E divided by lambda of P, it will come out to be, in the numerator you have root E. Okay, in the denominator you have, this is 1 by C also, and you have under root 2m. We'll be writing it something like this, 1 by C under root of E divided by 2m. Or you can write it something like this also, 1 by C, instead of root, you put its value, E divided by 2m whole raised power 1 by 2. E divided by 2m whole raised power 1 by 2, 1 by C. Option A. Is this clear? Now guys, next chapter we have got over here, that is atoms. Now we need to study atoms. Okay. We'll take the break at 6 o'clock, 6 p.m. Now take a look. So the first topic of this atoms chapter is basically what? It is Thomson's model of atom. So in this atoms chapter, we'll have to study different models of atom. Like you have Thomson's model of atom, Rutherford's model of atom, Bohr's model of atom. So different model of atom you need to study. Okay. So in this particular case. Now guys, understand one thing very carefully. When it comes to the Thomson's model of atom, Thomson was the first guy who came up with the model of atom. So he said atom is like a watermelon. Like you have watermelon. Inside the watermelon, you have got the seeds. Okay, these are the seeds that we actually eat. These are the seeds and this is the red portion that we actually eat. So these seeds basically represent the electrons. Seeds represent the electrons, and the red portion represents the positive charge. And he also said atom is electrically neutral. Electrically neutral means number of positive charge is equal to the number of negative charge. Okay. And he also said in an atom, positive charge and mass of the sphere is uniformly distributed. Positive charge and mass of the sphere is uniformly distributed. Like positive charge over here, it is not like, sir, positive charge here will be more and positive charge here will be less. No, it is uniformly distributed. Amount of positive charge here, amount of positive charge here. Similarly, mass is also equally distributed. Okay. And he said an atom is a sphere of radius 10 raised power minus 10 meters. Then you have, so this was basically the Thomson's model of an atom. Then you have the Rutherford's model of an atom. Rutherford's model of an atom. See, what does Rutherford's model of an atom actually say? Guys, see. So Rutherford did not basically came up with the theoretical model. He performed an experiment. Rutherford basically performed an experiment to prove the model of an atom. That is what we call the alpha particle scattering experiment. Rutherford performed an experiment, that is what we call the alpha particle scattering experiment. Okay. So with the help of this alpha particle scattering experiment, he came up with his model. So he basically took a source of alpha particles. Guys, this is what we call the source of alpha particles. This is the source of alpha particle. Source of alpha particles mean out of which, from which the alpha particles are coming out. So it is that source from which the alpha particles are coming out. Alpha particles are coming out from the source. Okay. Yes. Now, my dear friends, understand one thing very carefully. So these are the alpha particles which are coming out. This is what we call the beam of alpha particles. Beam of alpha particles. Okay. And then he placed a gold foil over here. This is the gold foil which he placed over here. Now, guys, he observed that all the particles are directly crossing this gold foil. And this is the deflection screen. And these are falling on the screen. And these are falling on the screen. These are falling on the screen. Okay. So these are not getting deviated. Maximum number of alpha particles are directly crossing and falling on the screen. Okay. Now, guys, in this particular case, we say this gold foil is made up of atoms. So basically, it is crossing the gold foil and falling on the screen. So you observed that 99.86% alpha particles are directly crossing the gold foil, falling on the screen. Only 0.14% were deviating. That means 1 in 8,000 alpha particles was getting deviated. If you are sending 8,000 alpha particles, only 1 is deviated. Only 1 is reflected back. Okay. What does this actually indicate? This actually indicate that this atom, if guys understand one thing, if according to the Thomson, the positive charge is present in the whole atom, okay, if according to the Thomson positive charge is present in the whole atom, then if you send an alpha particle, we say it will be deflected, it will be deviated. Why? Because alpha particle is also positively charged. So if you send this alpha particle over here, which is positively charged, it will be deviated. Why? Because this positive charge will repel it. It will not cross directly. So, but all the alpha particles are crossing directly. So means positive charge is not present in the entire atom. But we can say positive charge is present at a unique position, that is center. That is what we call the nucleus. This unique position is what we call nucleus. Okay. Now, if you send an alpha particle something like this, so it will be directly crossing. If you send an alpha particle, something like that, it will be directly crossing. If you send an alpha particle, it will be directly crossing. But if you send that alpha particle, which is along the center, which is along the nucleus, it will be reflected back. That is this one. 1 in 8,000 alpha particles will be reflected back. So what does Rutherford say? Rutherford said, positive charge is present at a unique position at the center, that is called the nucleus. That is called the nucleus. Okay. Okay. And. So according to this model, positive charge is concentrated at a unique position called nucleus. And electrons are revolving around the nucleus, but are not randomly distributed. Here I would mention this one. And electrons are revolving around the nucleus. Around the nucleus. In random orbits. Around the nucleus in random orbits. Okay, not in a fixed orbit. Like you say, sir, electron is revolving in this fixed orbit. No, it can revolve in any orbit around. Orbit means if there's a nucleus around the nucleus, it can revolve in any orbit, in any path. Okay, this is the graph between number of alpha particles crossing versus theta. We say at theta is equal to 0 degree. Let's suppose this is the atom. So at 0 degree means it is crossing directly. How many number of electrons or alpha particles are crossing? Okay, so all the alpha particles are crossing. So that's why at theta is equal to almost 0 degree. All the alpha particles are crossing. Which one is reflecting back? Only one alpha particle is reflecting back at an angle of 180. That's why at an angle of 180 you are getting very less particles. Okay. Now guys, drawbacks of Rutherford's atomic model. See, what are the drawbacks of Rutherford's atomic model? Drawbacks of Rutherford's atomic, it could not explain the stability of an atom. What does that mean? Guys, see, Rutherford said an electron is revolving around the nucleus. Okay, so electron is revolving means charge is revolving, because electron has got charge. Charge is revolving means charge is accelerating. Why? Because when a particle moves in a circular motion, it has acceleration called centripetal acceleration. Centripetal acceleration will be always there. So charge is accelerating. If charge is accelerating means electromagnetic wave is produced. Whenever charge accelerates, in that particular case, a wave is formed that is called electromagnetic wave, because accelerated charge is the source of electromagnetic wave. When electromagnetic wave is produced, means energy is radiated. Guys, this is the light. You say, this is the electromagnetic wave coming out of this light source. So means this is the energy being radiated. Energy is released. Now guys, if an electron revolves around the nucleus, means charge is revolving, means charge is accelerating, means EM wave is formed. If EM wave is produced, means energy is released. So if this is losing the energy, radiating the energy, so after some time it will be attracted by nucleus, it will collapse into the nucleus. So means atom is unstable. If electron falls into the nucleus, means atom is unstable. But we know atom is a stable system. Electron does not collapse into the nucleus. When people asked him these questions, he couldn't answer. He couldn't answer. Okay, people asked him, you are saying electron is revolving around the nucleus. If it is revolving, it is losing the energy. It will collapse into the nucleus. Okay. Okay, electron is collapsing into the nucleus. So give us the answer. But electron does not collapse into the nucleus. Electron keeps on revolving. So he couldn't answer this. So that's why it became his drawback. That's why it became his drawback. Then comes the Bohr's model of an atom. Then comes the Bohr's model of an atom. And before Bohr's model, I think we should take a break. Okay. So what does Bohr's model say? Bohr's first postulate. This is the first postulate. Bohr's first postulate simply says, yes, we'll take a break. Bohr said electron is revolving. Yes, agreed. Electron is accelerating. Yes, agreed. Charge is accelerating. Agreed. Forms wave. Agreed. But which wave? Not electromagnetic wave. It forms the stationary wave. This is the difference. It forms stationary wave. Stationary wave is that wave which does not radiate the energy. Hence, an electron while revolving forms the wave but does not lose the energy. If it does not loses the energy, it will keep on moving. It will keep on moving. Okay, it will keep on revolving. Hence, atom is a stable system. It does not collapse into the nucleus. Hence, atom is a stable system. It does not collapse into the nucleus. Hence, electron does not collapse and atom is a stable system. Okay, now guys, we'll be taking the break. Break till was the time? 6:30. We're taking the break till 6:30. Okay, see you guys at 6:30. Check.
Now, guys, let's take a look over here at the Bohr's second postulate. Generator karwa. Let's take a look at the Bohr's second postulate, guys. I hope everybody has joined back. Okay, take a look, guys. When it comes to Bohr's second postulate, what does Bohr's second postulate actually say? We say Bohr's second postulate defines the stable orbits. Bohr's second postulate defines the stable orbits. Now, guys, see. It says an electron revolves all around the nucleus. An electron revolves around the nucleus only in those orbits for which its angular momentum is some integral multiple of nh by 2 pi, nh by 2 pi. What does that mean? What does that mean? It means that if I'm saying an electron is revolving around the nucleus, if I'm saying this is the electron which is revolving around the nucleus, this is the electron which is revolving around the nucleus. Okay. And my dear friends, if the angular momentum of this electron in this nucleus is nh divided by 2 pi, then it will be revolving in this nucleus, that is for sure. If angular momentum is not equal to nh by 2 pi, then it cannot revolve in this nucleus, that is what it is saying. Okay, where n can be, like it is mentioned over here, 1, 2, 3, and so on, and so on. If let's suppose n is equal to 1, you guys can say it will be h by 2 pi. So if somebody asks you from now onwards, if an electron is having the angular momentum h by 2 pi, will it be revolving in a nucleus? Yes. If an electron is having 2h by 2 pi, will it be revolving in a nucleus? Yes. So 3h by 2 pi, yes. Okay. So basically an electron does not revolve in the random orbits. Electron revolve in the stable fixed orbits. So electron revolve in the fixed orbits. Fixed orbit. We say only in those orbits in which its angular momentum is, we say nh divided by 2 pi. So not in the random orbits. Let's suppose if I say, check if the electron is revolving in, I can say in this particular case, that is 3h divided by 4 pi. 3h divided by 4 pi. You'll be saying, sir, put this is equal to nh divided by 2 pi. h pi, 2 ones are 2 twos are. So n will come out to be 3 divided by 2. That is 1.5. So we say no. So it has to be integral multiple of nh by 2 pi. N can be 1, 2, 3, 4. N cannot be 1.5. So an electron will not revolve in this orbit. In this orbit, where its angular momentum is how much? That is 3h by 4 pi. So it can revolve only in these orbits. That is what we call the Bohr's second postulate. Then you say Bohr's third postulate. What does Bohr's third postulate actually say? See, it says that, let's suppose if an electron is revolving in the higher orbit, in this higher orbit, okay? Now, if it makes the transition from higher orbit to the lower orbit, if it makes the transition from higher to the lower, in this case, energy is, a photon is released. In this case, energy is released. Energy is released in the form of a photon. In this case, energy is released in the form of a photon. So if an electron makes the transition from higher orbit to lower orbit, we say electron is released. And if an electron makes the transition from lower orbit to higher orbit, then we need to supply the energy to it. Then only it can make the transition from lower orbit to the higher orbit. An electron
Oh. Guys, an electron, if it makes the transition from higher orbit to lower orbit, in that particular case, okay, in that particular case, I would say energy is released. Energy is released what? In the form of a photon. A photon is released. Okay. And if you have to make the transition from lower to higher orbit, in that case, you need to supply the energy in the form of a photon. Okay. So this is what we call the Bohr's third postulate. This is what we call the Bohr's third postulate. Then you have the mathematical analysis of Bohr's theory. Then you have the mathematical analysis of Bohr's theory. See, guys, the first thing that we need to understand over here is that is velocity of an electron in the nth orbit. What is this? If I'm saying you have got an electron over here, and at the center of the, if you have got an atom over here, this is the atom, okay? At the center of the atom, you have the nucleus. And this nucleus has got the charge of Zd. Zd is the charge on the nucleus. An electron is revolving around the nucleus. And if I say this electron has got the velocity b, somebody asks you, if it is revolving in the nth orbit, this is the nth orbit. This orbit which is given over here is nth orbit. So how much is the velocity of this electron in this nth orbit? So you'll be simply saying the velocity of this electron in the nth orbit is 2.2 into 10 raised power 6 Z by n. 2.2, just a second, guys. So you have over here 2.2 into 10 raised power 6 Z by n. And this 2.2, you can say in this particular case, that is V naught Z by n. That is V naught Z by n. What is Z? Z is the atomic number. Guys, what is Z? I'll write over here where Z is the atomic number. Okay. For hydrogen, Z is equal to 1. For helium, Z is equal to 2. For lithium, Z is equal to 3. Okay. So for different atoms, we have different atomic number in that particular case. Okay. And one more thing I just want to tell you over here. What is that? That is n means which orbit? If you're talking about the fifth orbit, n will be 5. So this is the velocity of an electron in the nth orbit. Then you have radius of an electron in the nth orbit. Okay. You have got the radius of an electron in the nth orbit. If an electron is revolving in the nth orbit, okay, how much will be this radius? Guys, directly remember, this radius is 0.53 angstrom n square by z. Okay, n means which orbit you are talking about. Z means atomic number. And instead of this, you can write R naught over here. Now, guys, let's suppose we have got a question. Find the radius of Li2 positive ion. In its ground state, assuming Bohr's model to be valid. Now see, we are supposed to find for Li2 positive. Guys, always remember Z is equal to 3. Atomic number is 3. For helium, it is 2. Now, guys, in this particular case, you are supposed to find the radius. Radius is R naught n square by Z. Okay. Now, it is saying that ground state. Ground state means first orbit. So, means n is equal to 1. So, R is equal to, you can say 0.53 angstrom into 10 raised power minus 10. Then you can write over here n square. N will be 1 divided by 3. So, R will come out to be 0.53 into 10 raised power minus 10 divided by 3. Do the more calculation from your end. Simply. Next you have over here, find the maximum angular speed of an electron. of a hydrogen atom in the stationary orbit. See guys. Listen to me very carefully. What does it say actually over here? Find the maximum angular speed of an electron. Guys, let's suppose this is a hydrogen atom, okay? And electron is revolving in a hydrogen atom. Electron is revolving in a hydrogen atom. This is a hydrogen atom, electron is revolving here. Okay, this is the nucleus. And electron is revolving in the first orbit, n is equal to 1. Stationary orbit means first orbit, ground state. And for this hydrogen atom, Z is equal to 1. Okay, guys, we say in this particular case, this will be the radius, this will be the velocity of the electron. Guys, it says the angular speed. Angular speed means omega. Omega. We said to find omega here. We need to find omega. We need to find omega. Okay, guys, always remember, we know V is equal to R omega. This is the relation between linear velocity and angular velocity. Here you can say this angular velocity divided by V is equal to V divided by R. Omega will be V by R. Now omega is equal to, guys, what is the value of V? That is 2.2 into 10 raised power 6 Z by N upon, what is the value of R? 0.53 into 10 raised power minus 10, or you can write as of now, angstrom N square divided by Z. Just you need to put the values. Omega is equal to, this is 2.2 into 10 raised power 6. Z is how much? It is talking about the first orbit, 1 by 1. It is 1 by 1 upon 0.53 into 10 raised power minus 10, 1 by 1. Okay, because 1 square by 1 square. Now guys, this will be omega is equal to 2.2. So 2.2 divided by 0.53 into, this will be 10 raised power 16. Okay, this will be rad per sec. Do the calculation more from your end. Next you have this one. That is the time period of the revolution of an electron in the nth orbit. Guys, see, if I'm saying in this particular case, an electron is revolving in the nth orbit. Okay, this is the electron which is revolving in the nth orbit. How much time an electron takes to complete one cycle? How much time an electron takes to complete one cycle is called the time period. Time period means the time taken by an electron to complete one whole cycle. Okay, and that is 1.51 into 10 raised power minus 16 n cube by z square. N cube by z square. This will be the time period. One more thing, magnetic field at the center of an electron due to a revolving electron. Always, I have told you in the magnetism also. Guys, if an electron, let's suppose this is the nucleus, this is the electron which is revolving. If an electron is revolving, we know, sir, charge is revolving, so means current is being produced. So current is produced in a loop over here. So a current carrying loop produces the magnetic field at the center. We say due to the revolving electron, magnetic field is produced at the center. And the value of that magnetic field will be simply B is equal to B naught Z cube by N raised power 5. Z cube by N raised power 5, where B naught is 9.27 into 10 raised power minus 24 joule per Tesla. Okay, this is the value of that magnetic field which is being developed due to the, because a revolving electron creates current. A current carrying loop produces the magnetic field. Now guys, total energy of an electron in the nth orbit. Guys, always remember, if this is the nucleus, ZE, charge on the nucleus is ZE. Z means the atomic number. Okay. Charge on the nucleus is ZE. Guys, see, this is the electron revolving. This is one charge, this is another charge. I have told you previously in electrostatics, if you have two charges, this is Q1, this is Q2. They are separated by some distance. They will have potential energy. That is K, Q1, Q2 divided by R. Similarly, here you have two charges. They are separated by some distance, so they will have potential energy. They will have potential energy. That is equal to minus Z E square upon 4 pi epsilon naught R. E is the charge on an electron. Z is the atomic number. If this is hydrogen, atomic number is 1. Okay, 4 pi epsilon naught R. R is the distance between the two. R is the distance between the two. Okay, this R is the distance between. Now guys, this is the potential energy. When it comes to the kinetic energy, we said this charge is moving with a velocity v. Guys, remember, whenever any mass moves, charge, it has mass m, velocity v, it will have kinetic energy, because whenever a mass is in motion, it has kinetic energy. And this charge will have kinetic energy. This electron has kinetic energy, Z E square upon 8 pi epsilon naught R. 8 pi epsilon naught R. Okay. Okay. And total energy. Guys, simply remember, when it comes to the total energy, it is kinetic energy plus potential energy. It is kinetic energy plus potential energy. So when you join this kinetic energy, when you join this potential energy, it will form kinetic energy. It will form total energy. And total energy is exactly in this particular case minus Z square upon 8 pi epsilon R. Whatever is the value of kinetic energy, same as the value of total energy. This is positive, this is negative. Positive and negative. Okay. Positive and negative. Now guys, I would want you guys to understand from the graph. Guys, if somebody asks you, make the graph between energy versus time. Guys, take a look. Kinetic energy is inversely proportional to R and is positive. So means graph of kinetic energy will be from the upper side and it is rectangular hyperbola. And then you check over here. Potential energy is inversely proportional to R, but it is negative. So the graph of potential energy will be from the lower side. Why it is negative? It will be a rectangular hyperbola. When it comes to the total energy, guys, total energy is also negative and is inversely proportional to R. So it will be also from the lower side. Okay. And it is between, potential energy is between this and this over here. You guys can see in the middle. Why? Because you can check over here. Total energy is minus Z E square upon 8 pi epsilon naught R. Ignore this negative sign. When you check from the lower side, it is Z E square divided by 8. So it will be less from the negative side. Okay. And this is Z E square divided by 4. So it will be, potential energy will be more from the negative side. From the negative side, I'm saying. So total energy is less from the negative side. So this will be, let's suppose, minus 10, minus 15, minus 20, minus 30. So potential energy will be more. That's why this graph is in between. Okay. Is this clear? Is this clear? Now guys, see, take a look here. When it comes to the total energy, you say it is minus Z E square upon 8 pi epsilon naught R. Guys, see. When you put the value of R over here, this is Z E square upon, you say 8 pi epsilon naught, say R naught, then you say N square divided by Z. Okay. Now guys, you will be writing it something like this. Take the z in the numerator. Minus e square upon 8 pi epsilon naught r naught. Okay, this will be n square divided by z. So epsilon naught value you know, r naught value you know, pi you know, charge on an electron you know. When you put all these values, it comes out to be 13.6. It comes out to be 13.6. So we say it will come out to be minus 13.6 n square by z square. This will be the total energy. Minus 13.6 n square by z square. And guys, if we talk about the hydrogen atom, for a hydrogen atom, z is 1. Put z is 1, so it will be minus 13.6 divided by n square. And I have recently told you that total energy is negative of kinetic energy. Whatever is the value of kinetic is same as total, but negative. So, can I say kinetic energy is negative of total energy over here? Yes. So, this, and if kinetic energy is negative, sorry, if total energy is negative, kinetic will be positive. Same. You can check here. Whatever is the value of total energy, kinetic same. This is positive, this is negative. That's why here also, total energy positive, this is negative. Okay. Now, there are some important graphs which I want you guys to remember. What is that? See guys, when it comes to the total energy, it is minus 13.6 z square by n square. It is minus 13.6 z square by n square. Guys, see, if I say z is equal to constant, let's suppose z is equal to constant. Okay, like you are talking about one atom. Okay, this is one atom. For different orbits, z will be same, one constant. If z is equal to constant, and if somebody asks you, plot the graph between energy versus n square, how will you plot? Sir, this is constant, this is constant. Total energy is inversely proportional to n square. Okay, and total energy is negative. So graph will be something like this. Graph will be something like this from the lower side. Where? Oh, yes, it is z square by n square. Sorry. When it goes in the numerator, it will become z square by n. Now, take a look here. If I say graph between energy versus 1 by n square, means total energy versus 1 by n square. On this axis, you are putting 1 by n square. Now, power of this is 1. In this particular case, guys, graph, see, total energy is, we can say directly proportional to 1 by n square. Keep that thing in your mind. Okay. If you're talking about n square only, then it is inversely proportional, but it is directly proportional to 1 by n square. So graph would have been straight line from the upper side. But since here is negative sign, so we'll be making the straight line, but from the lower side. Okay. Yes. Next graph. If I say n is constant, guys, if I consider n constant, now graph between total energy and z square. I can say total energy is directly proportional to z square. Graph would have been from the upper side. Guys, here power of this is 1. If I say graph between total energy versus z, then you can say graph will be something like this. But in this particular case, it is square, so power of this is 1. Since energy is negative, so graph will be from the lower side. E is negative. Straight line. Now guys, if I say energy versus z, energy is proportional to z square. Guys, here, if this energy was positive, I would have made the graph. This is y versus x graph if y is proportional to x square. Your energy is proportional to z square, graph would have been from the upper side. Since energy is negative, graph will be from the lower side. I hope these graphs are important, very important. I hope these graphs are clear. Energy in this case is negative. Okay. Now guys, take a look here. In this particular case, if we see, for a hydrogen atom, first orbit n is 1, second orbit n is 2, third orbit n is 3, fourth orbit n is 4. Okay, first orbit, second orbit, third, fourth. This is called the ground state. This is called the first excited state. This is called the second excited state. This is called the third excited state. You can see a value of n orbit states. Now energy. Guys, how do you calculate the energy? This is very important. We can say total energy is minus 13.6. If we talk about the hydrogen atom, divided by n square, because that is 1. Now for first orbit, n is 1, so it will come out to be 13.6. For second orbit, n is 2, minus 13.6 divided by 2 square is 4. It will come out to be 3.4. For third orbit, n is 3, so minus 13.6 divided by 3 square, it will come out to 1.51. Similarly, you can calculate all of these. Then for the next orbit, it will be 0.56. Okay, now guys, let's suppose you have this question. This is the previous question. The total energy of an electron in an atom in an orbit is 3.4 electron volts. Total energy is given as minus 3.4 electron volts. Its kinetic and potential energies are, guys, when it comes to the total energy, when it comes to the kinetic energy is negative of total energy. That is negative of this minus 3.4 electron volts. So minus into minus is plus. So that will be 3.4 electron volts. When it comes to the potential, we say total energy is equal to potential energy plus kinetic energy. Total energy is minus 3.4 is equal to, this is potential energy plus kinetic energy is 3.4. So take it over there. Minus 3.4 minus 3.4. So potential energy will come out to be minus 6.8 electron volt. So which option? Minus 3.4 plus 3.4 minus 6.8. Option C. Yes. Next. Here the question says, the electron in a hydrogen atom jumps from excited state n is equal to 3 to its ground state. Okay, see guys, an electron jumps from the excited state n is equal to 3 to the ground state. Okay, an electron jumps from n is equal to 3 to n is equal to 1. Okay. Guys, when an electron moves from higher orbit to the lower orbit, always remember energy is released. Energy is released in the form of a photon. Basically, a photon is coming out. And how do we calculate that energy? How much is released? That energy will be, guys, that energy will be, in this particular case, that will be gap between the two, this energy minus this energy. So you will be saying that is this energy in the third orbit minus energy in the first orbit. Okay. Now this energy will be energy in the third orbit. That is how much? Minus 1.51 minus energy in the first orbit minus 13.6. Okay. Now guys, how much it will be? This will come out to be equal to, that is 12.1 electron volts. So a photon is basically released, a photon comes out. This photon has an energy of 12.1 electron volt. Okay, yes. Now guys, Okay. Okay. Now, guys, further it says that, and the photon thus emitted, falls on a photosensitive metallic plate, So this photon which is emitted over here, let me show you something like this. This is the photon which is emitted, something like, okay, and this is the photon. It falls on the photosensitive metallic plate. Okay, this is the metallic plate. It falls on the photosensitive metallic plate. Okay. Now, when the photon falls on the photosensitive metallic plate, work function of this metallic plate is 5.1 electron volts. You guys are supposed to say, guys, if it falls onto the photosensitive metallic plate, electron will come out because photoelectric effect will take place. Okay. Okay. So photoelectric effect takes place. And my dear friends, if photoelectric effect takes place, can I say in that particular case, sir, energy of photon will be equal to the work function plus kinetic energy maximum, that is EV naught. Yes, kinetic energy maximum, we can write EV naught. Okay. Now, my dear friends, energy of photon is given how much? That is 12.1 electron volt is equal. Work function in this case is given as 5.1 electron volt plus EV naught. Now take it over there. 12.1 minus 5.1. This will be 7 electron volt is equal to EV naught. This and this will cancel. V naught will come out to be 7 volt. Okay, so stopping potential in this case will be 7 volt. Consider third orbit of helium. Using non-relativistic approach, the speed of the electron in the nth orbit will be. Okay, guys, for helium, Z is equal to 2. And it says that which orbit it is talking about, third orbit. So N is equal to 3. We are supposed to find the speed of an electron. V is equal to V naught Z by N. So V is equal to 2.2 into 10 raised power 6 Z by N. Z is 2 divided by 3. Simple. Now, guys, hydrogen spectrum. Yesterday, a student had mentioned in the live chat, sir, please teach hydrogen spectrum also in the atoms, because last time I didn't teach this in the last marathon, last year. I hope now that student is watching right now. Sir, can you define why there is a bent in the graphs of energy? Because it is inverse relation. That is why. If you say energy is proportional to Z square, okay, so what will be? We say Y is X. Y is proportional to X square. What is the graph of this curve? Okay. If you say Y is proportional to X only, what will be the graph? Straight line. If you say Y is inversely proportional to X, what will be the graph? Rectangular hyperbola. Now, guys, spectrum. Guys, see, what is the spectrum all about? We say it is the collection of radiations of different wavelengths on a photographic plate. Let me give you an example. Let's suppose you have got a white light over here, okay? And you are taking a prism. I recently taught you this prism will break the white light into 7 different colors, okay? When the white light will enter the prism, it will break into 7 different colors. Okay, this is violet, indigo, blue, green, yellow, orange, red. 7 different colors it will break it. Now, my dear friends, when these lights, okay, when these radiations fall onto this photographic plate, okay, a pattern will be formed. It is an image produced on the photographic plate. So when these fall onto this plate, falling of these radiations on this photographic plate is called the spectrum. Okay, a bright dark pattern kind of will be formed over here. That is what we call the spectrum. Falling of the radiations on the photographic plate. These radiations will have got the different wavelength on a photographic plate. This is what we call the spectrum and nothing else, Now there are 2 types of spectrum. We have absorption spectrum and we have emission spectrum. We have absorption spectrum and we have emission spectrum. Okay. See guys, what absorption spectrum mean? What absorption spectrum mean? Let's suppose I have got an atom over here. And this is the screen in this particular case. Okay. And in this particular case, let's suppose I am sending an electron from this point. Okay, I'm sending an photon. This is a photon. Photon means energy. And electron is revolving in the first orbit. If I'm sending an electron in this particular case if I'm sending a photon to this electron, so could you please tell me what is the gap between this and this first orbit and second orbit? Sir, it is minus 13.6, minus 3.4. So gap will be equal to 10.2 electron volt. So if you are sending a photon of 10.2 electron volt, this electron will absorb this energy, will absorb this photon, and it makes the transition to the higher orbit. Because if you want the electron to make the transition from lower orbit to the higher orbit, you have to supply the energy. And you will be supplying the energy in the form of a photon. Keep that thing in your mind. Okay. Now guys, so when you basically made the transition of the electron from the lower orbit to the higher orbit, now you sent a photon of equal to the energy gap. Now if someone says, sir, I want to make the transition from first to the third, then you set the energy equal to this gap. Okay. Now here, when the transition is made from lower orbit to higher orbit, we say a dark fringe, a dark line is made on the screen. This making of dark line on this bright background, this is called absorption spectrum. Because spectrum itself is the creation of the lines, falling of the lines over here. Okay. So we say here dark line is formed on bright background. So simply absorption spectrum means when the electron makes the transition from lower orbit to the higher orbit. In that case, the lines formed on the spectrum will be absorption spectrum. And here, more specifically, this dark line gives you the idea that this electron has emitted all the energy. That's why we are getting the dark line over here. Then you have got the emission spectrum. Now guys, in case of emission spectrum, if the electron is moving in the higher orbit, if it makes the transition from higher to the lower orbit, we say a photon is released. Now, if this photon falls onto this screen, this is the dark screen over here. Okay. We said this photon, this light falls onto this screen. Now, if the wavelength of this light matches with the wavelength of yellow, then the yellow spot will be created, yellow line will be created. If its wavelength is equal to the wavelength of red, red spot will be created. If its wavelength matches with the wavelength of the violet, violet spot will be created. So we say here, bright line is formed on dark background. So what does this creation of bright light mean? It means that a photon has been released, which means that an electron has made the transition from higher orbit to the lower orbit. Okay? An electron has made the transition from higher orbit to the lower orbit, and due to that a photon is released which falls on the screen, due to which we can say these bright lines are formed. Sir, which color will be formed? It depends upon the wavelength of the photon. Okay. If it matches with the wavelength of the red, red line will be formed. Okay. This is the emission spectrum. So in case of absorption spectrum, electron moves from lower to higher orbit. In case of emission, electron moves from higher to lower orbit. Next. Now guys, you have this Lyman series, Balmer series, Paschen series, okay? P-Fund series, bracket series, all of this series, let me just tell you over here. See guys, since you are saying when it comes to the emission spectrum, electron makes the transition from higher orbit to the lower orbit, okay? A photon is released, thus a photon is released, which falls on the screen. A photon is released, which falls on the screen, okay? Now guys, I told you this photon will have the wavelength lambda, yes. And it forms the line over here, yes. Now my dear friends, if you have to show this in the Lyman series, we say in Lyman series, when an electron makes the transition from higher orbit to first orbit, we show it on Lyman series. It is a not exact thing that I'm saying. It is a kind of, I would say, a graph. Sir, an electron makes the transition from higher orbit to the lower orbit. Now in Lyman series, we will represent it with this line. If I'm saying it has made the transition from 5 to 1, so make this line. So this line, when you see this line over here, in this particular case, you will get to understand that, sir, an electron has made the transition from n is equal to 5 to n is equal to 1. So means a photon has released. That photon has a wavelength. And that releasing of photon, we are representing over here with this line. Now, if somebody says, sir, an electron has made the transition from third to first, we show it with this line. An electron has made the transition from n is equal to 3 to 1, we show it with this line. That's why we say, in Lyman series, if the electron makes the transition from higher to the first orbit, then we show it in the Lyman series. Sir, what about Balmer? In Balmer series, when an electron makes the transition from higher to the second orbit, we show it in the Balmer series. Okay. Representing basically the transitions of the electrons from the higher orbits to the lower orbits, to the first orbit. Okay. See guys, in this particular case, take a look. If an electron makes the transition from second orbit to the first orbit, means it's a Lyman, we show it in the Lyman series. This is what we call the first line of Lyman series. Guys, in this Lyman series, we represent the orbits with the help of straight lines. This is the orbit n is equal to 1. Second orbit, third orbit, fourth, fifth, and as infinity. Okay. Now guys, if electron moves from second orbit to the lower, we show it with this line. First line, this is also called K alpha. If electron moves from n is equal to 2 to n is equal to 1, this is also called K beta, second line. If electron moves from n is equal to 3 to 1, this is called K gamma, third line. Okay. and so on. Okay. Now, my dear friends, in this particular case, then you have the Balmer series. Balmer series. Guys, tell me one thing. When it comes to the first line, could you please tell me what is the energy of this first line? Energy of the first line, it means that if an electron moves from second to first, so how much energy is released? Energy equal to the energy gap. That energy will be the energy of the first line. Tell me, is this energy maximum or this energy is maximum? I can say for first line, energy is minimum. Why? Because minus 13.6 minus 3.4. 13.6 minus 3.4, 10.2. This energy gap is more. So this has got minimum energy. And we say energy is equal to, I'll write over here, for first line. Guys, we say energy is minimum. And we say energy is equal to H into F. If energy is minimum, frequency is also minimum. Okay. And when it comes to the wavelength, we say energy is equal to Hc divided by lambda. So if energy is minimum, wavelength is maximum. Wavelength is maximum. Keep that thing in your mind. So my dear friends, so for the first line of Lyman series, energy is minimum, frequency is minimum, wavelength is maximum. But for the last line, energy is maximum, frequency is maximum, wavelength is minimum. Let's come on to the Balmer series. Let's suppose an electron makes the transition from higher orbits to the second orbit. So in this case, we say, mention this also, we say final orbit is 1, initial orbit is 2, 3, 4, and so on up to infinity. Here, if an electron makes the transition from higher orbit to the second orbit, we will represent it, we'll show it in the Balmer series. Okay, so can I say here, n initial is 3, 4, 5, and so on up to infinity, and n final in this case will be 2. N final will be 2. N final will be 2. Okay. Now, my dear friends, N final will be 2. N initial will be this. In this case also, this first line will have maximum wavelength, minimum frequency, minimum energy. So this is the first line of Lyman series. Second line, third line. L alpha, or this is also called L series. L beta, L gamma. Similarly, you have got Paschen series. In this particular case, N final is 3, N initial can be 4, 5, 6 up to infinity. Okay. And my dear friends, when it comes to this Paschen series, when an electron makes the transition from higher to the third, this is the first line. It will have maximum wavelength, minimum frequency, minimum energy. I have already discussed. Second line, this is called M series. M alpha, M beta, M gamma. Okay, this you can see over here. And then you have P fund series, okay, bracket series, Humphrey series, okay. Now, take a look. Let's suppose if I'm saying an electron makes the transition from higher to the lower orbit, you show it with a line, okay. Now that line, that transition will have the wavelength, okay. I'm saying, guys, if an electron makes the transition from the higher orbit to lower orbit, photon is released. This photon will have the wavelength. And what is the wavelength of this photon? How to calculate the wavelength of the photon? Wavelength of the photon emitted. This will be equals to 1 by lambda. This 1 by lambda is called wave number. Lambda itself is called wavelength. This is R. R means Rydberg constant. 1 by n final square minus 1 by n initial square. Let's suppose you have to find the wavelength of a photon, which makes the transition from 4 to 1. So we can say n final is 1, n initial is 4. And value of Rydberg constant is 1.03 in 10 raised power 7 meter inverse. Like, let me show you the question. This question was asked in NEET 2017. See the question. The ratio of wavelength of the last line of the Balmer series. The ratio of wavelength of the last line of the Balmer series and the last line of the Lyman series. Guys, see. Last line of Balmer series. Okay, last line of Balmer series. Let's talk about Lyman series first. Guys, last line of Lyman series will be, understand this very carefully. So means n initial is 1. N final is equal to infinity. Because when you talk about the Lyman series, in case of Lyman series, last line is when an electron makes the transition from infinity to 1. Okay, this is the Lyman series. So n final is 1, n initial is infinity. Okay. Okay. Now in this particular case, I want you to understand one thing. Guys, if you want to find the wavelength of this, 1 by lambda is equal to r. R is Rydberg constant. 1 by n final square. N final is 1 square. Minus 1 by infinity. So 1 by infinity is 0. So 1 by lambda will come out to be r. Do the reciprocal. R lambda will come out to be 1 by r. Okay, let's call it lambda 1. Now it says that when an electron makes the transition from, okay, last line of the Balmer series. Balmer series. Guys, can I say final orbit in the Balmer series is 2, initial orbit will be infinity. So if you want to find 1 by lambda will come out to be, so it is r, then 1 upon 2 square, that is 4, minus 1 by infinity. Okay, so this will come out to be 1 by lambda 2 will come out to be r by 4. So do the reciprocal, lambda 2 will come out to be 4 by r. Now you have to find the ratio. So lambda 1 divided by lambda 2. Lambda 2, it is 1 by r upon 4 by r. Okay. So this will come out to be 1:4. Is that clear? Lambda 1 by lambda 2. Last line of the Balmer and the, okay, we are supposed to find lambda 2 by lambda 1. Lambda 2 by lambda 1 will be 4:1. Value of Rydberg constant is this. 1.03 in 10 raised power 7 meter inverse. R is Rydberg constant. Is that clear? So with this, I have covered every single topic of the atoms also, of dual nature and matter and radiations also. Now you have nuclei. I'm not leaving any of the topics, okay? But in some points, being very honest, some points, not the topics, some points in ray optics I skipped because then it will take a lot of time, which are not important. But when it comes to the modern physics, when it comes to the wave optics, everything I covered. Okay. Now guys, take a look. Nuclei. Nuclei. Now, previously when it comes to the chapter atoms, over there we studied atoms as a whole. But when it comes to the center of the atom, we know at the center of the atom, there is nuclei. Okay, there is nuclei. And now we have to study this nucleus. Now we have to study this nucleus. Okay. Now we have to study this nucleus. Okay, which is present at the center of the atom. Which is present at the center of the atom. Now guys, see, in this particular case, when it comes to this nucleus, if somebody asks you, what is present inside the nucleus? All of you will say that inside the nucleus, you have got protons, you have got neutrons. The particles present inside the nucleus are protons and neutrons. And these protons have got positive charge. When it comes to the protons, protons are those particles which have got positive charge. And these neutrons are neutral. They have got no charge. And one more thing I want to say over here. Radius of the atom is 10 raised power minus 10 meters. Radius of the nucleus is 10 raised power minus 15 meters. 10 raised power minus 10, 10 raised power minus 10, 10 raised power minus 15. Now guys, the particles which are present inside the nucleus are called nucleons, hydrons or baryons. So these protons and neutrons are considered as hydrons, nucleons, baryons, because they are present inside the nucleus. And outside the nucleus, electron is revolving. Representation of a nucleus. Let's suppose, guys, you have a nucleus over here. Okay. You want to represent it. We represent a nucleus with a letter. Let's suppose X. On top of it, we write A. At the bottom, we write Z. What does A mean? A means mass number. Mass number means number of protons, number of neutrons, plus number of neutrons. Z means atomic number, number of protons. Like you have got a nucleus. Let's suppose you have a nucleus over here. Inside this nucleus, you have 3 protons. You have got 3 neutrons. So I can write this as X. For this nucleus, I can write over here X. Okay. And at the top, I can write over here 6. Why? Because number of protons plus number of neutrons is 6. A is 6, mass number. And Z is number of protons, that is only 3. Even if somebody asks you how to calculate the number of neutrons, that is A minus Z. Total minus protons. Total minus protons. Okay. Now you have few different particles. That is what you need to understand over here. The first one is neutrino. Okay. Neutrino, it is a neutral particle. And when it comes to the net charge of this particle, it is 0. Okay. Net charge of this particle is 0. Neutrino. Okay. And when it comes to the mass of this is much less than mass of electron. Almost you can say it is massless, because mass of electron itself is very small, so you can consider this as a massless. It's very small. Then you have alpha particle. Alpha particle is made up of 2 protons plus 2 neutrons. 2 protons plus 2 neutrons. When it comes to the charge, net charge, guys, proton has charge E, electron has charge minus E, proton has charge plus E. That is 1.6 into 10 raised power minus 19. It is negative for electron. For proton, it is positive. Charge on this is, we say 2E, because protons have got E charge, 2 has 2E. Neutron has got no charge. When it comes to the mass is 4 times mass of proton. Why? Because 2 proton and neutron has same mass. So 2 protons has got 2m, 2 neutrons has 2m. 2m plus 2m is 4m. Then you have beta particle. We say it is an electron beam of electrons, or fastest moving electron. So if there are different number of electrons moving, we can call it the electron beam, or you can call it the beta particle. Okay. And in this particular case, you can say charge same as electron. Charge same as electron. Then positron. We say it is the antiparticle of electron. Antiparticle of electron. What does that mean? That means it is the opposite of electron. Okay, electron has got negative charge. Positron will have got positive charge. So Q in this case is positive. Okay, and it is plus E. Okay. Sir, what about mass? Its mass is same as electron. Mass same as electron. Sir, what is the difference between proton and positron? Mass of proton is very large as compared to the positron. But charge of positron is same as the charge of proton. Okay. Next. Then you have the quarks. Sir, quark means we say proton and neutron are made up of quarks. Proton and neutron are made up of quarks. Proton and neutron are made up of quarks. Okay. Proton and neutron are made up of quarks. When it comes to the proton, guys, when it comes to the proton, it is made up of UUD. Now, first, let me just tell you here. See, there are 6 types of quarks. Up quark, down quark, top quark, bottom quark, beauty quark, charm quark. Charge on this is plus 2 by 3, plus 2 by 3, plus 2 by 3. E is the charge on an electron or proton. This is 2 by 3E, not E, 2 by 3. Charge on down quark is minus 1 by 3, minus 1 by 3, minus 1 by 3. A proton is made up of UUD. 2 up quarks, 1 down quark. 2 up quarks and 1 down quark. And when it comes to a neutron, it is made up of DDU. Neutron. I can say in this particular case, this is D, D, and this is U. 2 down quarks, 1 up quark. 2 up quarks, 1 down quark. Next. You have got rest mass energy. This concept. Now, guys, take a look. Rest mass energy. Let's suppose, my dear friends, you have a mass over here. Okay, this is mass M. And this mass is moving with a velocity v. This mass is moving with a velocity v. Okay? Yes. This mass is moving with a velocity v. Now, my dear NEET aspirants, I say due to the motion of the particle, it has kinetic energy, and that kinetic energy is simply 1 by 2 mv square. Due to the motion of the particle, it has kinetic energy, and that kinetic energy is simply 1 by 2 mv square. So 1 by 2 mv square is the kinetic energy of this particular particle. Now take a look. Now take a look. Rest mass energy. And let's suppose you might have studied this also. Sir, if this is an object which you place at an height h, we say its mass is m. It is at height h. We know its potential energy will be mgh. Due to the height, it has potential energy. Now, due to the mass of an object, it has energy associated with it. That is called rest mass energy. Due to the motion of an object, it has energy associated with, that's kinetic. Due to the mass itself, sir, this object has mass. Does it have energy? Yes. Which one? Rest mass energy. That rest mass energy is equal to E is equal to mc square. E is equal to mc square is the rest mass energy. Like this was the question which was asked in NEET 2020. Question says that the energy equivalent of 0.5 grams of a substance is, you have got a mass over here that is 0.5 grams. You are supposed to find how much energy is associated with, how much energy is present in this one. Now I can say E is equal to mc square. So I can say E is equal to, mass is 0.5. It's in grams. Okay, so multiplied by 10 raised power minus 3. If you write it in kgs, into mc square. C is 3 into 10 raised power 8, its whole square. Energy will come out to be 0.5 into 10 raised power minus 3. This 3 square is 9 into 9 into 10 raised power 16. 8 square is 16. Okay. Now tell me guys, in this particular case, what can we write? Okay. So this you can write over here. E is equal to 5 into 10 raised power minus 4. And 10 raised power minus 4, 10 raised power 16. So it will become 10 raised power 12 into 9 into 10 raised power 12. Okay. Now guys, this is 45. So you can write it 4.5 into, or you can write it something like this. E is equal to 45 into 10 raised power 12. Okay. Or you can write 4.5 into 10 raised power 13 joules. 4.5 into 10 raised power 13 joules. Okay. Because this is the only option which is matching. Now take a look here. Nuclear size / size of nucleus. Nuclear size / size of nucleus. Guys, smash the like button if you have not liked this session yet. Now guys, take a look. MPC student. What is MPC? MPC student. Guys, see. Nuclear size of nucleus. let's suppose you have got a nucleus over here. Okay. You have got another nucleus over here. We say size of this nucleus, see. If I am saying these are the nucleons present inside the nucleus, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So its mass number is 10. Its mass number is 5. If I say more is the mass number of the nucleus, bigger is the size of nucleus. Obviously, less is the mass number of nucleus, less is the size of nucleus. Obviously, if you have more number of nucleons, you would need bigger nucleus, and here you would need smaller nucleus. Now guys, can I say mass number is directly proportional to the size of nucleus, or size of nucleus, or volume of nucleus is directly proportional to the mass number? Yes. So I can say in this particular case, guys, understand this very carefully. Volume of nucleus is directly proportional to the mass number. More is the mass number, more will be the volume, means size. So we can say volume is proportional to, and what is the volume of the nucleus? It's the sphere. 4 by 3. It is 4. So 4 by 3 pi r cube is proportional to A. 4 by 3 pi is constant. So R is proportional. Take this cube over here, A raised power 1 by 3. So we can say R is equal to R naught, A raised power 1 by 3. What is R naught? R naught is basically the constant over here. What is R? R is the radius of the nucleus. R is the radius of the nucleus. Okay. So mass number is proportional to A raised power 1 by 3. And value of this R naught is around 1.2 angstrom. So this R naught is around 1.2 angstrom. Please do check it from your end also, okay? Because sometimes I forget. Now guys, now you have, this is the radius of nucleus, means size of nucleus, okay? How to find the size of nucleus, radius of nucleus? R naught, A raised power 1 by 3. I'll show you the questions on this one also. You have got nuclear density. What does nuclear density mean? Density of nucleus. Simply. Density of nucleus will be mass of proton divided by volume of V naught. Guys, see. What is this? When it comes to the density of nucleus, guys, what is density? It is mass divided by volume. Mass divided by volume. Mass of nucleus divided by volume of nucleus. Guys, if you have nucleus in which there are, let's suppose, in which mass number is, it has mass number A. Could you please tell me, and mass of proton is MP. Could you please tell me what is the mass of the nucleus? You say mass of the nucleus. If it has 10 nucleons, 10 MP. 5 nucleons, 5 MP. A nucleons, A MP. Divided by volume of nucleus. We say volume of nucleus is proportional to the mass number. So we can say V is equal to V naught into A directly. So V naught into A. A and A will cancel. So it will be MP divided by V naught. If you put the values of these two, it will come out to be density of nucleus as 10 raised power 17 kg per meter cube. And it is constant. It is constant. It does not depend upon the mass number. It is same for all the nuclei in the world. Same for all the nuclei. Now take a look at this. Radius of 2He4 nucleus is 3 fermimeter. You have got a nucleus over here. This is the nucleus, okay? 2He4, helium nucleus. And it says that radius of 2He4, or directly I'll write, radius of He is given as 3 fermimeter. Radius of this nucleus is given as 3 fermimeter. Okay. Then the radius of sulfur will be, that is 16s32. 16s32. So I can say RS will be, you are supposed to find this. Guys, radius of this is given. You are supposed to find radius of S. Guys, we say as radius is proportional to A raised power 1 by 3. We recently studied. Now, can I say radius of HE divided by radius of S will be equals to mass number of HE divided by mass number of S whole raised power 1 by 3. Now I can write radius of HE is given as 3 divided by RS is equal mass number of helium. This is mass number, that is 4 divided by mass number of sulfur. This is 32 and whole raised power 1 by 3. Okay. So 4 ones are 4, 8s are. Cube root of 8 is 2. 2 into 2 is 2 into 2 into 2 is 8. So 3 divided by RS will be equals to 1 by 2. Now do the cross multiply. So RS will come out to be 6 fermimeter. RS will come out to be 6 fermimeter. The radius of this sulfur is 6 fermimeter. Let's move on to the binding energy. Let's move on to the binding energy. Guys, see, binding energy mass defect. What does binding energy actually mean? Guys. Let's suppose you have got a nucleus over here. Okay. This nucleus has got A mass number and Z is the atomic number. Okay. I want you guys to break this nucleus. So in breaking the nucleus, you have to use your energy. Because without using the energy, it is not possible for you to break the nucleus. Yes. Now, guys, when you break the nucleus, you are taking these nucleons out. It has A mass number, Z number of protons, okay? And how many number of neutrons will be over here? That is A minus Z. Now, when you break the nucleus, you take the protons out, place it over here. How many protons? Z protons. One proton has got mass MP. Z will have Z MP. Then plus. How many neutrons? A minus Z neutrons. So A minus Z neutrons have got mass A minus Z into Mn. 5 will have 5 Mn. A minus Z will have A minus Z Mn. So this is what we call the individual mass of the nucleons. This is what we call the individual mass. And this is called the collective mass. When they were inside this nucleus, mass of this nucleus was M. Collective mass. Guys, if these nucleons are inside the nucleus, we check the mass of this nucleus, it is M. When we are taking them out individually, this is the mass, individual mass. And we observed that this individual mass is greater than collective mass. Experimentally, we saw it. This individual mass is coming out to be greater than collective mass when they are inside this nucleus. Now, why does it exactly happen? We said the energy which is used in breaking the nucleus, the energy which we used in the breaking the nucleus is stored in the form of mass in the nucleons. That energy is not wasted, my dear friends. That energy is not wasted, my dear friends. Okay. So that energy gets stored, like when you are breaking the nucleus, the energy you are using, that gets stored individually in the nucleons. That's why individual mass has increased as compared to the collective mass. Now guys, let's suppose I am saying here mass is 20 kgs collective and individual mass is coming out to be 22 kgs. Don't you think that here mass defect has occurred? How much? 22 minus 20. That will be how much? 2 kg mass defect has occurred. Okay. So this energy is called the binding energy. This energy is called the binding. The energy which is used to break the nucleus. The energy which is used to break the nucleus. That is called the binding energy. And this energy gets stored in the form of mass, due to which mass defect occurs. So due to this energy, only mass defect occurred. And if somebody asks you how to find mass defect, you'll say, sir, final mass minus initial mass, individual mass minus collective mass. And how much is this? ZMP plus A minus ZMN minus M. So this mass defect will be equals to, that is ZMP, A minus ZMN minus collective mass. This will be the mass defect. 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 Okay. And my dear friends, in this particular case, I would want you to focus over here. Now guys, okay, this is the mass defect. If somebody wants to find out how much binding energy is there, how to calculate the binding energy. Guys, I am saying the energy which you used in breaking the nucleus is stored in the form of mass, due to which mass defect occurred. And we calculated that mass defect. Now, how much energy is stored in this mass? That will be only in a binding energy, because this mass came because of the binding energy. Okay, now if we find how much energy is in this mass, that will be itself the binding energy. Because of binding energy, mass defect came. Now, how much energy is stored in this mass defect? That will be binding energy. What I'm trying to say is, because of binding energy, this mass defect came, delta M. Now, how much is the energy stored in this mass defect? That will be the binding energy. Yes. Reverse process. So how to calculate that? Binding energy is equal to mc square. We'll be saying, sir, this binding energy will be delta M, that is this value, multiplied by c square. Multiplied by c square. Very important expression. One more important thing. Binding energy per nucleon is proportional to the stability. Now, what does binding energy per nucleon mean? Guys, see. Binding energy per nucleon means, the amount of energy required to take out. Binding energy per nucleon means the amount of energy required to take out every nucleon. Binding energy per nucleon means the amount of energy required to take out one nucleon from the nucleus. Let's suppose, guys, you have got a nucleus over here. It has got large number of nucleons. Now, if I am saying binding energy total in this particular case is 20 electron volt, what does it mean? It means the amount of energy required to take out all of these electrons is, all of these nucleons is 20 electron volt. But if I am saying binding energy per nucleon means binding energy divided by total mass number. If it is, let's suppose, 4 electron volt, it means if you have to take out one single nucleon, it requires 4 electron volt. That's called binding energy per nucleon. Now, guys, and it says that binding energy per nucleon is proportional to stability. Binding energy is not proportional to stability. Binding energy per nucleon is proportional to stability. Like here, a nucleus of 4x6 and 6x12 has binding energy X and Y are 24 and 36 electron volt. Okay. Which of the two is which one is more stable? Guys, see, you have got two nucleus over here. This is X and this is Y. This is X and this is Y. If I say binding energy of this X is given as 24, binding energy of this Y is given as 36, what does that mean? How much amount of energy is required to take out all the nucleons? How much amount of energy is required to take out all the nucleons? Now, if I say binding energy per nucleon, so that will be 24 divided by, this has got mass number of how much? 6. This has got mass number of 12. So 24 divided by 6. So this will be 4 electron volts. If I find binding energy per nucleon here, that will be 36 divided by 12. That will be 3 electron volts. So if you have to take out one nucleon from the nucleus, so how much energy is required? 4. Here are only 3. So we say X is more stable than Y. Why? Because binding energy per nucleon is proportional to the stability, not binding energy only. Okay. Now, guys, take a look. You have got over here graph between binding energy per nucleon versus mass number. Or you can say this is the graph between stability. You can also say, either you call it the stability or you say binding energy per nucleon. It's one and the same thing, ladies and gentlemen. Okay, versus mass number. Binding energy per nucleon versus mass number. Guys, see, we say experimentally it has been seen that graph between binding energy per nucleon and mass number comes out to be something like this, stability versus this. Now see, what does it mean? As you keep on increasing the mass number, you see stability increases. Like, if let's suppose there is a nucleus, it is having mass number 10. How much stability it has? Less stability. It is not stable. If there is a nucleus, it has got mass number, let's suppose 85. How much stability it has? This much. Large stability. It is more stable. Okay. And then if you have, let's suppose go to something like this. If you have a nucleus, its mass number is 200. How much stability it has? Less. Now you clearly see, as mass number increases, binding energy per nucleon or stability also increases. Now at certain value, up to certain value, after which it again starts decreasing. Okay. Now take a look. Those nuclei with mass number less than A is equal to 30. Those nuclei with mass number less than A is equal to 30. So till mass number A is equal to 30, less than this, A is equal to 15 can be there, 15 can be there. Okay. Are called lighter nuclei. These are lighter nuclei. Why? Because they have got less number of nucleons. and are unstable. Why? Because their stability is less. Their stability is less. They are unstable. Those nuclei with mass number greater than 170 are called heavy nuclei and are also unstable. Those nuclei which has got large mass number, see, this has also less binding energy per nucleon, this less stability, this has less stability. So if there is a nucleus, it has less stability. So these are also unstable. Now guys, in this particular case, I would say we say nuclei between A is equal to 30 to A is equal to 170 are highly stable. So all those nuclei which comes between this range, those are stable. Like you have A is equal to 45, that is stable. A is equal to 70, stable. A is equal to 100, stable. Okay. Now, my dear friends, if there is a nucleus over here which is unstable, okay, this nucleus and this nucleus, everybody in this world wants to become stable. Like you guys are unstable right now. You are looking to crack the NEET. Once you crack the NEET, you will become stable. Now, if this is the nucleus, it is having 16 mass number. This is also 16. Those are unstable. But if they fuse together, if they join together, so they will form a bigger nucleus. 16 plus 16 is 32. Now it is in the range, this end, between this and this. So this process in which two nucleus fuse together so that they attain stability, the process is called fusion. Okay. Here two lighter nuclei will combine together to form a bigger nuclei in order to attain stability, and the process is called fusion. Energy is released in the process. Why? Because whenever something attains stability, always remember energy is released. If something attains stability, energy is released. Okay. And now guys, one more thing. If there is a bigger nuclei, it is also unstable. It breaks, let's suppose its mass number is 200. It breaks into two smaller nuclei, 100 and 100. Now 100 is stable. This process is called fission. This process is called fission. It is mentioned over here. A bigger nuclei with mass number greater than 170 breaks into two smaller nuclei. To gain stability, the process is called fission. Energy is released in this process also. Why? Because here also it is moving towards stability. That's why energy is released. Energy is released, absorbed, depends upon whether it is attaining stability or not. Then you have Q value of the reaction. You have Q value of the reaction. Q value of the reaction. What does Q value of the reaction mean? This is how much energy is released or absorbed. It is how much energy is released or absorbed. It is how much energy is released or absorbed. What does that mean? I'll tell you. What does that mean actually? It is how much energy is released or absorbed. Now guys, see. Let's suppose you have got the two nuclei over here. This is nuclei A plus you have got nucleus B in this particular case. Let's suppose you have got the two nucleus over here. A and B. Okay. Yes. And my dear friends, these two nucleus are combining together. Sir, how? Like in case of fish fusion. Two nucleus combine together, fuse together, and they form the new nuclei C and D. Okay. Here we call this as reactant nuclei. We call this as product nuclei. And then we say plus Q. Q is the Q value of the reaction. What is that? That is energy absorbed or released. So means when reactant nuclei are converted to the product nuclei, in this reaction, some energy is either absorbed or released, and that is what we call the Q value of the reaction. And how do we find this? Mass of reactants minus mass of products into C square. Mass of reactants is what? Mass of A plus mass of B minus mass of C plus mass of D into C square. This is how we can find the Q value of the reaction. Now guys, important relation here is this one. To write the Q value of the reaction in terms of binding energy. Okay, how to find the energy absorbed or released in terms of binding energy? See. This is Q value of the reaction will be binding energy of products minus binding energy of reactants. This is important. Okay. Now guys, one thing you remember over here, if binding energy of products, if this binding energy of products, okay, is greater than binding energy of reactants, then Q will come out to be positive. If this is greater than this, Q will come out to be positive. Okay. And we say if binding energy of products is less than binding energy of reactants, Q will come out to be negative. Simply, if this is 5, this is 10. 5 minus 10 is 5. 5 minus 10 is 5. Okay. So, if Q is positive, it's an exothermic process. Exothermic process. Okay. Energy is released. It means energy is released. It means energy is released. And when it comes to this is an endothermic process. It means energy is absorbed. It means energy is absorbed. Here it is energy is released, energy is absorbed. Q is positive, Q is negative. Okay. Energy is absorbed, energy it's an. And in terms of mass also you can say, if mass of reactants is greater than mass of products, Q will be positive. Means energy is released, it's an exothermic process. If mass of reactants is less than mass of products, then Q is negative, energy is absorbed, it's an endothermic process. Guys, important relation is this one. Q value of the reaction, energy absorbed or released in terms of binding energy. Let me show you the question. The question is this. First, let me show you this one. Guys, tell me, in a nuclear fusion reaction, if energy is released, then binding energy of products is greater than binding energy of reactants. Binding energy of reactants is greater than binding energy of products. Binding energy of products is greater than binding energy of reactants. Guys, in a fusion reaction, energy is released. Energy is released. What does that mean? Energy is released. Can I say in that case, Q is positive? Recently we studied. If Q is positive, Q is only positive, my dear friends, if binding energy of products is greater than binding energy of reactants. Recently we proved it. Q is positive, energy is released. It means binding energy of products is greater than binding energy of reactants. So, option C, without any doubt. Now here, the binding energy per nucleon for 3Li7 and 2He4, for 3Li7 and 2He4 nuclei are 5.60 MeV and 7.06 MeV. Okay. This is the reaction over here. Guys. 3Li7 plus 1H1 gives 2He4 plus 2He4 plus we say Q. Okay. Yes. Now guys, in this case, we have to find the Q value of the reaction. How do we find? Sir, Q value of the reaction will be simply binding energy of products minus binding energy of reactants. So Q value of the reaction, binding energy of products. Guys, see. It says the binding energy per nucleon for 3Li7. Guys, it is 5.60. Guys, one nucleon of 3Li7 has got how much binding energy? 5.60. How many nucleons are there? 7. So 7 will have how much? 7 will have 7 into 5.60. This is the total binding energy of reactant. Sir, what about this? Binding energy of this will be 0. Why? Because this is 1H1. It is only one particle. It is only one particle. One particle binding energy is used in that case where you have to separate two particles. Here it is one particle. How can you separate one particle? It is separated only. So, one nucleon of 3Li7 has got 5.60. 7 will have how much? 7 into 5.60. Okay, then minus. Binding energy of reactants. Reactant here is 2He4, 2He4. Now, and 2He4 nucleus has got this much binding energy, 7.06. One nucleon of 2He4 has got 7.06. How many nucleons? 4 plus 4 is 8. So 8 nucleons will have 7.06. This is the binding energy of. Okay, we are so products minus this. Okay, reverse we have to do. So it is 8 into 7.06 minus reactants is 7 into 5.60. Is this crystal and clear? Is this crystal and clear? Guys, tell me. Is this crystal and clear? See. What I'm saying in this particular case is, you have to tell me Q value of the reaction. That's binding energy of products minus binding energy of reactants. These are the products. One nucleon of products has got binding energy 7.06. How many nucleons are there? 4 plus 4 is 8. 8 will have how much binding energy? 8 into 7.06. Sir, 10 will have how much? 10 into 7.06. 15 will have how much? 15 into 0.06, 7.06. So 8 will have 8 into 7.06. That will be the total binding energy of products. Similarly, binding energy of reactants, 7 into 5.60. So Q will come out to be 17.4 MeV. 17.2. Now take a look at this question. Tell me the answer of this one. The binding energy per nucleon of deuteron and an alpha particle are x1 and x2 respectively. What will be the Q value of the reaction in the reaction? Okay, this is the reaction. 1H2 plus 1H2 gives 2He4 plus Q. Now guys, in this particular case, you are supposed to find Q value of the reaction. What will you say? Q value of the reaction will be binding energy of products. Guys, product is this much. It says that the binding energy per nucleon for deuteron and alpha particle. This means deuteron, this is alpha particle. For deuteron, it is x1. For alpha particle, it is x2. Now guys, one nucleon of alpha particle has got how much binding energy? X2. 4 will have how much? 4x2. So this is binding energy of products. I'll write binding energy of products minus binding energy of reactants. So Q will come out to be. So binding energy of 2He4. So 4 into X2 minus binding energy of deuteron is X1. This is deuteron. How many nucleons are there? 2 plus 2 is 4. So 4 nucleons will have how much binding energy? 4 into X1. So Q value of the reaction will be simply 4 into X2 minus X1. Is this clear? Is this clear, guys? Now you have got the last topic over here, that is nuclear force. What does nuclear force? It is the force which acts between the nucleons. Okay? Okay? It keeps the nucleus stable. It keeps the nucleus stable. It keeps the nucleus stable. Like, guys, if you have a proton and a proton, okay, we say between these two, nuclear force will act. Okay? And if you have a proton and a neutron, we say between these two, nuclear force will act. If we have a neutron and a neutron, between these two also, nuclear force will act. Nuclear force will act. Sir, what about proton and proton? Is there any other force which will act? Yes, that is electrostatic force. So between proton and proton, electrostatic force will also act. And always remember, nuclear force between two protons will be equal to nuclear force between proton and a neutron will be equal to nuclear force between neutron and a neutron. Okay, this is always equal. Okay. And guys, when it comes to the net force in this case will be less as compared to the net force in this case. Guys, what is the net force between proton and proton? That is nuclear force only. What is the net force between neutron and neutron? That is this force only. What is the net force between proton and proton? Sir, here net force is inward force is nuclear, outward force is electrostatic. So net force will be this force minus this force. Let's suppose if this is 10, this is 5. 10 minus 5, net force will be 5. Here, how much is net force? If this is 10, so 10. If this is 10, so this is 10. 10, 10, 5. So net force in these two cases will be large as compared to this. Okay. So you can write it over here. F net between proton and proton is less than F net between neutron and neutron, which is equal to F net between proton and neutron. Why? Because proton and proton has got charge. That's why if there are two charges, electrostatic force will also act. Sir, here also will act? No. This is proton and this is neutron. This is proton and this is neutron. Between proton and neutron, electrostatic force will not act. So this is very important. This is very important. Keep that thing in your mind. Net force in this case will be less as compared to this and as compared to this. Okay. I hope this is clear. I hope this is crystal and clear till over here. So, and one more important thing I just want to tell you over here, when it comes to this nuclear force, this nuclear is attractive in nature. This nuclear force is attractive in nature. And one more thing I want to say, that this F nuclear is 10 raised power 39 times the gravitational force. It is a very strong force, very extremely strong force. 10 raised power 39 times than the gravitational force. And this F nuclear is 100 times electrostatic. Okay. And one more thing over here, that is graph between potential energy and distance between the nucleons. Let me make this graph. Okay. This is potential energy versus distance between the nucleons. Guys. This graph is something like this. Okay. So this is the graph between, like you have got, let's suppose, two nucleons, proton and neutron. Okay. Distance between them is r. So we say there is a potential energy which exists between these two nucleons. And the graph between potential energy versus r will be something like this, Keep this thing in your mind. So we are done with the chapter nuclei. Now you have got the next chapter, that is what we call the semiconductors. I have discussed all the topics of nuclei. Now you have the semiconductor. You have the semiconductors. Guys, is this crystalline clear till over here? Tell me in the chats. This is the 6th chapter that we are starting right now. Okay. I think we must take a break, huh? After the break, we'll start the semiconductors. After the break, we'll be starting the semiconductors. So do not leave, okay? And you have my heart here.
Check. Okay, guys, let's move on to the today alternating current chapter is out because only 2 hours left. Let's see. Let's see if we can do that also. Chill, take a chill pill. Okay, guys, let's talk about the chapter semiconductors. Okay. So, guys, when it comes to the chapter semiconductors, as of now, you might have studied in your previous classes, there are two materials that we have been studying: conductors and we say insulators. Okay. Conductors are those materials in which conduction is possible, means current, electricity can flow easily in these materials in conductors. Okay. And when it comes to the insulators, we say conduction is not possible. Like if you take a conductor over here, we say current, electricity can easily flow. Okay, like you have metal. Because why? We say so many free electrons are present in a conductor. That's why conduction is possible. If this is a conductor, this is a wire, electrons can flow easily, current can flow easily. When it comes to the insulator, there are no free electrons. That's why we say conduction is not possible. Now, in between these two, there lies a material that is what we call the semiconductor. It's a special type of material. And we say semiconductor lies between conductors and insulators. This semiconductor can behave like a conductor also. It can behave like an insulator also. This is the, we say, property of the semiconductor. It can behave like both. Insulator cannot be converted into a conductor. But this can be converted into the insulator also. Now, we say semiconductor has got the dual nature. It behaves like a conductor as well as it behaves like a insulator. Its conductivity and resistivity can be controlled. Its conductivity, like if I say conductor has got large conductivity, less resistivity. Okay. We say insulator has got less conductivity. That's why conduction is not possible. But conductor has got large conductivity. See, when it comes to conductor, semiconductor, insulator, conductivity of the semiconductor is between 10 raised power 2 to 10 raised power 8 ohm meter inverse. It's a large conductivity, huge. Why? Because there are large number of free electrons. When it comes to semiconductor, its conductivity lies between 10 raised power minus 5 to 10 raised power 6 ohm meter inverse. For insulator, its conductivity is less than 10 raised power minus 6. We can say something like that, 10 raised power minus 9, 10 raised power minus 6. Now see guys, if you decrease the conductivity of the semiconductor, make it 10 raised power minus 5, it will behave like an insulator. Why? Because you have decreased the conductivity. And my dear friends, if you increase the conductivity of the semiconductor, you make it 10 raised power 6, it will behave like a conductor. That's why its conductivity lies between 10 raised power minus 5 to 10 raised power 6. That's why we say it is controllable. If you increase it, it behaves like a conductor. If you decrease it, it behaves like an insulator. That's why it has got a special characteristic. Now there is a concept of band diagram which is very much important. Band diagram concept we need to study over here. Take a look. Guys, let's suppose I am taking a material over here. Sir, what material? Anything. Like this is a material, okay? I'm taking this material over here. Okay. I'm taking a material over here. This is the material. Okay. This is any material. And now we know, sir, this material, or you say crystal, this material is made up of crystal. This crystal contains millions of atoms, okay? We say this is the marker. This marker is made up of millions of atoms. And inside those millions of atoms, you have got millions of electrons. Okay? Now, my dear friends, in reality, sir, are these electrons present in a random order, something like this? No.
You say in reality, these electrons are present in the energy levels. In reality, these electrons are not present something like this. If you go at the molecular level, you keep on zooming, zooming, zooming. Over there, you'll find that these electrons are present in the energy levels, something like this. In every energy level, 2 electrons are present. 2 electrons are present. Okay. Now, this as a whole is what we call the energy band diagram. If you take any material like this marker, if you go on, if you move inside, keep on zooming, zooming at the molecular level, you'll find atoms. Inside atoms, you'll find electrons. Now, those electrons are not present in a random, in a messy way. They are present in a proper, in a nice manner, in the energy levels. And this is what we call the band diagram, energy band diagram. Okay. And in each energy level, you have got 2 electrons. Now, band diagram in case of semiconductors. You'll have band diagram for conductors, semiconductors, for insulators. For semiconductors, band diagram looks something like this. So, this one, okay, from the upper side, these energy levels, this is these energy levels. This upper portion is what we call the conduction band. This lower portion is what we call the valence band. Upper is conduction, lower is valence. Okay. Now, my dear friends, in this particular case, understand very carefully. Listen. This is what we call the lowest energy level of conduction band. Upper one is what we call the conduction band. Lower is valence band. I'll mention over here. This one is called conduction band. This one is called valence band. Now, guys, this energy level over here, this is the lowest energy level of conduction band. This is the highest energy level of valence band, this one. And this gap between these two, this is what we call the energy band gap, Okay. And my dear friends, this is the maximum energy level of valence band. This is the minimum energy level of conduction band. Okay. And always remember, this energy band gap, it is always equal to, that is minimum energy level of conduction band minus maximum energy level of valence band. Okay. Minimum energy level of conduction band minus maximum energy level of valence band, higher minus lower. Okay. Now, my dear friends, one more thing I just want to tell. What is that? We say at 0 Kelvin, conduction band is completely empty. In case of semiconductors, we say at 0 Kelvin, this conduction band, it is completely empty. No electron is present in this. Means 0 Kelvin means you have not increased the temperature of the semiconductor. And valence band is completely filled. This valence band is completely filled with the electrons. Ignore these 4 as of now. Okay. If we increase the temperature, of the semiconductor, now we say these electrons, bonded electrons, these are what we call the bonded electrons. These are what we call the free electrons which are present here. We say these bonded electrons will gain energy, kinetic energy. They will start vibrating. Bonds will break. And these electrons will shift to the valence band. Conduction band. So at 300 Kelvin, these electrons would have shifted over here. We say bonded electrons move to the conduction band. So electron hole pair is created. My dear friends, at T is equal to 300 Kelvin, always remember, guys, always remember, we say this conduction band becomes partially filled, this becomes partially empty. Because now the electrons will shift over here. When the electrons shift over here, I would want you guys to listen. This electron will shift here, this electron will shift here, this electron will shift here, this electron will shift here. So we say hole is created here. These are the holes which are created. Okay, these are the holes which are created. So as you keep on increasing the temperature of a semiconductor, electrons from valence band will shift to the conduction band. At T is equal to 300 Kelvin, this becomes partially filled, this becomes partially empty. Now holes will be created over here. Hole is a vacant space. Hole is a vacant space. When it comes to the hole, guys, hole has got positive. Sir, if you are saying hole is a vacant space, how it will have positive charge? Hole is the deficiency of electron. Like, if you say this is a material, it has plus 2 coulomb charge, minus 2 coulomb charge. If you remove negative charge from this, if you take negative charge from this, what charge will be occupied on this? Positive. If you remove positive charge, negative charge from somewhere, positive charge gets occupied over there. That's what the concept we are using. So we say if you remove the electron from here, positive charge gets occupied here. So hole have got positive charge. Okay. Now, band diagram for conductors. Okay, for conductors. Guys, this is the band diagram for conductors. Okay, you can clearly see the difference between the band diagram of semiconductors and conductors. Here, energy band gap is 0. Okay, you see, conduction band is overlapping the valence band. Okay, this is the maximum energy level of valence band. This is the minimum energy level of conduction band. And in this case, this conduction band is also completely filled. Valence band is also completely filled. So basically, these electrons are called free electrons. These electrons are called free electrons. These electrons are called bonded electrons. So when it comes to the bonded electrons, why we call them as bonded electrons? Because they are bonded. These are free and they form the current electricity. They constitute the current. Because of these, current will be produced. That's why conduction, it's having the large conductivity. When you see insulator, they have got insulator. This is the conduction band, this is the valence band. Okay, here also valence band is completely filled. But even if you increase the temperature over here, these electrons won't be able to reach the conduction band. Why? Because this energy band gap is very large. It is mentioned over here. Energy band gap is very large. Greater or equal to 3 electron volts. By giving thermal energy, we won't be able to shift the electrons to the conduction band. So no current flows. Okay. No electrons will be present in the conduction band. That's why no current will flow. But in case of semiconductor, if you increase the temperature, electrons will shift to the conduction band. So conductivity will increase. Next. Now guys, types of semiconductors. There are 2 types of semiconductors. We have pure, okay, these are intrinsic semiconductors, also called pure semiconductors. Okay. Then you have impure semiconductors. Impure semiconductors. Pure and impure semiconductors. Now guys, when it comes to the pure semiconductor, sir, what is impure and pure? And which one is good? Impure is good. Okay. So when it comes to the pure semiconductor, means no impurity has been added. Sir, why do we have to add the impurity? In order to increase the conductivity. Well, I'll tell you. Guys, this is a pure semiconductor. Let's suppose this is pure silicon. Basically, silicon is the material which we consider as the pure semiconductor. Germanium is the pure semiconductor, pure germanium. So we have got the pure silicon over here. Okay. And my dear friends, in this particular case, this is the pure silicon over here. Okay. Let's suppose at room temperature, understand very carefully, at room temperature, it has got holes. These are the holes. Okay. These are the holes. These are the electrons present. Okay. Now you connected a battery to it. We know because of the battery, electric field will set up. Battery sets up the electric field. Okay. Now, these electrons, when an electron is placed in the external electric field, it experiences the force in the opposite direction. This negative charge experiences the force in the opposite direction. This whole positive charge, it experiences the force in the same direction. Okay, like over here, this is the pure silicon. This is the hole, this is the electron. When you apply external electric field, this electron moves something like this and it gets occupied into the hole. Electron gets occupied into the hole. When electron gets occupied into the hole, so we say now hole will be created over here. It looks like electron moves from this point to this point, hole moves from this point to this point. So we say here, due to the motion of electrons and holes, current is produced. Here, due to the motion of electrons and holes, current is produced. Okay. And my dear friends, if somebody asks you what is the value of net current in case of pure semiconductor, this is a pure semiconductor in which some holes and electrons are present. Okay. At room temperature, some electron hole pairs are present in the semiconductor, pure semiconductor. Then we applied battery. Because of the application of the battery, electron holes started moving and current is produced. And how much is the current? N. Okay, Ni. Ni is the intrinsic charge carrier density. Okay. Ne, AVdV. Okay. Then you have divided by L, where L is the length of the semiconductor in this particular case. Mu E plus mu H. What is this mu E? Guys, I'll tell you. This E is the charge on an electron. Remember directly, E is the charge on an electron. Okay. This A, what is this A? A is the area of cross section of this semiconductor. Okay, area of cross section. Delta V is the potential difference. L is the length of the semiconductor. And this mu E is the mobility of electrons. We say mobility. This is mobility of electrons. Mobility of electrons. And this is mobility of holes. Mobility of holes. If somebody asks you, sir, what is mobility? Mobility means ability to move. Okay, like if there is a fat person and there is a slim person, who is having more mobility? Who is free to move? Obviously slim person, because he is having less mass. So less mass is more free to move and more mass is less free to move. Okay, that is what we call the mobility. Okay. I hope this is crystal and clear to each and every single student. Okay. So this is the net current in case of pure semiconductor. Now guys, let's move on to the extrinsic semiconductor. Extrinsic semiconductor, or we say impure semiconductor. Impure semiconductor. Now the question is, why do we have to make a semiconductor impure? Why do we have to make the semiconductor impure? Okay. Now the question is, why do we have to make a semiconductor impure? See guys, we say in order to increase the conductivity of a semiconductor, in order to increase the conductivity of a semiconductor, we add impurity to it. We add impurity to it. Like, my dear friends, understand very carefully. You have got a pure silicon. This is pure silicon. Okay? Silicon crystal means pure semiconductor. Now guys, in this case, what you are doing is that you are adding the impurity. What is the impurity? Phosphorus. You are adding the phosphorus impurity. Okay? Now, while you add the phosphorus, now see, phosphorus atom is basically like, this is one phosphorus, your phosphorus atom. Okay, so it is added over here. It is added over here. Okay. Now, guys, on adding one, I'll not go in much depth, much detail. I have taught this in much detail, how this is released and that is released. What is this is pentavalent. Okay. So, one thing I just want to tell you over here. What is that? That is this phosphorus is a pentavalent impurity. So, my dear friends, pentavalent means which has 5 valence electrons. But when it comes to the silicon only has 4 valence electrons over here. Okay. So, in order to fit into this crystal, an atom must have only 4 electrons. But phosphorus has how much? 5. So, phosphorus will basically donate 1 electron. Okay, here. And with the rest of its 4 electrons, it will become stable over here. Now, on adding 1 phosphorus, how many electrons are released? 1. On adding million phosphorus, how many electrons will be donated? Million. Now, these are what we call the free electrons. Okay. So, on adding million phosphorus, we say million. On adding million phosphorus, we say million electrons are donated. So, conductivity increase. Okay. Now, my dear friends, could you please tell me in this particular case, when it comes to, understand very carefully, when it comes to the majority charge carriers in this extrinsic semiconductors is basically of 2 types, N-type, P-type. First one, we are creating N-type. So, in N-type semiconductor, we are adding phosphorus, pentavalent impurity. Okay, keep that thing in your mind. So, if you are adding 1 phosphorus, 1 electron is released. On adding million phosphorus, million electrons will be released. Okay. Now, can I say in this particular case, you are adding phosphorus means electrons are released. So, can I say majority charge carriers in this case will be electrons? Yes. Why? Because number of electrons are increasing. So, Ne will be the majority charge carriers. Okay. Charge carrier means which contain charge. Electrons also contain charge, holes also contain charge. And minority charge carriers will be holes. Why? Because electron number is increasing, holes remain the same. Okay. And my dear friends, in this particular case, can I say number of electrons added will be equal to the number of donor ions. Donor ion means phosphorus, because phosphorus is donating electron. If you are adding 5 phosphorus, 5 electrons. Million phosphorus, million electrons. Number of electrons donated will be equal to the number of will be equal to the number of donor ions, will be equal to the number of donor ions. I hope this is clear. I hope this is clear. Yes. Now. P-type semiconductor. To create a P-type semiconductor, that's it, more than sufficient detail in case of N-type. To create a P-type semiconductor, we add boron impurity. This is trivalent. Trivalent means which has 3 valence electrons. But in order to fit, we are taking a pure germanium. Germanium also has 4 valence electrons. In order to fit into this crystal, boron must have, we say 4 valence electrons, but it has only 3. So if boron has only 3 valence electrons, 1, 2, and 3, and here germanium has its own 4 electrons. Okay, own 4 electrons. Now, when germanium sees boron is having only 3 electrons, it will donate its electron and give to the boron. And here hole will be created because it has donated electron. Now guys, on adding 1 boron, how many holes are created? We say 1. Okay, we say 1. I'll say on adding millions of borons, how many holes will be created? Millions of holes. On adding million boron, millions of holes are created. Millions of holes are created. Can I say positive charge in this case is increasing? So I can say in this particular case, holes will be the majority charge carriers. Holes will be the majority. Achha, by the way, one thing I just want to ask you over here. If somebody asks you, what is the net charge of N-type semiconductor if electrons are increasing? Is the net charge positive or negative? We say net charge in this case. Okay. Why? Why? Because if you are adding, what is phosphorus? Phosphorus is basically the positive donor ion. Because phosphorus is donating electrons, so there is positive charge on the phosphorus. On adding 1 for positive charge, 1 negative charge is added, so neutral. On adding 10 phosphorus positive charge, 10 electrons are added, so 10 positive, 10 negative, neutral. Same is the case over here. Same is the case over here. When it comes to the boron, we say majority charge carriers or holes. Why? Because when you are adding million boron, million holes are created. Okay. And electrons are minority charge carriers. Number of holes is much greater than number of electrons. And here, I can say number of acceptor ion. Boron is acceptor ion because he is accepting the electron. So number of acceptor ion is equal to the number of holes. Number of acceptor ion is equal to the number of holes. Keep that thing in your mind. Okay, so number of acceptor ion is equal to the number of holes. And here also you can say net charge is equal to 0. Why? Because number of acceptor, number of positive charge is equal to number of negative charge. Here boron is negative. Why? Because boron is accepting the electron. That's why it is getting negative charge. Now, answer this. Assertion and reason. A means assertion is correct, reason is correct. Reason is the correct explanation of assertion. B means assertion is correct, reason is correct. Reason is not the correct explanation of assertion. C means assertion is correct, reason is false. D means assertion is false, reason is false. Now tell me. Conductivity of a semiconductor increases on doping. Doping means adding impurity. Adding impurity. Due to increase in impurity, guys, on increasing the impurity, it does not increase the temperature of a semiconductor. Assertion is wrong. Okay, wrong. Doping, okay, conductivity, okay, sorry. Conductivity of a semiconductor increases on doping. Yes, true. Assertion is true, correct. Assertion is true. Because when you are doping, you are increasing the majority charge carriers. In p-type, electrons increase, in n-type, holes increase. So I can simply say assertion is correct. What about reason? Doping raises the temperature of a semiconductor. Wrong. Doping does not increase the temperature. So assertion is correct, reason is false. So C part. For a given applied voltage, current in n-type semiconductor is more than that in p-type semiconductor. Guys, current in n-type semiconductor is more than in p-type semiconductor. Guys, when it comes to the n-type semiconductor, look at this. In n-type semiconductor, majority charge carriers are electrons, okay? And in p-type semiconductor, majority charge carriers are holes. Always remember. What? Always remember, mobility of electrons is much greater than mobility of holes. So current due to electrons will be much greater than current due to holes. Why? Because electrons are faster as compared to the holes. Holes have got more mass. Because you mention over here, mass of hole is much greater than mass of electron. Mass of positive charge is greater than mass of negative charge. That's why I'm saying current due to electrons is greater than current due to holes. Because mobility of electrons is greater than mobility of holes. Option A. Assertion is correct, reason is correct, reason is the correct explanation of assertion. Hello. Amidresh. Just a second, guys. Now, guys. NEET 2019. Okay. Which of the statements is true for, I hope this is visible. Which of the statements is true for p-type semiconductor? Electrons are the majority charge carriers and trivalent atoms are the dopants. Okay. When it comes to the p-type semiconductor, what is majority charge carriers? Holes. And trivalent atoms are the dopants. Holes are the majority charge carriers, trivalent atoms are the dopants. Option B. Directly. Okay, NEET 2013. In an n-type semiconductor, which of the following is true? In n-type semiconductor, majority charge carriers are electrons. Pentavalent atoms are the dopants. Impurity is pentavalent. Still not visible? I am saying na. You guys are able to understand. Okay. In an n-type semiconductor, which of the following is true? Holes are, just a second. Electrons are majority carriers and trivalent atoms are the dopants. Electrons are wrong, incorrect. This is n-type. In electrons are minority charge carriers. Wrong. Holes are minority charge carriers. Pentavalent atoms are the dopants. Yes, D option. Holes are minority charge carriers. Pentavalent atoms are the dopants. Pentavalent impurity we added in n-type, and holes are minority charge carriers. Now guys, let's move on to the PN junction. Let's move on to the PN junction diode. See guys, when it comes to the PN junction diode, I would want you guys to focus exactly over here. See, what does PN junction diode actually mean? We say when P and N type semiconductor are joined together, when P and N type semiconductor are joined together, when P and N type semiconductor are joined together, it forms the PN junction diode. It forms the PN junction diode. Okay. Okay. Now guys, in this case, this is P type, this is N type. They are joined together. Now guys, what happens? When we talk about the P type semiconductor, what is the majority charge carrier? Sir, holes. Holes are the majority charge carriers. And if you see, if you try to have a look in case of a P type semiconductor here, in case of a P type semiconductor, okay, we say majority charge carriers in the P type semiconductor are what? They are holes. They are, in case of majority charge carriers, they are holes. Okay. And along with the holes, if you try to look over here, you have added the impurity that is boron. If you are adding 100 boron, there will be 100 holes created. There will be 100 holes created. Now, my dear friends, game of NEET class notes is available in the Unacademy NEET English Telegram channel. Oh, Unacademy NEET English Telegram channel. Now guys, you have over here, in this particular case, sir, majority charge carriers are holes, and then you have the fixed ions. Fixed ions means boron negative. If you are adding 100 boron negative, there will be 100 holes created. So this is boron negative, boron negative, boron negative. So 4 boron negative, 4 holes. Similarly in N type, what is added? Phosphorus is added. Okay, phosphorus is added. Now guys, so here in case of N type, majority charge carriers are electrons. Okay, and fixed ions are this phosphorus positive. This is fixed ions. Majority are holes, sorry, electrons. Now guys, tell me in this particular case, I would want you guys to understand. When you join P and N type semiconductor, this electron is coming close to the hole. Whenever an electron sees the hole, it wants to get occupied himself into the hole. So here electron hole recombination takes place. I would say in this particular case, electron hole recombination takes place. Electron hole recombination. Okay. So when electron hole recombination takes place, guys, these electrons will shift to this side. So now, this is negative charge. Negative charge will be occupied here. And what remains on this side? Positive charge. This is what we call the depletion region. So depletion region is formed. DR is formed. So due to the electron hole recombination, we say in PN junction diode, depletion region is formed. And in this depletion region, you have got positive charge, negative charge. So electric field will set up from positive to negative charge. So electric field will set up from positive to negative charge. Okay. So electric field will set up from positive to negative charge. Now guys, tell me one thing. If electric field is set up from positive to negative charge, understand one thing very carefully. We say here, current will be produced. I diffusion is produced due to the recombination of electrons and holes. Okay. Now guys, when these electrons will shift from here to here, so electrons move. Due to this motion of electron, current will be produced. And that current is what we call the diffusion current. Diffusion current is produced due to the recombination of electrons and holes. Okay. And drift current is produced due to the electric field in the depletion region, which makes the minority to move. Guys. This is N-type, this is P-type semiconductor. What is minority? Electrons. Okay. This is N-type semiconductor. What is minority? Holes. Okay. Now, here also I would say, guys, here also, these electrons are in minority, and this is N-type. These holes are in majority. Now, because of this, guys, understand, because of this electric field, these minority will move in the opposite direction. This hole will move in this direction. So it will again create current. That's what we call the drift current. Diffusion current is due to the recombination of electrons and holes. Drift current is due to the electric field in the depletion region. So we say this diffusion current is from P to N. This diffusion current is from P to N. Guys. Diffusion current is from P to N. Because if electrons move from N to P, current is moving in the opposite direction. Current is moving in the opposite direction. Okay, current is moving in the opposite direction. And this drift current is from N to P. Drift current is from N to P. Why? Because if electrons move from P to N, current will be from N to P. So both the currents are equal and opposite. So net current in PN junction diode will be 0. Here two types of currents will be formed, diffusion and drift. Both will be equal, so net will be 0. Then you have the forward bias. Guys, what does forward bias actually mean? Oh, Mufti Menk unofficial. Game of NEET PDFs are present in the Unacademy NEET English Telegram channel. How many times I'm supposed to tell you? Go check the Telegram channel of Unacademy NEET English. Over there, all the PDFs are available. Again and again, you are sending the same message. This t.me/Unacademy NEET English. This one. We send it over there only. Else you can check in the Wasim sir's Telegram channel, own Telegram channel. Rest, God knows better. Now guys, forward bias. Let's take a look at the forward bias. What does forward bias actually mean? See guys, let's suppose you have the PN junction diode. Okay. In case of P-type, majority charge carriers are holes. These are the majority charge carriers. Here, majority charge carriers are electrons. This is the depletion region. Positive charge, negative charge. Electric field is set up from positive charge to negative charge. Now. Connect the battery to it. This is the positive terminal of the battery. This is the negative terminal of the battery. Connect this positive terminal of the battery with this P-type, P side. Okay. Connect the negative terminal of the battery with N side, Okay. Then when? Okay. Now guys, Let me write over here. When positive terminal is connected to P side and negative terminal is connected to N side. Positive terminal is connected to P side, negative terminal is connected to N side. It is called forward bias. Guys, when positive terminal of the battery is connected to P side, negative terminal is connected to N side, it is called the forward bias of PN junction diode. Now guys, see, this positive terminal will create the positive charge on this side because positive terminal will send positive charge. Negative terminal will send negative charge on this side. Now, this positive charge will repel the holes. Why? Because holes also have got the positive charge. Positive, positive repel. So this positive charge will repel the holes, This negative charge will also repel the electrons. Sorry, this negative charge will repel the electrons. Negative, negative repel. Now we say, in this case, depletion region will decrease. Why? Because these electrons are pushed, these holes are pushed. Depletion region will decrease. And my dear friends, when the depletion region decreases, the electrons and holes, these electrons will again start recombining. The electrons, guys, we say when you push this, these will come closer. Now when the electron sees hole, they will start recombining. Okay, when these electrons start recombining, understand very carefully, when these electrons start recombining in these holes, now sir, will these electrons stop over here only? No. But these electrons now which will come here from this N side, they will start flowing through the battery. Okay, and will again come over here. Again electron hole recombination takes place. Again they will flow through the battery. And this is how current flows in the forward bias. What happens over here? Depletion region decreases. Electrons will move from N side to P side. Now electrons will not stop here. They will flow through this wire, through the battery. Again will come here. Again will shift over here and current will keep on flowing. Okay. Now battery will make these electrons flow to the N side once again. Due to the battery, they will flow to N side once again. Once again, they will move from N to P, from P to N. So this is what we call the forward current flowing in the forward bias. And if somebody asks you, sir, if the current flows in the forward bias, what is the graph? Graph between current versus voltage in case of a semiconductor, in case of a forward bias is this. This is the graph. Current is initially increasing. At certain value, it becomes very large. Okay. And that potential is what we call the barrier potential. This is called the barrier potential, at which current is very barrier potential. This is the procedure of current in the forward bias. And when it comes to the symbol of PN junction diode, guys, this is the symbol of PN junction diode, like this. This is the symbol of PN junction diode. This back side is called P side, this is called N side. Now, if you have to show this is forward bias, connect this P side with the positive terminal, connect this N side with the negative terminal. This will be the forward bias. Okay? And when it comes to the forward bias, always remember current flows easily. Current flows easily in case of forward bias. Okay? So current will flow easily in case of the forward bias, because we have seen current is flowing in the large amounts. When it comes to the reverse bias, guys, see, reverse bias is just the opposite of forward bias. Guys, this is P side, this is N side. Just reverse the polarity. Here you need to connect negative terminal of the battery with P side, positive terminal of the battery with N side. If this happens, we say diode is said to be reverse bias. If positive terminal of the battery is connected to P side, sorry, N side. Negative terminal is connected to P side. Diode is said to be reverse biased. Now guys, this negative charge, this see, this is the negative charge, this is the positive charge. It will send the negative charge here. If it gets negative charge gets occupied, these electrons will be attracted towards negative charge. So this will send the positive charge here. So these negative charge, these electrons, these holes will be attracted, these electrons will be attracted. Now here depletion region increases. If depletion region increases, we say electron hole recombination does not take. Electron hole recombination does not take. Electron hole recombination does not take place. Okay. Electron hole recombination does not take place. If electron hole recombination does not take place, current will not flow. Okay, here current will not flow. And my dear friends, if current does not flow, I can say, understand one thing very carefully. So now do one thing. Now keep on increasing. Now keep on increasing the potential difference. On increasing the potential difference. Guys, always remember, when you check over here, forward bias, so positive charge was created here, negative charge was created here. Between the positive and negative, external electric field due to the battery is created. Okay. Now similarly in this particular case, remember, similarly, here positive charge is created, negative charge is created. This is the external electric field from positive to negative. As you keep on increasing the potential difference, I would say electric field due to battery is this battery is increasing. Electric field due to the battery is increasing. Okay. If electric field increases, we say in the depletion region, guys, electric field is in this direction. Outward electric field is also in this direction. So we say this electric field in the depletion region will also increase. So electric field in depletion region in DR will increase. Okay. And after some time, guys, this electric field is very large. We say after some time, these bonds will break over here. After some time, bonds break. And when these bonds break, then this negative charge start moving in this direction, positive in this direction, current starts flowing. Bonds break and current flow. But this current will be very small. But this current is very small. But this current is very small as compared to forward current. This current is very small as compared to forward current. HSP, magical guru. What's up, HSP? Sir, how are you, sir? The Baba of all Babas. The king, the legend, the ultimate guru. That's nice. यार आज थक गया बहुत. Mir Muzab. That was nice. Now, guys, take a look. But this current is very small as compared to the forward current. Okay, take a look, guys. If we make the graph between current versus voltage, this is the graph in case of forward bias. When it comes to the reverse bias, we say current is almost zero, almost 0.00000. Now, guys, when you applied certain potential difference, sir, electron hole recombination does not take place. Okay. Okay. Now, guys, we say electron hole recombination does not take place. But as you keep on increasing the potential difference, like 10 volt, 20 volt, 30 volt, okay? Guys, at this particular voltage, let's suppose 30 volts, stronger electric field is developed. Bonds break, that's what I said. And current starts flowing. Current starts flowing immediately by the large amount. Okay? Current starts flowing immediately by large amount. This voltage at which the bonds break is what we call the breakdown voltage. Okay? This voltage, electric field in depletion region will increase. After some time, bonds will break and current flows. Okay? Current will flow at what voltage? At breakdown voltage. If you say, sir, this current in the reverse current is very large. No, it is very small as compared to the forward current. This is in the microampere. Okay, this current is in the microampere. Very small, very small. So we say almost, we consider current in reverse bias almost zero. Almost zero. We consider current in the reverse bias almost zero and current in the forward bias. So diode in reverse bias behaves like an open wire. Okay, and diode, open wire means in which current does not flow, and diode in forward bias behaves like a simple wire. And when it comes to the symbol, it is something like this. Guys, this is the diode. Positive terminal is connected to N side. Negative terminal is connected to P side. Okay, here resistance will be infinity. That's why we say current is zero. Okay, diode behaves like an open wire, current is zero. So diode will not allow the current, so current is zero. Okay, always remember current leaves from the positive terminal. So we say this current is not allowed in the diode. Current in the diode is zero. Why? Because it is reverse biased. Whatever you want to say over here. Okay. I hope this is crystal and clear to each and every single student. So basically, when it comes to the P-N junction diode, in case of forward bias, current flows. Diode behaves like a simple wire. In case of reverse bias, current does not flow. Diode behaves like an open wire. Okay. Now, guys, a certain reason. In an unbiased PN junction, holes diffuse from P region to N region. Unbiased PN junction in which no biasing is done. Holes diffuse from P region to N region. Holes diffuse from P to N. Electrons move from N to P. Correct? Then, reason is hole concentration in P region is more as compared to N region. Correct, 100% correct. So option A. Assertion is correct, reason is correct. Reason is the correct explanation of assertion. NEET 2020. Guys, the increase in the depletion, the increase in the width of depletion region in a PN junction diode is due to increase in the depletion region happens in forward bias or reverse bias? Sir, reverse bias only. Option D. Option D. Due to the reverse bias only. Because in the forward bias, depletion region decreases. Then only electron hole recombination takes place. Then you have, which of one of the following represents the forward bias? Which one of the following represents the forward bias? Guys, you have to tell me which one of the following represents the forward bias. This means higher potential, this means lower potential. If this is connected to P side, if P side is connected to higher potential means forward bias. Simple. Guys, this is P side, this is N side. Always remember this, the resistance is the resistance of the diode. See, P side is connected to 3 volts. N side is connected to 5 volts. So here, N is at higher potential. This is higher potential. This is lower potential. So this is reverse bias. Okay? And in this case, this is N and this is P. So N side is connected to -2. P side is connected to 0. So this is higher potential. This is lower potential. This is forward bias. Here, this is P and this is N. N is connected to -3. P is connected to -4. So this is higher potential. Because it is -3. This is lower potential. Okay. So this will be reverse bias. What about this? This is N, this is P. N is connected to +2. This is connected to -2. This is lower potential. This is higher potential. This is also reverse bias. So option B is the correct option. Yes, correct. Next you have, first do this. In the which one of the following, which diode is in the forward bias condition? Guys, this is P, this is N. This is lower potential, this is higher potential. So this is forward bias. This is P, this is N. This is 0 and this is +2. This is lower potential, this is higher potential. So this is reverse bias. This is P, this is N. N side is connected to -2. This is -5. So this is lower potential, this is higher potential. This is again reverse bias. This is P, this is N. N is connected to higher, P is connected to lower. Again reverse bias. Option A. Great. Okay, tell me about this one. 2 ideal diodes are connected to a battery as shown in the figure. The current supplied by the battery is, guys, this is positive terminal, this is negative terminal. If you check over here, this diode D2 is reverse biased. Clearly, if this is visible, I hope, I'm sorry, if this is visible, this is N side, this is P side. N side is connected to positive terminal. Okay, so D2 is reverse biased. So if D2 is reverse biased, current in this is 0. So I is equal to 0 in D2. Now guys, it will behave like this. Circuit will behave like this. This is the resistance. This is 5 volt. This is 10 ohm resistance. This is 5 volt. So current will be equals to V divided by R. V is equal to 5, R is equal to 10. That is 1/2, 0.5 ampere. Next, because this will behave like an open wire, this will behave like a simple wire. Okay, tell me about this. Guys, in this question, in 2016, you guys are supposed to tell me what is the current flowing. Tell me here. In this case, this is the positive terminal, this is negative terminal. See, here this negative terminal is connected to P side, this is N side. Negative terminal is connected to P side. This is N and this is P. So can I not say this D2 is reverse bias? This D1 is reverse bias, D2 is forward bias. Okay. Now let's make this circuit. Guys. This will behave like a simple wire, open wire. Let's make the new circuit. It would be something like this. So this upper resistance, then this resistance only. So this is 2 ohms, this is 2 ohms, this is 10 volts. Now tell me, current will be equals to delta V divided by R. What is the value of delta V? Delta V is potential difference, that is 10 volt. Resistance is 2 plus 2 is 4. That will be 2.5 ampere. I hope this is clear. Okay, in this case, tell me guys, see, clearly this is positive, this is negative. And this is N side, this is P side. So this one is reverse bias. This one is forward bias. Okay, this one is forward bias. Now you guys are supposed to tell me what is the potential difference. Guys, what is the current? Guys, see, here in this particular case, this diode is taking how much of potential difference? See. It is something like this. This is 5 volt. You might have studied, I have told you in the current electricity, if this is the resistor and this is, let's suppose, 10 volt battery. If I'm saying 5 volt, this resistance is taking. So in this 5 volt, this is taking. How much will be remaining? 5. 5 plus 5 is total 10. In case of series combination, potential difference divides. Similarly, your barrier potential of this is given as 3 volts. So what does that mean? This will take 3 volts of potential difference. So 5 minus, sorry, not 3, 0.3. 5 minus 0.3. How much is remaining? 4.7. So 4.7 this will take. Okay. Now tell me, what is the current? I is equal to delta V divided by R. Now, potential difference across the resistance, that is 4.7 divided by V. This is the current. Is that clear? Tell me quickly in the chats, is this clear? Guys, give me the signal in the chats. Is this clear? Now you have got the half wave rectifier. Guys, what is a half wave rectifier? A rectifier is a device, okay, which converts alternating current into direct current. Alternating current is that current which is having two directions, bidirectional. Like, let's suppose you have got an AC source over here. AC source means which gives the alternating current. This will give the current which will flow in this direction also, which will flow in this direction also, in both the direction. If there is a DC current, direct current, okay, this direct current will leave from the positive terminal and will enter the negative terminal. It can never leave the positive terminal. So there is only one direction of the current. That is what we call the direct current. In graphs, if you have to make the graph of AC current, it will be something like this. In graphs, alternating current will be, current is from the upper side also, positive also, from the lower side also, negative also. But when it comes to the direct current, graph will be from the upper side only. This is the positive only. Graph is positive only. Okay. Okay. So, alternating current means bidirectional current, sinusoidal current. Direct current means unidirectional current. If let's suppose I am saying in a circuit, current is flowing in this direction also, in this direction also. This you take positive, this you take negative. This will be alternating current. If in a circuit, current is flowing only in one direction, means this is direct current. It has got only one direction. That's what I said. Now, let's make the half wave rectifier. You take a coil. This is a transformer. Sir, why do we need transformer? So that it maintains the proper voltage. Directly see. Okay, this is the transformer. And here, this is the alternating current which is coming. This is the input current. We want to convert this alternating current, which is positive as well as negative, into the direct current. Now see guys, when this current enters, okay, when this current enters, we will connect a diode over here, PN junction diode, okay? And this is the load resistance. So load resistance will require this current. This current will enter the load. Load can be anything, television, like you have the current coming. If we want to send this current to the television, so that television will be load. Load can be bulb also, anything. Now guys, we say in this particular case, positive cycle will flow through this side because this has got positive as well as negative cycle, and negative cycle will flow from the lower side. Okay. Now guys, this is P side, this is N side. I have told you, if the current is entering the P side, it can easily flow. Guys, in case of forward bias, we were saying something like this. Current is leaving from this and it is entering the P side. Then you have got something like this. This is the reverse bias. Okay. So in this particular case, reverse bias is this. So current cannot enter this side, okay? Because this is higher potential is connected to N side. What does that mean? That means current is leaving from positive terminal. It cannot enter the diode. Okay. Now tell me, this positive cycle can easily flow through the diode, but when this negative cycle wants to enter the diode, it cannot flow. Why? Because N side does not allow the current. P side allows the current. So we say here, diode only allows the positive cycle. Here diode only allows the positive cycle. Now guys, when positive cycle enters, it will flow and it will go into the load resistance. It will complete the loop. Current has to complete the loop. Keep that thing in your mind. Okay. Positive cycle will flow. This is the positive cycle. But when negative cycle flows, it is not allowed. So at the time of negative cycle, current will be zero. Current is zero. Again, when the next positive cycle comes, current will flow. Again, when the negative cycle comes, current is zero. Current will flow, current is zero. Current will flow, current is zero. You can clearly see in this particular case, this is the output current. And here, this output current is direct current. It is positive only. Positive only. I know this is not a good current. Current is coming, becoming zero. Then again coming, becoming zero. Now we have another device, that is what we call full wave rectifier. Full wave rectifier is that device which will allow the positive as well as negative. Okay. This converts negative cycle to the positive also. Okay, it converts negative cycle to positive also. Guys, see, you have got over here this alternating current. Okay, this is AC. See. When it comes to this full wave rectifier, you connect two diodes. This is D1, and there is another diode over here, D2. Another diode over here, D2. And then in this particular case, you connect over here load resistance somewhere around over here. Something like this. Okay. Now guys, understand very carefully, understand very carefully. I am saying when positive cycle enters, this is I positive, will move from the upper side, and negative cycle will move from the lower side. I negative will move from the lower side. Now guys, positive cycle when enters, D1 will easily allow the positive cycle. Okay. Now guys, it wants to complete its loop something like this, but here D2 will not allow the positive cycle. So what this positive cycle will do, it will flow through this path. It will flow through this path. Okay. It will flow through this path. So this positive cycle will take this path. Okay. And complete its loop. So positive cycle is allowed? Yes. Now guys, what I'll do is that now negative cycle flows something like this. Okay. Now it cannot go through this path because D2 will not allow it. So it will flow. It has also completed the loop. See, negative cycle is also completing the loop. Positive cycle is also completing the loop. Okay. Again, I will show you. Path of the positive cycle is this. Path of the positive cycle is this. And path of the negative cycle is this. Path of the negative cycle is this. Path of the negative cycle is this. Okay. So we say here both the cycles are allowed. And my dear friends, if I make the output over here, if I make the output over here, if I make the output over here, this is positive cycle. Okay. If I make the, let's suppose this is input. This is the input. Okay. This is AC. And when it comes to the direct current DC, when it comes to the direct current DC. Okay. Guys, positive cycle remains positive only. And negative cycle is also converted to the positive because it is now allowed. This will be the output of this. Okay, this is. Now guys, is this output a good output? This output is fluctuating. This output is fluctuating. It is not a good output. This output is fluctuating. It is not a good output. Keep that thing in your mind. Okay. So what do we do instead? We will do one thing. We will connect a capacitive circuit. Guys, fluctuating means this output is becoming maximum, then zero, then maximum, then zero, then maximum, then zero. So means it's a bulb in your light in your room. It is glowing, then it is brightness is glowing, maximum brightness. Again decreasing, zero. Again maximum, again zero. It's not a good output. It's a fluctuating. So we use capacitor filter. Capacitive filter is, what does the capacitive filter do? When the positive cycle flows in this one, okay? At the time this capacitor gets charged. Okay. Now, my dear friends, when positive cycle flows, capacitor gets charged. Now, when the current through the load resistance will try to decrease, at that time, this capacitor will send the energy. At that time, capacitor will send the energy. I would say after using capacitive filter. Capacitive filter. After using capacitive filter. After using capacitive filter. My dear friends, let me show you after using capacitive filter. We say initially this output will increase. Okay. When this output wants to decrease, when this will decrease, this will decrease. This has already charged. Now it will send the energy. it does not let the current output to go down, but it will keep it constant. This is after using the capacitive filter. Again, for the next cycle, I would say, when this current is increasing, this capacitor gets charged. When current will decrease, it will again send the energy, so it maintains the constant output. So this is full wave rectifier over here. Like it is mentioned in this case. Okay. So we use the capacitive filter in the full wave rectifier. This is the output after using the capacitive. Now guys, let's first move on to the Boolean algebra. Okay. Now guys, take a look. When it comes to the Boolean algebra, what do we have to study in the Boolean algebra? See guys, we will be given a device over here, okay? And in this device, we will have to give some input. And this device will provide us the output, okay? Like after some time, I'll be giving you the device which has to do the addition, okay? A device will be given to you which has to do the addition, okay? Like if I say I'll give A, I'll give input as B. What is the work of that device? It will do the operation of addition. Output will be A plus B. So like in this Boolean algebra, we'll have to study different devices which has different work to perform. Okay. Now guys, this input is what we call the digital signal, or this output is also called the digital signal. This is called digital input, digital output, or digital signals. And this digital signal will be in the form of 0 and 1 only. Here, whatever the devices we study, whatever the gates we study, they will have the input and output 0 and 1 only. They cannot have the input 45, 75, something like that. No, it will be 0 and 1 only. 0 also means 0 volts, 1 also means 5 volts. 0 also means low, 1 also means high. 0 also means off, 1 also means on. Okay. Now guys, first thing, addition, multiplication and inverse. First, we'll understand the basic addition, multiplication and inverse in case of the Boolean algebra. Let's suppose you are getting 0 plus 0, 0 plus 0, low plus low is always low. Let's suppose you are getting 0 plus 1, 0 plus 1 is always 1. Let's suppose you are getting high plus high, 1 plus 1 is always 1. In case of, like previously we have studied in our previous classes, normal algebra, 1 plus 2 is 3, 5 plus 4 is 9. Here, in the Boolean algebra, you have only two things, that is 0 and 1, 0 and 1. Now, A plus 0 is A. Sir, what is this A plus 0 as A? You said only here either it can be 0 or 1. Let's suppose I'm saying this is A plus 0, okay? A can be either 0 or 1. A can be either 0 or 1, okay? So, if you put A is equal to 1, so 1 plus 0 is equal to 1. If you put A is equal to 0, 0 plus 0 is equal to 0. So the answer in this case is either coming out to be 1 or 0. So resultant we say A. A can be 0 and 1. So that's why A plus 0 is A. A plus 1. Guys, see, A plus 1. Let's find its answer. If we put A is equal to 1, 1 plus 1 is equal to 1. If we put A is equal to 0, 0 plus 1 is equal to 1. In both the cases, answer is 1. So A plus 1 will be equal to 1. That's why A plus 1 is 1. Now, I'll directly say AB plus BA plus A bar plus this. What is A bar? Guys, if I say 1, inverse of 1 is 0, reverse of 1 is 0. If I say 0, inverse of 0 is 1. If I say A bar means reverse of A. Now, if I say A double bar, that will be A only because these two cancel each other. Sir, how? If I say 1 bar, if you do 1 bar, that will be 0. Okay, do once only, that will be 0. Reverse of 1 bar, reverse of 1 is 0. Now this bar, again do the bar, it will come out to be 1. That's why 1 double bar is 1. 1 double bar is 1. Okay. Now guys, take a look. See. Arey. What is happening? Okay. Now guys, A plus A bar will be equals to 1. Take a look here. 0 into 0 is 0. Low into low is low. 0 into 1 is 0. 1 into 1 is 1. A into 0 is 0. Okay. If you consider A as 1, 1 into 0 is 0. If you consider A as 0, 0 into 0 is also 0. That's why A into 1, how much? So if you consider A as 1, 1 into 1 is 1. If you consider A as 0, 0 into 1 is 0. So that's why we are saying A, because here answer is either 0 or 1. A into A bar will be 0. So this you guys need to learn over here. This is simple, very simple. Then you have De Morgan's law. What does De Morgan's law say? De Morgan's law says if you have A plus B whole bar, and if you want to break this bar, you can, but you have to change this addition to the multiplication. So you can break this bar, A bar, B bar, but change this multiplication. Similarly, if you have A dot B whole bar, if you want to break this bar, you can break it into A bar, B bar, and this is plus. Okay. Break the bond, change the sign. Yes. Commutative law. A plus B is equal to B plus A. Simple. Associative law. A plus B into C is equal to. Now you can take the bracket for these two. A plus B plus C. Distributive law. A into B plus C will be equal to A into B plus A into C. A into B plus A into C. Simple. Okay. Simple. Now guys, you have got three types of gates. You have got three types of gates. Sir, what are gates? As I told you in the starting of the lecture, gates are the devices which will perform the mathematical operations. Like you have fundamental gates, NOT gate, OR gate, AND gate. What is the work of NOT gate? Work of NOT gate is to do mathematical operation inverse. Its job is to do inverse. Whatever the input you give to it, it will do its inverse. Work of OR gate is to do addition. Work of AND is to do multiplication. Okay. Then you have universal gates. In universal gates, you have NAND gate, you have NOR gate. First, we'll learn these three gates. See guys. When it comes to NOT gate, What is the work of NOT? Its job is to do inverse. Let's suppose you are giving the input as A. What will be its output? Whatever you give the input, output will be its bar, because its job is to do the inverse. So its Boolean expression is y is equal to A bar. Let's make the truth table. Truth table is the relation between input and output. If you are giving input A, it will be A bar. If you are giving input 0, it will be 1. If you are giving input 1, it will be 0. Output will be 0. Output will be 0. Keep that thing in your mind. Okay? Now guys, electrical equivalent circuit of NOT gate. You have to make that circuit which exactly behaves like NOT gate. Guys, see. You make a circuit over here. This is bulb and this is key. This is key. Guys. Let's see. Let's make the truth table over here. Let's make the truth table over here. Okay. This is key. This is bulb. When you, let's suppose you keep this key on. You keep this key on. So we say current will leave from this positive terminal. It will flow through the key. Why will it not flow through the bulb? Because current always prefers that path through which there is less resistance. Current always prefers that path through which there is less resistance. Bulb has got resistance. So current will flow through this key. So bulb remains off. Okay. This is 1, this is 0. Okay. When you keep the key on, off. Okay. It is not connected. It is open. It is cut. Then current has only one path, that is through the bulb. Bulb remains. So 1, 0, 0, 1. Don't you think it is exactly matching with this truth table? So we say this is that circuit which exactly behaves like NOT gate. Then you have OR gate. We say the symbol of OR gate is this. The symbol of OR gate is this. Okay. These are the two inputs. This is the symbol. And what is the job of this OR gate? To do the addition, A plus B. This is the Boolean expression, y is equal to A plus B. If we make a truth table, we'll make a truth table like A, B, this is the input, y is equal to A plus B. Let's suppose if you keep one input 0, another 0, 0 plus 0, output will be 0. If you keep this 1, 0, 1 plus 0 is 1. If you keep this 0, 0 plus 1 is 1. If you keep this 1, 1 plus 1 is 1. Okay? 1 plus 1 is 1. One more thing I just want to tell you over here. Guys, see. We say output is high when any of the two inputs is high. Here this is high, here this is high, here both are high. Say output is high when any of the two inputs high. When any of the two inputs is high. And output is low when both the inputs are low. Okay. Now, electrical equivalent circuit of OR gate. You have to make that circuit which exactly behaves like OR gate. Guys, see. Let's take two keys. These are the switches and this is the bulb. Okay, let's make the truth table. Guys, understand very carefully. Let's suppose, my dear friends, if we keep key 1 off, okay, it is open over here, off. Key 2 is also off. Sir, current will leave from the battery. It cannot move forward. This is off, this is off. It cannot go to the bulb. Bulb remains off. Okay. Now, you keep key 1 on, this off. You keep this on. Now, current can flow through this key. Bulb remains on. Now, if you keep this key off and you keep this on, current will flow through this path and bulb remains on. If you keep both on, this on, current can flow through both, bulb remains on. Now see, 0, 0, 0. Compare with this one. 0, 0, 0. Okay. 1, 0, 1. 1, 0, 1. Or you can like see over here. When both the inputs are low, output is low. When any of the two inputs is high, when any of the two inputs is high, output is high. So it is which gate? OR gate. It behaves like OR gate. It exactly behaves like OR. Next, AND gate. AND gate. AND gate. So we say its symbol is this. The symbol of AND gate is this. Okay. This is A, this is B, this is Y is equal to A dot B. Its job is to do the multiplication. Its job is to do the multiplication. Its job is to do the multiplication. Okay. Its job is to do the multiplication. And if you see the truth table, guys, this is 0, this is 0. 0 into 0 is 0. Output is 0. 0 into 1 is 0. 1 into 0 is 0. 1 into 1 is 1. This is the truth table. Now in this case, what will you write? What will you write? See guys. We say output is low when any of the two inputs is low. Here this is low, this is low, this is low. So I say output is low when any of the two inputs is low. Okay. And we say output is high when both the inputs are high. Output is high when both the inputs are high. Next, electrical equivalent circuit for AND gate. This is the electrical equivalent circuit for AND gate. See guys, this is key 1, key 2, and this is bulb. Guys, let's keep key 1 off, key 2 off. This is off, this is off. Bulb remains off. Okay, no current will flow through the bulb. Let's keep key 1 on, key 2 off. Still current cannot flow further because this circuit is open over here. Bulb is off. Let's keep this off, this on. Still, bulb remains off. No current flows through the bulb. So if this is on, this is on, both are on, then only bulb is on. Now you can see over here. Output is low if any of the two inputs is low. Output is high. Output is high when both the inputs are high. Check exactly like AND gate. Now you have got NOR gate. This is a universal gate. What does NOR gate actually mean? Guys, when it comes to the NOR gate, it is simply NOR means, or I can say when you add OR gate plus NOT gate, it forms OR plus NOT is NOR. Okay. What is the output? Guys, like this. This is the symbol of OR gate. This is the symbol of NOT gate. OR plus NOT is equal to NOR. Now guys, you make it as it is. Instead of this NOT, you put the ball over here. This will be the symbol of NOR. Now see, if A and B is the input, what is the job of OR? It will do the addition A plus B. Job of OR is A plus B. Now, this A plus B goes in the NOT. What is the output, guys? Whatever goes inside this NOT, it will do the inverse. So, output is A plus B whole bar. A plus B whole bar. Okay, A plus B whole bar. So what is the Boolean expression? That is A plus B whole bar. So basically, what does the NOR gate do? It will first add the two inputs, then put the bar. That's it. It will first add the two inputs, then put the bar. Like, let's make the truth table. Guys, this is 0, 0. What will be output? 0 plus 0 is 0. And then 0 plus 0 is 0. And then put the bar, it will be 1. Bar of 0 is 1. 0 plus 1 is 1. Put the bar, it will make 0. 1 plus 0 is 1. Put the bar, it will make 0. 1 plus 1 is 1. Put the bar, it will make 0. Now, can I write over here? Can I write over here? We say output is high when both the inputs are low. Output is high when both the inputs are low. Okay. And output is low when any of the two inputs is high. Output is low when any of the two inputs, is high. Let's make the electrical equivalent circuit. Let's make the electrical equivalent circuit for NOR gate. Electrical equivalent circuit for NOR gate. Guys, this is the electrical equivalent circuit. Check, 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 check. Check. This is key 2, this is key 1, and this is the bulb. Guys, in this case, these are the two inputs and this is the output. Guys, see. If K1 is off, K2 is off. K1 is off, K2 is off. Current will be flow from this. This is off, this is off. So current will has to flow through the bulb. Bulb remains on. Okay. When K1 is on, K2 is off. This is on. This is off. Current will prefer this particular path. Okay. Current will complete the loop like this. Sir, why will it not flow through the bulb? Because bulb is a resistance. Current flows that path in which there is less resistance. So this is on, this is off, so bulb remains off. If any of the two keys is on, bulb is off. Now, if this is off, this is on. Current will prefer this path. Current will prefer this path. Okay. On. Okay, now this option. This one. This one is off. This one is on. Bulb remains on. Okay. Now, if both are on, then current will flow through these two. Bulb will remain off. Okay. Now check. Now check. Now check. If both the inputs are low. If both the inputs are low, output is high. Compare with this. Output is low when output is high when both the inputs are low. Output is high when both the inputs are low. That's what I said. And output is low when any of the two inputs is high. See, on, output is low. Check here. Output is low when any of the two inputs is high. So it is exactly matching with that. So it is the electrical equivalent circuit of NOR. Then you have the NAND gate. Then you have the NAND gate. Now guys, see. NAND gate is basically the combination of AND plus NOT, and it forms NAND. Okay. Now guys, the symbol of AND is this. Symbol of NOT is this. Join this AND, join this NOT. Okay. Okay. So now guys, I told you shortcut is make this AND as it is. Instead of this NOT, you make this ball only. You place this ball over here. And when it comes to the Boolean expression, so Boolean expression in this case is y is equal to AB bar. Okay. Now guys, what is the work? Work of this NAND gate is to multiply the two inputs and then put the bar. Multiply two inputs and then put the bar. See, let's suppose if one input is 0, another is 0. 0 into 0 is 0. Now put the bar, it will be 1. Now this is 0, this is 1. 0 into 1 is 0. Okay, now put the bar, it is 1. 1 into 0 is 0. Put the bar, it is 1. 1 into 1 is 1. Put the bar, it will be 0. It will be 0. Okay. Okay. Now guys, electrical equivalent circuit of NAND gate. Let me show you this. Electrical equivalent circuit of NAND gate. Now guys, take a look. You have got K1, you have got K2, and you have got bulb. Okay, K1, K2 and bulb. Let's suppose according to this only we will move. 0, 0, let's say, if both the keys are off, this key is off, this key is off. So current will leave. It has to flow through the bulb. Bulb remains on. Okay. Now let's suppose if this key is off. Okay, like I'll write the statement first over here. We say output is high. Output is high when any of the two inputs is low. Output is high when any of the two inputs is low. Okay. And another statement I'll write. Output is low when both the inputs are high. When both the inputs are low. Now guys, tell me in this case, this is off, and this remains on. Now another one is 0, 1, 1, 0, 0, 1. So this is off and keep this on. If this is off, this is on. So still current will not flow through this one because circuit is broken. And then current has to flow through the bulb. This. Now if this is on and this is off, still this is because current has to flow through. If this is off and this is also off, this off, this off, off we already did, on. This is on and this is on. Now both are on, current will flow through this path only, the bulb remains. bulb remains. You see, this is exactly matching with this, exactly matching with. So we say this is the electrical equivalent circuit of NAND gate. Electrical equivalent of NAND gate. Okay. Okay. Is this clear? Okay. Guys, could you please tell me what did I mention over here? Okay. Could you please tell me what did I mention over here? After this, I'm continuing with the game of NEET 2.0 only. 11 chapters. Yes. After this, I'll be completing your game of NEET 2.0 11 chapters only. Okay. Now, guys, take a look. Guys, this is what we call single input NAND. Basically, when you join the two inputs, it becomes single input. Guys, whatever you send through this, let's suppose A will go in this one also, A will go in this one also. What is the output? Output of NAND gate is basically Y is equal to A dot B bar. But here, both the inputs are A and A. So A into A bar. So it will be A bar. Now, could you please tell me what is the, if your input is A, final output is A bar. Don't you think it behaves like which is a NOT gate? NOT gate. Yes. So single input NAND gate means NOT gate. Similarly, if you have this is what we call NOR gate. Now, guys, join this, this becomes single input NOR. This becomes single input NOR. Let's suppose this is A. This A will go in this one, this A will go in this one. What is the output of NOR? Y is equal to A plus B bar. But here both the inputs are A plus A bar. That will be A bar only. This is also NOT, which is a NOT gate. So, guys, always remember, single input NOR gate is equal to NOT gate. Single input NAND gate is equal to NOT gate. Okay. Let's take a look at this question. The correct Boolean operation represented by the circuit diagram. You guys are supposed to tell me this is the equivalent circuit of which gate? This is the equivalent circuit of which gate? You guys are supposed to tell me this is the equivalent circuit of which gate? Tell me. Guys, make the truth table. Make the truth table as simple as that. Simply. This is K1, this is K2, this is bulb. Guys, this is key 1, this is key 2, and this is bulb. This is a higher potential. This is V is equal to 0 volt over here because this is grounded. So current always flow from higher potential to the lower potential. Now guys, in this particular case, tell me one thing. If I'm saying, I'll keep this K1 on, okay? I'm keeping this K1 on, and this also I'm keeping on, okay? What will happen? Current will flow and it will follow through this path. It will flow through this path and reach over here from higher potential, lower potential. Bulb will not get, this bulb is over here. It will not get the current. So bulb remains off. Okay. Now if I'm saying this is off and this is on, this is off. So current will not flow through this path. Current has only one path, that is through this resistance, through the bulb. So bulb remains on. Now if I'm saying this is on and this is off, still current cannot flow through this path. Current has to flow through the bulb. The bulb remains on. If both are off, bulb remains on. Now tell me, guys, when both the inputs are high, output is low. When any of the two inputs is low, output is high. Which option? Which gate? When both the inputs are high, output is low. Tell me. Output is low when both the inputs are here. Output is low when both the inputs are high. Output is low when both the inputs are high. You see, it is exactly matching with the NAND gate. So it is a NAND gate. Okay. Because output is low when both the inputs are high. Output is high when any of the two inputs is low. Okay. Anya, मेरा सेशन खत्म होने वाला है 5 मिनट में कॉल करूंगा तब हाँ? Now guys, take a look. You guys are supposed to tell me this is the electrical equivalent circuit of which gate. See, I'll make this diagram over here. The bulb. Guys, what you are supposed to do, make the truth table over here. This is K1, this is K2, and this is K1, K2, and this is bulb. Okay. Now do one thing. Keep this K1 and this K2, this on and this on, this on and this on. What will happen to the, guys, if this is on, current can flow through this path and will reach over here. Bulb will not get, bulb remains off. Now, if this is on and this is off, if this is off and this is on, current will still flow through this path, bulb will remain off. Okay. If this is on, okay, if this is first one is off, second one is on, we say current will flow through this path, bulb will not get the current, so bulb remains off. If both are off, then we say current remains on. So this is which gate? It is NOR gate. It is NOR. It is NOR gate. Next you have, what is the, okay, NEET 2018, in the combination of the following gates, in the combination of the following gates, the output Y can be written as, guys, tell me what is the answer of this one? In the combination of the following gates, okay, the output Y can be written in terms of, guys, this is A. Guys, understand, this A will directly go over here. This is which gate? This is which gate? This is OR gate, okay, AND gate, AND gate, AND gate, AND gate. So this is AND, this is AND, okay. This is NOT. So basically this will go over here A, this will go in this particular case B, and what is the job of this NOT gate? Job is to do inverse, so it will B bar, okay. And my dear friends, this gate over here, this is NOT, so this A will directly flow over here, so this will be A bar. This B will directly flow over here, this is B. Now, what is the job of AND gate? To multiply. So this is A into B bar. What is the job of this AND? This is A bar into B. Now this is OR gate. What is the job of OR gate? To do the addition. So this will go as input. This will go as input. Final output Y will come out to be, that is AB bar plus A bar B. This is the final output. Tell me this one. What is the output Y in the following circuit? When all the three inputs A, B, C are first zero and then 1. Guys, in this particular case, if you put all the three inputs first 0, okay, this is AND gate, this is NAND gate, okay, put all the three as 0. This is 0, 0 and 0. What is the job of AND? Its job is to multiply. 0 into 0, it will be 0. Now this 0 will go as it is. Now guys, in this case, what is the job of NAND? Its job is to multiply and then put the bar. Guys, this NAND will multiply 0 and 0, then will put the bar. 0 into 0 is 0 and its bar is 1. Final output will be 1. So if, mention over here, so if all are 0, output is. Now guys, let's put over here all the three as 1. 1, 1, 1. Its job is to multiply. 1 into 1 is 1 and this 1 will go as it is. Now, what is the work of NAND? Work of NAND is to multiply. Then put the bar. 1 into 1 is 1. Bar of 1 is 0. So final output will be 0. When all are 1, then output is 0. The final result is option D. Okay, we are done with this chapter also. One thing I will tell you over here. What is that? What is that? Okay. Guys, you have got, I hope this is also clear to each and every single student. Okay. I hope this is also clear to each and every single student. There is no confusion in this one. Let me show you this one. A bar plus A bar, how is it 1? Guys. If you say in this particular case, if A is 1, okay, and put A bar, if you put A bar is equal to 1, guys, simply, if you put A bar is equal to 1 over here, this, if you put A is equal to 1, and this will be 1 bar is 0, 1 plus 0 is 1. If you put A is equal to 0, 0 bar is 1, 0 plus 1 is again 1. That's why we are getting 1 over here. I hope you would be able to do these, okay? I think all the things are crystal and clear now. So I guess we need to end the session, and guys, I would want you guys to write down in the comments later on, not later on, once I end the live stream. Do let me know in the comments how was the session, okay? So thank you so much. Done and okay. Guys, do let me know in the comments how was the session. I'll be waiting for your comments. Everybody out there. So take care and bye-bye. Thank you so much. Anya, इसको एंड कर दो, थोड़ा जल्दी लेट हो गया, बड़ा होने वाला 12 घंटे का।